to you starting. Get Helga down and okay. Okay, we're ready to start. So this is the opening ceremony of the 2022 virtual ICM. I am Carlos Koenig, the president of the IMU, and I would like to welcome those of you here in person and the great majority of you who are participating online to the 2022 virtual ICM. As many of you know, the 2022 General Assembly of the IMU and the 2022 ICM were scheduled to take place this July in St. Petersburg, Russia. This did not happen. Due to the brutal and unprovoked Russian invasion of Ukraine, the Executive Committee of the IMU decided at its scheduled virtual annual meeting in February 2022 that it would be impossible to host the scheduled GA and ICM in Russia. The EC expressed at this time, and we reiterate it here today, its deepest sympathy to the Ukrainian people and to our Ukrainian colleagues in these grave moments. At this meeting, the EC decided to have the GA as a traditional in-person event outside of Russia. After receiving several generous offers from our members, we decided to accept the extremely generous offer from Finland to host the GA. The GA was successfully held in Helsinki 2 days ago, and many important decisions for the future of our union were taken there. The ICM is a much more complex and extensive event than the GA. At the same EC meeting, we also decided on how to proceed with the ICM. Since ICM speakers had already been selected and notified, and the EC had a strong desire to follow the tradition of reporting the most exciting mathematical events of the last 4 years, and given the infeasibility of alternative options, we decided to opt for a fully virtual ICM with its organization taken over by the EC. Modern technology and the pandemic experience made this a feasible option. The ongoing barbaric war that Russia still continues to wage against Ukraine shows that no other alternative was feasible. The organization of the virtual ICM has been an enormously challenging and labor-intensive task. It had to be carried out under a very difficult financial situation, and it has put a severe strain on IMU personnel, since we cut off entirely the financial and organizational ties that Russia had been providing. We are immensely grateful to the Heidelberg Laureate Forum Foundation for its very generous financial support. We are also indebted to the London Mathematical Society, Japan Mathematical Society, NTNU, the Norwegian University of Science and Technology, the Committee for Developing Countries of the IMU, the International Commission for Mathematical Instruction, another commission of the IMU, and the Friends of the IMU for generous financial support. The IMU is also extremely grateful to the IMU Secretary General, Helge Holden, and to the IMU staff at the Secretariat in Berlin, especially to Scott Young, the IMU manager, and Vanessa Chung, the IMU assistant, for their remarkable efforts in dealing with the many administrative and logistic challenges that arose. We are also especially thankful to EC members, Nalini Yoshi and Paolo Piccione, and to Martin Heyer, chair of the program committee, for their very valuable help in the preparation of the virtual ICM. The so-called Satellite Coordination Group, moderated by Alexis Borodin, Martin Heyer, and Terry Tao, has worked independently of the IMU to coordinate the organization of various community-based overlay events in conjunction with the virtual ICM. We are very grateful for all these efforts. We are all now greatly looking forward to this wonderful opportunity to learn about the most important mathematical discoveries of the last 4 years unfolding in the next 9 days. The scientific organization of an ICM is a daunting task. There are 2 very important committees of the IMU dedicated to this. The first one is the Structure Committee, whose charge is to decide the scientific structure of the Congress. This is the inaugural Congress for the Structure Committee, which is to remain a standing committee with rotating membership to enable the continuous evaluation and revision of the scientific structure of the Congress. The Structure Committee is chaired by Terry Tao from UCLA. The second committee is the Program Committee, whose charge is to select the speakers for the Congress. It is chaired by Martin Heyer from Imperial College, and the PC carried out its work with the advice of 20 sectional panels. We are extremely thankful to all these selfless volunteers that did a wonderful job in developing the outstanding scientific organization of the Congress. Traditionally, at the open ceremony of an ICM, there is an award ceremony at which all the recipients of the IMU prizes are announced. At the virtual February 22, 2022 meeting of the EC, it was decided that on July the 5th, the day after the GA, there would be a live award ceremony at which all the IMU prizes will be awarded. This took place yesterday in Helsinki, like this in-person event, with the generous help of our Finnish colleagues. At this time, Hugo Duminil-Copin, Jun Ho, James Maynard, and Marina Wiezowska were awarded the 2022 Fields Medal. Mark Braverman was awarded the inaugural IMU Abacus Medal. Barry Mazur was awarded the Churn Medal. Elliot Lieb was awarded the Gauss Prize, and Nikolai Andreev was awarded the Lilavati Prize. Today, July the 6th, is the opening day of the virtual ICM. We will take advantage of the fact that the Fields medalists and the IMU Abacus medalists are all present in Helsinki, so that the recipients will be giving their ICM plenary talks in front of a live audience in Helsinki. Their lectures will, of course, also be streamed via the virtual ICM platform, for those who are not fortunate enough to be in Helsinki today. So without further ado, I declare the 2022 virtual ICM open. Thank you.
Good morning, everybody in this room, and hopefully the 7,000 people participating remotely at this ICM, which is an all-time high for participation at an ICM. So there is a tradition that before we go to the important part, the reason why you're all here, to listen to mathematics, there will be a brief report on the activities of the International Mathematical Union during the last 4 years. So I will give this report and stress some of the highlights and some of the challenges we have been facing over the last 4 years. So I will report on what we have done over the last 4 years and some of the highlights from the General Assembly that we finished 2 days ago. And of course, this term was characterized by 2 big events on a global scale: the COVID-19 pandemic and the Russian invasion of Ukraine starting February 24. So let me start with the pandemic. First of all, I would like, on behalf of the IMU, to express our mourn for the loss of millions of people all over the world due to this pandemic. And we also express our deepest sympathy with all that lost their jobs during this pandemic. It has affected the daily life of everyone on the planet. Also for people in academia, we have turned into remote teaching, video meetings, hybrid and fully virtual conferences, and it has not all been that successful, but we have learned to cope with it. It has also stressed the importance of basic research and the importance of a high-speed, dependent internet. Without that, we would not have come out of this pandemic. I will stress in the next slides the consequence for mathematics. But we have been able to profit from the pandemic, at least in the past. So if we go back to 1665, the University of Cambridge had to close due to the Great Plague, and the young Isaac Newton had to go back home. He remained there for 2 years, no internet, no library, no nothing, but in spite of this, he developed theory of calculus, optics, and gravitation. No similar progress has been reported during the COVID-19 pandemic. So a key task for the ICM, for the IMU, is to work on the next ICM. And we started at the first meeting in Berlin in 2019, and we have discussed it every meeting ever since then. The collaboration with the Russian organizers went very well during the period. However, due to the invasion by Russia on Ukraine on February 24, it was clear that we could not go along according to the plans that we had made. So we issued several statements. We were having a meeting, as Carlos said, starting February 24, that had been scheduled a year in advance. So we decided quickly that the General Assembly would be organized outside Russia on the same dates. The ICM would be organized as a fully virtual congress, starting the same date as was planned. There will be an award ceremony as a unique event that happened yesterday, and it was a great event. And that the ICM would be open to every participant worldwide. We also decided that the General Assembly and the ICM would be conducted without any financial contribution from the Russian government. And no official representative from the Russian government will be part of the organization and the activities of the ICM. We have received generous support for the organization of the General Assembly, the award ceremony, and the virtual ICM, and we could not have done it without that support. The institutions are listed here. I would like to stress once again the very generous support from Heidelberg Laureate Forum Foundation and the Council of Finnish Academies. Without the support of these two institutions, we could not have pulled it off. That's the full story. So now comes the structure of the ICM. As Carlos said, it's comprised by two serious committees that do a lot of work. The first is a structure committee that decides, as the name says, the structure of the ICM. What are the panels? How big should they be? Should there be special lectures dedicated to certain topics? And this has been chaired by Terry Tao. And a challenge for me will be to read these names, because some of them are difficult for me. Terry Tao, Carlos Koenig as the IMU president, ex officio member. Nalini Anatararam, Alexei Borodin, Annalisa Buffa, Elene No, Irene Fonseca, Terry Lyons, Stefan Mala, Hiraku Nakajima, Eva Taros, Peter Teichner, Akshay Venkatesh, and Anna Wienhardt. So they are responsible for the format of this ICM that we are going to enjoy the next weeks. The program committee used to have this task. As of this ICM, they have the task of selecting the 220 speakers. This committee, except for the chair, is kept confidential until this day. So it was chaired by Martin Heyer, as Carlos said, and the other members were Sanjeev Arora, Anna-Karin Thornberg, Shafi Goldwasser, Ursula Hammerstadt, Sergei Ivanov, Mikhail Kapranov, Yiming Long, Felix Otto, Jonathan Pila, Venkarataramana, Jori Williamson. In addition, they had one panel for each of the sections, which amounts to about 20 panels, each of them comprising a number of participants or members. So all in all, there are equally many people involved in the selection of the speakers as there are speakers. So it's a big task. It's a big task, and the result we will see in the following week. We have prize committees for the awards that we are giving out, and we saw the result of their selection yesterday. But the membership of these committees have been kept confidential until this day. So for the Fields Medal Committee, it was chaired, as the tradition is, by Carlos Koenig, the president, Arthur Avila, Camilo Di Lellis, Michael Hopkins, Antti Kupiainen, Rahul Pandiripande, Alfio Cateroni, Vera Serganova, Lorentzian Polynomials, Richard Taylor, Wai-Ping Tsang, and Tamar Ziegler. And we can see the result of their selection yesterday. So the new IMU Abacus Medal was awarded for the first time yesterday, very appropriately in Finland, because it is sponsored by Finland and the Science Foundation. So this was chaired by James Demel from the US, and other members, Annalisa Buffa, Mihima Maharajan, Amit Singer, and Dan Spielman. And as you all know, this is for outstanding contribution in mathematical aspects of information science. So the two awards here, the Fields Medal and the Abacus, are for scientists below 40. The Gauss Prize is awarded to honor scientists whose mathematical research has an impact outside mathematics. And this committee was chaired by Eva Taros, and other members were Liliana Borsea, Albert Cohen, Bernd Stumfels, and Tao Tang. The Churn Prize Committee comprised Jakob Eli Aschberg, Alice Chang, Henri Darmon, Alice Guionnet, and Hiraku Nakajima. And this is to recognize the highest level of outstanding achievements in the field of mathematics. So no restrictions on field or anything. The last prize is going in a rather different direction. It's the Lelavati Prize, and this was chaired by Pavel Ettinghoff, Kanan Sundarajayan, Tadashi Tokiheda, Chandrasekhar Kar, Michel Artigue. And this is for increasing the public awareness of mathematics. And this is in a different direction from the other prizes, but it's very well received in the community, and it's very important for us. So now, at the recently concluded General Assembly, we elected, or rather the General Assembly elected, the new leadership for the next 4 years. So for the present Executive Committee, it comprises Carlos Koenig, Helge Holden, Nalini Joshi, Loiso Nongsa, Luigi Ambrosio, Andrei Okunkov, Paolo Piccione, Ramadas, Gang Tian, Günther Ziegler, and as past president, Shigefumi Mori. So our term expires December 31st this year. The new leadership of the IMU comprises the following EC: Hiraku Nakajima as the new president, Christoph Sorger as the new Secretary General, Ulrike Tillman and Tatiana Toro as the new presidents, vice presidents. Members at large is Mohammed Mustafa Fall, Nalini Joshi, Yong Hakum, Paolo Piccione, Günther Ziegler, and Tamar Ziegler. And Carlos will continue as a past president for the next 4 years. We also have a Commission for Developing Countries that does outstanding work in this area. The present leadership comprises Dipendra Prasad, Olga Gil Medrano, Alf Unsus, Mama, he goes by the name Mama, so I stopped there, Jose Balmaceda, Andrea Solatar. And in addition, Michelle Malschmidt and Galina Russo, and Anjum Halai and Jean-Luc Dorier. And they are working very hard to support mathematics and mathematicians in developing countries. And their term will also end December 31st. The new leadership comprises the following members: Andrea Solotar, Maria Balmaceda, Jose Balmaceda, Ludovic Rifford, Norbert Hunkuno, Le Tuan Hua, and Marielle Saez. And there are some additional members that will be appointed later. We also have a commission for the history of mathematics, and in the previous term, Isabel Falconer and Catherine Goldstein were members from the IMU side, and as newly elected members of the committee starting next year, Guillermo Curbera and Isabel Falconer are our representatives in this commission, which is a joint commission between the IMU and the Division of History of Science and Technology of the International Union of History and Philosophy of Science and Technology. They maybe should work on abbreviating their name slightly, but that will be their task. So we have had some changes in the membership over the last 4 years. But fortunately, we did not lose any regular members, but we have gained some new. So new members in Group 1 is Belarus, Cyprus, and Kyrgyzstan. We have a new associate member, Mongolia. I'm also happy to report that several members advanced in the adherence. So from associate member to Group 1 is Uzbekistan, from Group 1 to Group 2, Indonesia, from Group 2 to Group 3, Chile, Denmark, and Portugal, and from Group 4 to Group 5, which is the highest group, the Republic of Korea. And this is a sign of the development of mathematics worldwide. It's a very good sign that the countries advance in the adherence group. Unfortunately, Cambodia, Madagascar, Moldova, and Nepal had been associate members of the IMU for 2 periods, and they were not able to advance at this point to become regular members. But we hope to see them back in the near future as regular members. So we have 5 commissions and committees that do a lot of work for the IMU. We have the Commission on Mathematical Instruction, which is Math Education. We have the Commission for Developing Countries. We have the Commission on History of Mathematics, Committee for Electronic Information and Communication, and Committee for Women in Mathematics. And we have Friends of IMU. We also have 2 ad hoc committees that we established during the last term, namely a Committee on Diversity. Diversity is a very important aspect of our activities. It gets more focus, and this is well deserved, and we have to see how we can improve our performance regarding diversity. We also have an ad hoc committee on permissions. Permissions, this is to get access to our journals freely after maybe a short window where the publishers have to take money. So they're working on permissions regarding publications. So, because I'm not giving the full justice when I report in one line on the activities of a commission and committee over 4 years. So the ICMI successfully held its quadrennial conference, ICMI 14, in Shanghai as a hybrid meeting in 21. It was scheduled to take place in 20, but it has to be postponed for the reasons you know, for a year. CDC took the opportunity when all travel come to a halt during the pandemic to look for other ways to deliver on its remit. And I think we learned something from this that we can take advantage of in the future. The Committee for Women in Mathematics established that standing committee for gender equality in science in collaboration with other organizations. But the CWM took a leading role in this standing committee. The Committee for Electronic Information and Communication established this committee on permissions to advise us in how we can negotiate regarding open access. The Commission on History of Mathematics organized several meetings with other organizations. There was one great new initiative over the last 4 years that I want to report on, namely the International Day of Mathematics. So on November 26, 2019, UNESCO declared March 14, in many countries called Pi Day, as the official International Day of Mathematics. We set up a governing board to carry out the work for the IDM. And this allows us to reach out to new groups. Let's face it, the IMU is mostly involving research mathematicians, but the IDM lets us reach out to other young kids, adults, and people not involved in research mathematics on a global scale. So this is a very valuable addition to the activities of the IMU. During the last 4 years, we also passed our Centennial. So in 20 September in 1920, the IMU was established in Strasbourg. So we planned to do a meeting in Strasbourg, the same building, almost the same date, 100 years later. We had to postpone it for a year due to the pandemic, but we were able to carry out an almost in-person meeting. Some lectures were given virtually, but most people were actually in the room. And this was a great event for all of us who were there. Also taking the advantage of that we were celebrating our Centennial, we solicited in May 2019 the writing of a book on the history of mathematics. And the project was generously funded by Klaus Gira Foundation. And the book was written by the mathematician and historian Norbert Schappacher. We insisted that this book had to be freely available to everyone from day one. And it is. And you can go to SpringerLink and download it for free. And it has to remain that way. We want to reach out to everybody so that everybody can read it. It's a very good book, very interesting, and I recommend it to everybody. So we made some decisions at the General Assembly that have consequences outside the meeting. So we decided to change the IMU status. That does not happen very often. So we added a new article. And it says the following: the Union adheres to the International Science Council's principle of embodying the free and responsible practice of science, freedom of movement, association, expression, and communication for scientists, as well as equitable opportunities for access to science, its production and benefits, access to data, information, and research material, and actively upholds this principle by opposing any discrimination on the basis of such factors as ethnic origin, religion, citizenship, language, political and other opinion, gender identity and sexual orientation, disability or age. And this was passed unanimously at the General Assembly. I think this is a great decision, and hopefully we will live up to this. That's the hardest part. So we are approaching the end of my presentation. So as Carlos said in his opening address, we discussed the situation in Ukraine and also the situation for many other countries that are in a position where it's very hard to pay their membership dues. So the first resolution, the IMU expresses the support for all mathematicians affected by the war in Ukraine. And in particular calls upon its members and other scientific organizations to do everything they can to assist our Ukrainian colleagues in these difficult times. Passed unanimously. The IMU will set up a reserve fund to help adhering organizations whose dues are in arrears due to temporary extreme adverse circumstances. The reserve fund will be funded by earmarked contributions. Requests for help will be considered by the IMU Executive Committee, who will decide on them on a case-by-case basis. The IMU Executive Committee will report to the next General Assembly on the working of this program. And we hope this can be a temporary relief for some of the countries that are facing problems paying the membership dues. It's not a permanent solution for these countries, but it's a temporary solution. The final resolution, and again, this was passed unanimously. The final resolution was in response to a request from the Ukrainian Mathematics Union. We resolved to waive the IMU membership dues for the Ukrainian Mathematics Union for the years 2022 and 2023, unless these fees are covered by third party or third parties. And I'm happy to report that we had many volunteers to cover the dues of the Ukrainian Mathematical Society. My final slide is this one. So we are going to meet in 4 years, hopefully in person, for the next ICM. The General Assembly will be in New York City on July 19-20, and the ICM will be in Philadelphia on July 20 to 22 to 29, 2026. We have been on a site visit, looked at the venue. it's going to be a great event. So I recommend everybody to come to Philadelphia for the ICM in 2026. So with that, I think it's time for mathematics. So thank you very much. So if you look at the schedule, we still have some time, which means that we will have a break now. So you can go outside, take a coffee, talk with the person sitting next to you, or check your email.
Hello, everyone. Welcome to the first of our Fields Medalist lectures. It's my pleasure and honor to introduce our first speaker, James Maynard. James Maynard got his PhD under the supervision of Roger Heath Brown from Oxford in 2013. From 2013 to 2014, he was a postdoctoral fellow at the CRM in Montreal under the supervision of Andrew Granville. Subsequently, James was a Clay Research Fellow, and since 2018, he's been a professor at Oxford University. He's received many awards for his spectacular work. These include the Sastra Ramanujan Prize, the Whitehead Prize, the Prize of the European Math Society, the Cole Prize, and of course, yesterday, the Fields Medal. James?
Okay, thank you very much, Sound, for the introduction, and it's a great honor to be talking to everyone here as the first mathematical talk of this 2022 Mathematical Congress. So because this is a fairly mixed audience, my talk is going to be something of a survey talk of an area of mathematics that's very close to my heart, which is that of counting prime numbers. So I'm hoping that my talk will be reasonably accessible for a general mathematician, but there might also be some bits and pieces that will keep the experts interested. So hopefully there's a little bit of everything, a little bit for everyone. So in the general field of counting prime numbers, the main question that I'm often interested in my research is you give me your favorite set of integers, let's call that set A, and then the challenge is how many primes are there in the set A? So depending on the context, you might be asking for whether there's finitely many primes or infinitely many primes, or you might be asking for some density for how often primes occur in A. And just so that we're on the same page, maybe I'll start off with a couple of somewhat simple examples. So maybe the simplest set of integers that you could consider is the set of all integers. And so then we'd just be asking for how many primes are there. And in this case, we know it goes back to the ancient Greeks that there's infinitely many primes in our set. It's the prime number theorem, a classic of the number theory from a bit over 100 years ago, that we get an asymptotic count for the density of primes. But if you start asking for more refined quantitative questions, then you start getting into questions that are very closely connected to the Riemann hypothesis, where Riemann has two ends. So that's one example where we have a pretty satisfactory answer to lots of the basic versions of this question, but when you start asking for more quantitative refined questions, we quite quickly get into questions that we don't know how to answer, that are connected to some of the most famous open problems in mathematics. A second example, which is certainly a favorite example of mine, is you could take the prime numbers and shift them along by 2. And so in this case, we'd be asking, are there infinitely many twin primes, or how many twin primes are there? So pairs of primes that differ by exactly 2. And essentially, beyond computational evidence, nothing is really known in this case for how many primes there are. So it's believed, the twin prime conjecture, that there should be infinitely many pairs of primes that differ by 2, which would be saying that there's infinitely many primes in the set A. And moreover, you could make precise asymptotic guesses for the density of the number of twin primes, which fit as well as you could possibly hope with computational evidence, but we don't know how to really prove anything in this context. But both of these two examples are maybe somewhat representative of the sorts of things that I like to think about, where if you take any reasonably dense set of integers, so sparse sequences can have lots more complicated behavior, but if you take some reasonably dense set of integers, then we expect that there should be infinitely many primes in this set, And in fact, we expect there should be maybe some fairly nice asymptotic formulas for most sets that come up of interest, unless there's some simple reason why not. So there are some obvious obstructions to fairly dense sets containing infinitely many prime numbers. If your set only contained numbers which were the multiple of some fixed small prime, then obviously they wouldn't contain infinitely many numbers. Similarly, if you were contained in the value set of a reducible polynomial or something, then you certainly can't contain infinitely many prime numbers. But our mindset and philosophy in this area is always that either there's some very simple to explain reason why your set wouldn't contain lots of prime numbers, or it should contain lots of prime numbers. And the challenge then is just to try and prove that it should contain lots of prime numbers. And from a theoretical point of view, finding one prime number, if you're not allowed to just use a computer to try and find one prime number, is often seems as difficult as actually finding lots of prime numbers. And so even if you just want to prove the existence of a single prime in a set A, often we're trying to come up with some theoretical way to count primes and show, in fact, that there's many primes in set A. So maybe the most basic way to count prime numbers is using ideas from multiplicative number theory. And here the key property of the primes that multiplicative number theory uses is that the fundamental theorem of arithmetic that the primes generate the positive integers via multiplication. And essentially, because of the fundamental theorem of arithmetic and its variance over number fields and things, you can define certain nice generating functions, L functions, which encode lots of the properties of the prime numbers. On the one hand, you have some product formula. So this is the most basic L function, the Riemann zeta function, which is great for studying just the count of primes. But there's a whole slew of different L functions that can study different refined questions about primes. And on the one hand, you have this product formula, which is related to the primes. On the other hand, you have some Dirichlet-Sears representation, which is related to the integers. And so you can try and understand the primes through understanding the integers. And in this way, you can understand properties of the primes can be re-encoded as maybe analytic properties of a corresponding L function. And this turns out to be an exceptionally fruitful way of studying prime numbers, which is well over 100 years old. So it turns out that although we certainly have lots of techniques that don't count as multiplicative number theory and are rather different to these sets of techniques, these multiplicative techniques are almost the only results that really somehow produce prime numbers. And so from this perspective, a huge number of results on counting primes in some set of integers can be viewed as some elaborate set of complicated maneuvers to relate the count of primes in your complicated set of integers to the count of just prime numbers themselves, which you can then understand using techniques from multiplicative number theory. And one important aspect is that because these L functions really encode very deep properties and symmetries within the prime numbers, which means that despite the philosophy that the primes should behave in a sort of somewhat random way, and any reasonably dense set should contain primes unless there's some good reason why they don't contain primes, the existence of zeros of these L functions actually means that there's some slightly subtle differences between the prime numbers in a completely general random sequence with similar density and similar small divisibility properties. And so this indicates that there is some underlying structure in the primes which does cause slight differences to what you might naively expect. But nevertheless, the hope would be that if you want to count primes in your set A, then you'll find some then the only way that your set A could not contain primes would be if there's some strong, strange conspiracy amongst the prime numbers, and you hope to find some simple statistic to do with the prime numbers, which could then rule out that conspiracy. And ultimately, this statistic you want to be able to prove by relating this statistic about prime numbers to some technique in multiplicative number theory, which is how we can finally produce primes. So multiplicative number theory is maybe one of the oldest ways to really count primes, maybe one of the most successful, but it's sort of a blessing and a curse at the same time, because there's many different important open problems in multiplicative number theory that remain unsolved, but seem very, very difficult problems. So obviously there's the famous Riemann hypothesis. For lots of the applications to prime numbers, you don't actually need something quite as strong as the Riemann hypothesis. So often, rather than saying all the zeros lie on the half-line, it's sometimes sufficient to have a suitable zero-free region. So if you could say there's a large region of the complex plane or the critical strip which doesn't contain zeros, that might be a sufficient substitute. Sometimes zero density estimates, which say even if it's possible that there might be some zeros lying off the critical line, provided there's sufficiently few zeros close to the critical line, often that can be an unconditional substitute for the Riemann hypothesis, and the zero density estimates very closely related to other properties of, say, the Riemann zeta function, like the Lindelof hypothesis or bounds for the moments of the zeta function. But unfortunately, although we have partial progress in the direction of many of these substitutes for the Riemann hypothesis, we also have pretty hard barriers, and many of these questions have resisted any progress for the best part of 80 years or so. So we feel like, unfortunately, we're a little bit stuck, even if we do have these very high-profile important questions related to the distribution and counting primes using multiplicative number theory. In a slightly different direction, as well as just looking at basic L functions like the Riemann zeta function, you can often look at higher degree L functions, and then questions to do with uniformity of conductors and how the aspects of the L function depend on the key parameters that define the L function, turn out to be very important for related questions on primes. But in exactly the same way that there's difficult famous questions, despite, say, for example, very recent important progress on subconvexity, there's still many well-known difficult open problems which we've been stuck on for a very long period of time, maybe most notably the question of z equals zeros, but also dependence on the discriminant, and obviously questions to do with just basic analytic properties and automorphy is a major subject in algebraic number theory. So in summary, multiplicative number theory gives us some very powerful tools which are very successful in counting primes in very straightforward, in some ways, multiplicatively structured sets. But there's maybe two key drawbacks. One is that to make further progress, we quite quickly run into very difficult problems which are related to the Riemann hypothesis, and the other maybe key problem with multiplicative number theory is that they're really manipulating structure in the underlying set by trying to make use of multiplicative properties of the set. And so as soon as you have a set which isn't somehow multiplicative in nature, often these techniques break down completely. So for example, there doesn't seem to be any natural way for multiplicative techniques to naturally say something about twin primes, because the mixture of addition and multiplication causes there to be a complete lack of multiplicative structure in the sets that you're looking at. And so this means that there's a slight all-or-nothing approach, that multiplicative techniques, when they work, give you often very nice answers, but they only work in structured situations, and so they're not so flexible to other different situations. And so to make further progress, we need more flexible techniques which can either give some partial results, or can reduce less structured questions to a more structured question, which we can then use techniques from multiplicative number theory. Just before I finish talking about multiplicative number theory, I thought I'd highlight a couple of slightly technical questions, which are some questions that I like to come back to and certainly interest me. So I mentioned zero density estimates. It turns out that the sort of fundamental question for zero density estimates is just trying to calculate large values of one very specific Dirichlet polynomial. So I'd just like to advertise this as a question that I come back to and I sort of think about once a month and I make virtually no progress on, and we've been stuck on for 80 years, but you can just take one very specific Dirichlet polynomial where you take the sum of n to the power it for integers n between some large t to the power 2/5 and 2 times t to the power 2/5. So then this is for some given large value of capital T. This is I'm thinking of this as a function of little t, and I want to count the number of real values in a Lebesgue measure sense, the number of little t's between maybe capital T and 2 times capital T when this takes a large value. And here there's some precise quantification of what I mean by a large value, and I want to show that this Dirichlet polynomial takes large values suitably frequently, and if we could make progress on this one somehow very concrete specific problem, then we'd make progress on zero density estimates and a whole host of questions to do with prime numbers. And related to this problem is also the question as to what happens if we really can't make progress on this. So imagine that we can't improve zero density estimates, and somehow the current zero density estimates we have, or you could imagine a theoretical world where the Riemann-Zeta function does have several counterexamples to the Riemann hypothesis. What precisely would the configuration of zeros have to look like? That it's certainly my belief that actually, even if there were a number of counterexamples to the Riemann hypothesis, the zeros would have to look really quite structured and have certain patterns to them for them to really still cause a barrier to counting prime numbers. And so even if there were exceptions, a random collection of zeros would cause virtually no problems from the point of view of just counting prime numbers. And so certainly one question that I've thought about quite a bit recently is what patterns of zeros are really the things that prevent progress. So we know, for example, based on zero density estimates, that it's only many zeros on the line, or very close to the line, real part of S equals 3/4 that could possibly cause problems. But equally, recent work with Karl Pratt shows that this can't be the only obstruction, and there's more subtleties. It's not just zeros on the 3/4 line which are the relevant thing here. Okay. So moving on from multiplicative number theory, to counteract the issues that multiplicative number theory somehow can't make partial progress on sets that don't have a strong multiplicative structure, the key alternative method that we have developed for saying something about prime numbers is Sieve methods. So Sieve methods fundamentally forget that the fundamental theorem of arithmetic and that primes generate the whole numbers. The key property of prime numbers from the point of view of Sieve methods are prime numbers are integers with no small prime factors. And so when you think about prime numbers in this way, a very natural thing to try and count the number of primes in your set A would be to do inclusion-exclusion, where you can think about Sieve in your set, where first of all you remove from your set all multiples of 2, then you remove all multiples of 3, and so on. And hopefully at the end of this process you might be left with primes in A, or if you stop the process early, you might just be left with numbers with no small prime factors. And it turns out that, well, for you to possibly be able to say something like this, you need to have some understanding of the number of elements of your set A of interest which have which are a multiple of 2 or a multiple of 3, and so you need to have some moderate understanding of your set A in arithmetic progressions. There's a sort of technical version of what we typically really need to assume from the point of view of Sieve methods, but the technical formula here doesn't matter so much. The key point is that we just need some fairly moderate understanding of our set in arithmetic progressions, which turns out we do have for a huge number of the sets of interest. And this means that provided we are set A, we do have some moderate understanding in arithmetic progressions, then essentially standard Sieve methods can give some certainly useful partial information about the number of primes in the set A. So if we do have this fairly weak assumption, which holds in most cases of interest, then almost for free, we get good upper bounds for the number of primes in your set A. So you can't necessarily prove that there are primes, but you can prove that there aren't too many primes compared to what we would guess. And you can get nice counts, not for the primes, but for numbers with no small prime factors, or maybe just a bounded number of prime factors. So for example, by using this basic philosophy, it's now very straightforward to show that even though we can't show that there are infinitely many twin primes, we can show that there aren't many more twin primes than the expected amount. So it's very straightforward to show that there's the number of twin primes up to x is at most 100 times what we would expect. And so we get upper bounds with the right order of magnitude, and as well as on their own saying something about the number of primes in a set A, it turns out that these Sieve methods are an exceptionally useful initial step to get you into a situation where you're close to counting primes. And so as well as just black box results on the number of primes in a set, Sieve methods are an absolutely vital sort of intermediate technical tool to combine with other methods. And yeah, I guess maybe I'll just stress that the key advantage of Sieve methods is that even though the conclusions aren't quite as strong as we'd like, it's exceptionally flexible and it applies to lots of different sets A that you might be interested in. Morally, what sieves are good at is controlling small prime factors. So they show that for any set A where you have a reasonable control over the set in arithmetic progressions, the divisibility by small prime factors behaves as if these small primes were roughly independent of one another. And because they're independent of one another, almost all sets behave in roughly the same sort of way, and therefore you can get very nice answers that don't depend too much on the underlying structure of your set, just some basic properties of how the set works in arithmetic progressions. However, the large prime factors are necessarily going to be much more complicated because they're discrete objects and the number of large prime factors of elements will vary from one set to another set. And so you can't just use knowledge about your set A in arithmetic progressions to fully control the effect of the large prime factors. And Sieve methods can still say something about large prime factors, but for any given question, how you arrange your sieve to try and control the large prime factors remains a bit of a poorly understood art. So I often tell my students that controlling small primes is a science. We know exactly what we're doing with sieve methods, but controlling large prime factors is a bit of an art, and almost any sieve that's worth the name can control small prime factors in a very good way, whereas often for an individual problem, if you want to get the best possible results, the sieve has to be tailored for the specific application when you care about how you're controlling the large prime factors. Yeah, I guess as I mentioned, there's many things that we still don't fully understand about how to try and control these large prime factors. So in particular, if all I know about my set is a reasonable understanding of the distribution of the set in arithmetic progressions, a very natural question is, how well can we control the large prime factors given only this information? We know that we can't control them perfectly. We have pretty satisfactory answers in the so-called linear sieve setting, but outside of this linear sieve setting, our knowledge is still pretty poor, and in particular, high degree or high dimensional sieves, we really have a pretty weak understanding of what sort of bounds would be the optimal bounds, or from a dual perspective, what would be the extremal sets that would have either the maximum or the minimum number of primes, given some understanding of our set in arithmetic progressions. So, as was mentioned in the laudatio, progress on bounding gaps between primes and clusters of primes come together, particularly some of my work and work with collaborators, has been looking at these high-dimensional sieves and finding optimized high-dimensional sieves that do rather better than we previously knew how to do, at least tailored to a very specific application. So that's one concrete example of high-dimensional sieves being useful in practice for questions about prime numbers. The other sort of very natural and important question is we can't expect to go too far based on just an understanding of our set A in arithmetic progressions, and so a natural question is what extra types of arithmetic properties of our set A can be usefully incorporated into this method. So I'm going to talk quite a bit later on about one specific type of arithmetic information that can be used to improve the situation and improve the bounds that come out of sieves. But I think it's certainly an important question to think about what other types of arithmetic information can be used and what other properties of our set can be used to, beyond just our set in arithmetic progressions, can be used to get improved bounds. So very famously, Churn got a partial result towards the twin prime conjecture, showing that there's infinitely many primes p, such that p plus 2 has at most 2 prime factors, by precisely exploiting extra structure and arithmetic structure in the set still in a fairly traditional sieve method from a sieve method point of view, but this allowed him to improve on just the standard sieve bounds when you have extra arithmetic information. And so this is very much, from my point of view, a proof of principle that there's still various bits of extra arithmetic information still in the perspective of standard sieve methods that one might hope to incorporate in and to exploit this extra information to get improved bounds, which correspondingly would have lots of improved applications for prime numbers. But as I mentioned, there's the very nice thing about sieve methods, or standard sieve methods as I'm calling them here, is that they are very flexible and apply to a large number of different situations. Unfortunately, the big drawback is that they're inherently limited and they're not going to, on their own, easily count prime numbers themselves, precisely because we can't control these large prime factors. And in fact, there's a very concrete obstacle, which is well known. It's the Parity Phenomenon, which roughly says that sieve methods can't tell the difference between integers with an even number of prime factors and integers with an odd number of prime factors. And this means that if you're getting any upper bound for the number of primes in a set A, you're going to always be off by a factor of 2 unless you come up with some means of getting around this parity phenomenon. And it also means that you can't get a non-trivial lower bound for the set, for the number of primes in this set A. So unfortunately, this is a big barrier to standard sieve methods, which means we would need to incorporate some sort of extra structure somewhere to get around this barrier. And in some situations, at least, this isn't just some limitation from only having sort of two weak techniques. So for at least certain sets A, this parity phenomenon is really a manifestation of the possible existence of z equals zeros. And so one of the key obstacles in multiplicative number theory turns out to be hiding in one of these key obstacles in sieve methods and additive number theory as well. But at least in certain nice situations, morally, you can imagine that this parity phenomenon is really the key barrier to making progress. And if you have good understanding of your set A in arithmetic progressions, then it's almost only the parity problem that you really need to overcome. And I would be very optimistic if you come up with some means of getting around the parity phenomenon for numbers with large prime factors in your set A, then this should be able to be combined with sieve methods and allow you to count primes in your set A in the way that we'd like. Okay, so we've seen that sieve methods are very flexible, but we've seen that there's this big obstacle to them. We've seen that multiplicative techniques are often very successful, but they're somewhat structured, and making further progress is limited by various famous conjectures. But one thing I'd like to highlight is that despite this limitation of sieve methods, sometimes the nature of the setup is such that you can exploit some extra properties of the setup to sidestep these limitations and count prime numbers, even though at first sight you might not have enough information about the set to count primes. So maybe one very basic example of this is a result I very much like by Noam Elkies, that there's, for any elliptic curve over Q, there's infinitely many supersingular primes. And so this is one way of counting primes with certain properties. And in this case, Elkies is able to really exploit algebraic structure in the problem, and it turns out that in this case he's able to sidestep all of these issues that one might worry about counting primes, and just reduce the whole problem to counting primes in arithmetic progressions, which we understand well through Dirichlet's theorem. And so it doesn't need any terribly advanced technology from the point of view of primes, it's just exploiting some algebraic setup of the problem. Okay, so as was mentioned in the Laudatio, one work that I've been involved in is about bounded gaps between primes and clusters of many primes that occur in bounded length intervals. One way of phrasing this is if you look at the distance between the n plus kth prime and the nth prime for some fixed value of k, then you can find infinitely many integers n such that this distance is bounded. So this is saying that there's bounded length intervals containing k primes, provided you've chosen the length of the interval to be big enough in terms of k. And so this whole argument really only relies on understanding of primes in arithmetic progressions, and so it does just follow the basic input of standard sieve methods. But at least from my perspective, in this case, the reason that you're not limited by the parity problem is a completely trivial one. It's that you can set up the whole question where you're using the pigeonhole principle to sidestep this limitation. And provided you set up the problem correctly, the parity problem can still exist. It can still be the case that when you that the sieve estimates that you're looking at can't tell the difference between numbers with an even number of prime factors and an odd number of prime factors. But thanks to sidestepping some of the parity issues, you can allow a certain ambiguity to go through your arguments, and you can nevertheless prove a result using only standard sieve methods that is manifestly a result about prime numbers. And finally, I'll mention another result that was also mentioned in the Laudatio in the opposite direction. Instead of looking at small gaps between primes, you could look at large gaps between primes. And so in work with collaborators, building of rather earlier work of Erdos and Rankin and others, we can improve the lower bound on the largest possible gaps between prime numbers with this rather messy expression here. And again, we're not really getting some great new arithmetic information that we're putting into the method to prove a result about prime numbers here. Fundamentally, instead, we're taking a slightly different approach, which concentrates very much on special, unusual large gaps between primes, where you have lots of consecutive integers, all with an unusually small prime factor. And this reduces questions to combinatorial covering questions. And this means that, again, without any extra information, we can still use sieve methods in the basic arguments, and we can sidestep some of these limitations. And so it's always worth bearing in mind, if you're trying to count primes in your favorite set, that even if there's some well-known limitations to the techniques, at least in certain nice situations, you can sidestep these limitations, and then you can make further progress. However, it's not always the case that we know how to sidestep the basic limitations, and so sometimes to make further progress, we really do need to have some extra arithmetic input that we're trying to put into the whole argument. And in not the most necessarily imaginative terminology, the terminology in the field here is that we often refer to the results about the distribution of the set A in arithmetic progressions as sort of type 1 arithmetic information, and you can combine this with so-called type 2 arithmetic information, which is estimating certain bilinear sums associated to A. So if you haven't seen this before, it doesn't matter too much, but essentially it's bilinear sums with somewhat arbitrary coefficients. And you can't possibly hope to get a good understanding of this if either one of the sequences is supported on integers which are too large or too small. But the somewhat miraculous thing is that in a number of at least nice cases, you can get a fairly good understanding of these somewhat arbitrary bilinear sums. And if you do that, you can combine it with standard sieve method techniques to actually count prime numbers. So just as a proof of principle as to why bilinear sums might possibly be useful if you haven't seen any of this before, if I want to count the number of primes in my set, I could do inclusion, exclusion based on the smallest prime factor. And so primes are numbers with no prime factor bigger than, if I'm thinking of my set A as lying between maybe x and 2x, then they're numbers with no prime factor less than 2x to the 1/2. And so I can write it as numbers with no small prime factors minus numbers with the smallest prime factor p for some value of p between some cutoff x to the delta and x to the 1/2. And okay, this is a very crude thing that you'd need a more sophisticated version of this in practice, but roughly standard sieve methods are very effective at counting numbers with no small prime factors, and so could count this first term, whereas the second term contains various terms where you have some control on the size of one of the factors. And so you could imagine a slightly more elaborate version of this, decomposing the count of primes in your set to things that you can control either using standard sieve methods or by bilinear sum estimates. And this indeed works. It's still something of an art exactly how you might combine all of this, but it's a principle that goes all the way back to Vinogradov in the early 20th century, that you can, in at least certain special situations, count the number of primes in your set A of interest if you're good at understanding your set A in arithmetic progressions, so understanding type 1 estimates for your set A, and you're good at estimating certain bilinear sum estimates that are associated to A. And there's been a number of different mathematicians who've all made important refinements of this basic principle for precisely what sort of information you need and in what sort of ranges do you need it. I certainly haven't done justice to everyone who's worked here. And to just make this a little bit more concrete, if I have some set A between x and 2x, I can give it a type 1 range if I understand, so I give it a type 1 range between 0 and up x and gamma if I understand it in arithmetic progressions to moduli roughly x to the gamma, and I give it a type 2 range between alpha and alpha plus beta if I can understand bilinear sums where one factor lies between x to the alpha and x to the alpha plus beta. So here I'm just thinking of gamma, alpha, and beta as fixed numbers between 0 and 1, give me fixed intervals between 0 and 1. Then it follows from something called Vaughan's identity that if you have a type 1 range and a type 2 range, where the length of the type 1 range plus the length of the type 2 range is bigger than 1, then you can get an asymptotic formula for the number of primes today, and you can count things very nicely. One proof of principle of this, it's a beautiful result of Friedlander and Vanich that there's infinitely many primes of the form x squared plus y to the 4, and morally this is roughly doing something like proving a type 1 range 0 up to 0.75, and proving something like a type 2 range of roughly 0.25 up to 0.75. In this case, the type 1 range and the type 2 range have lengths summing to bigger than 1, and so we should expect to be able to get an asymptotic formula in this case. I'm clearly sweeping lots of details under the carpet, but it gives a proof of principle as to how these bilinear estimates can combine with standard linear estimates. So unfortunately, often establishing any type 2 estimate and controlling these bilinear sums is really the heart of the problem and is very difficult. And even if you can produce a type 2 estimate, often you can maybe only produce it in somewhat narrow quantitative regions. And the previous methods that I mentioned depended very much on the length of the type 1 interval and the length of the type 2 interval. But there's this nice principle due to Harman that says that even if you're not in the situation where you can get an asymptotic formula, if all you care about is showing the existence of primes, then often in practical cases, if you just have a small type 2 estimate, that can still be enough to get a non-trivial lower bound. One concrete example of this is mentioned in the Laudatio, that there's infinitely many primes with no decimal digit equal to 7. So the main reason I was interested in studying this is sort of developing new techniques for studying primes in sparse sets, but that followed something along the lines of a type 1, type 2 strategy, and so morally you can think of this as producing a type 1 range that goes up to about 0.65, and a type 2 range between about 0.36 and 0.425, and because this is not enough such that the lengths of the two ranges would sum to something bigger than 1, but nonetheless we can still sort of follow this principle of Harman and get infinitely many primes in this set by getting a non-trivial lower bound. And so this means that we do now have at least a optimistic strategy for how we might try and count primes in a fairly arbitrary set A, which is reasonably dense, which is, first of all, you would try to obtain as big a type 1 range as possible. Often it's not too difficult to obtain some type 1 range, but you might have to work quite hard to produce a quantitatively big type 1 range. Then the second step, which is often the hardest step, is obtain as big a type 2 range as you possibly can. And then the third step would be given some type 1 range and some type 2 range, trying to convert this sort of arithmetic information via Sieve methods into some result about the number of primes in A. And at least in certain circumstances, you can make this whole strategy work, and you can count primes in sets A, even when they don't have strong multiplicative structure or something like that. As I mentioned, in many of the most important questions that remain open about prime numbers and counting primes, if you wanted to adopt this strategy, there's no particular reason why the strategy shouldn't work, but the key obstacle is obtaining any type 2 information at all. So for example, if you want to prove the twin prime conjecture, then an actual way of trying to show that there's infinitely many twin primes would be to try and follow the strategy that I outlined on the slide before, we can produce type 1 information for this set of shifted primes in various ranges, and we can get some fairly good estimates in that case. The next step would be to get some type 2 information and then hope to use Sieve methods to translate that arithmetic information into something that would be enough to produce primes. But unfortunately, we don't know of any argument that gives any non-trivial type 2 information, and this is one of the key barriers to this approach possibly saying anything about twin primes. So certainly one major open problem from my point of view, and almost at the heart of trying to solve the twin prime conjecture, would be, can you say anything at all that would give you something in the direction of bilinear type 2 information as a way of trying to get around the standard parity problem of Sieve methods? But even if you put aside the question of obtaining type 2 information, so because type 2 information is naturally arithmetic information about the set of interest, it's going to depend on whichever set you're looking at. So if you have a set that has a certain fractal structure, you'll need to use sort of fractal type techniques to try and obtain any type 2 information. If you have a set which has additive structure, then you'll naturally be trying to exploit additive properties of the set to obtain type 2 information, and that will depend from case to case. But one universal thing is step 3, which is just given some type 1 information, some type 2 information, what can we say about primes? In particular, is this enough to get an asymptotic formula for primes? Is this enough to get a lower bound for primes? Can we prove infinitely many primes, or do we not have enough information? And even this basic question about using Sieve methods to transfer the arithmetic information remains pretty poorly understood. So in practice, there's numerical processes that you can go through that give us reasonable results, but we don't have a very good theoretical understanding of precisely how far these techniques can be pushed. And so certainly one question that I'm very interested in, and I'd highlight as maybe one of the most important open problems in my mind from the point of view of Sieve methods, is if you're given some type 1 range and some type 2 range, what are the optimal upper bounds and lower bounds you can introduce just from using this as a black box? And in particular, again, taking the dual approach, what are the extremal sets that have the maximal or minimal number of primes, but satisfy a given type 1 and type 2 estimate? Certainly, I'm interested in seeing if there's any specific properties of extremal sets, because extremal sets often give you natural hints for how you might try and further improve any of these techniques and incorporate extra arithmetic information, because you would need something to distinguish your set of interest from one of the extremal sets if you're possibly going to hope to prove something which is better than these optimal upper bounds and lower bounds. So it also leads us towards further improvements. Okay. Finally, I guess building on that last point, a natural question is, we have these sort of type 1 estimates that work in certain contexts and give us some useful partial results and are very flexible. We have these type 2 estimates that are often hard to produce, but when they do work, often they work pretty well in practice, even if there's still interesting questions from the point of view of Sieve methods for how to combine these. But then a natural question is, how can we push these techniques further, and what extra arithmetic information can be incorporated into the method? Is there something which, some other ways of getting around the parity problem that maybe doesn't require something as strong as type 2 estimates? Or is it the case that there's some extra arithmetic information that would allow you to be boosted up, even if you don't have sufficient type 1 and type 2 information to necessarily deduce anything about primes? So one well-known proof of concept as to how you can incorporate extra arithmetic information into this whole setup. So maybe there's one unsurprising aspect that type 2 estimates are naturally bilinear sum estimates, but if you have understanding of trilinear quadrilinear or quintilinear estimates, then these can also help push your ranges a little bit further. And so it can be the case in some situations that you have a given type 1 estimate, a given type 2 estimate. On their own, we don't know that this is sufficient to produce primes, but you can combine this with a trilinear estimate, and together these three estimates can produce primes. And in particular, often it's sufficient to not necessarily have these additional estimates with arbitrary coefficients. If you just have improved ranges, even with very nice coefficients like 1, then this corresponds to counting things like the divisor function or the ternary divisor function over your set, maybe in arithmetic progressions. And one maybe slightly speculative question is that you can think of the divisor function and the ternary divisor function as coefficients of higher degree L functions. And so can we exploit some extra higher degree L functions to incorporate extra arithmetic information into the method? There is some work I have with Sari-Drapeau, which in some sense can be viewed as exploiting properties of Klusterman sums, which are maybe not quite, but closely related to coefficients of higher degree L functions, which allow you to not need bilinear estimates per se. The inherent structure of the Klusterman sums effectively boosts your sieve methods slightly, and so if you have very strong type 1 information, that alone would be sufficient when you making use of these Klusterman sums. And also related to this is that in all of these estimates, we're implicitly starting off with a sequence of primes in our set A, and we're lifting them to some sequence of integers in our set A. So in almost all the examples that I've talked about so far, the sequence of primes is just the indicator function of the primes. It's 1 on primes and 0 everywhere else, and we're lifting them to the constant sequence 1, and you're trying to understand how this indicator function fits inside the constant function 1. This is one pretty natural choice of lift, but there's certainly different other possible choices of lift, and maybe you could exploit something that's more arithmetic. So, for example, you could try lifting the indicator function of the primes. Well, a simple example would be 2 divided by the number of divisors of n, which is a more arithmetic lift. It would agree on primes, it would still be non-negative, but it would have some inherent sifting properties that would mean that if you had strong type 1 information, you wouldn't need any type 2 information if you could understand estimates with that particular lift. Now, we don't have terribly good techniques for understanding that lift, but this would be another way of potentially incorporating extra arithmetic information into the method, and the work that I just mentioned before with Sari-Drapeau is a sort of very special proof of concept of this, that it can work in very, very special situations. And maybe one final thing that I'll mention is that often estimates for primes are proved not by directly counting the number of primes in the set A, but really doing some comparison process where you're approximating the number of primes in some set A by the number of primes in some intermediate set B, or maybe some weighted intermediate set, and then you're trying to estimate the number of primes in this intermediate set B. So in lots of situations of interest, B is a simple set that we can estimate using just techniques from multiplicative number theory, but certainly in certain contexts, these intermediate steps seem to be exceptionally useful from the point of view of our techniques. So certainly from the point of view of primes in arithmetic progressions, we can prove much stronger results when the arithmetic progressions factor nicely, and so there's a natural intermediate step where you're just looking at one of the factors of the arithmetic progression. Maybe this is just a technical thing, but I think one aspect that can be exploited more is to look at further intermediate steps. So there's certainly some cases when you can take a sequence of approximations in related questions and first of all simplifying things until you ultimately get to something that can be estimated using techniques from multiplicative number theory. And so maybe understanding this process a bit better would allow us to further our techniques for counting primes. I think I'm almost out of time, so maybe I'll stop here for questions, but I'd like to just finish by saying that I think there's been a huge amount of exciting progress in prime number theory and and our techniques for counting primes with lots of different successes from a number of different mathematicians. And so hopefully you've got a vague feeling of the overview of some of the techniques and some of the ideas that go into these methods. Thanks a lot for listening.
Thank you very much, James, for a very wonderful talk. Are there any questions? There's one at the back there.
This may be a kind of naive question, but in your result where you say that there's infinitely many primes with no 7 in the decimal expansion, is there something special about 7? Like, do you expect there's also infinitely many primes with no 5 or no 4 or what have you?
There's nothing special about 7 at all, so yeah, the result actually proves it for any given digit. There are some very slight technical reasons that mean you get a very slightly different type 1 and type 2 range depending on which digit you exclude. So I think it's slightly easier to exclude the digit 0 rather than the digit 5. And this is to do with carriers, but the result works in essentially exactly the same way for any individual digit that you exclude, and 7 was just chosen somewhat arbitrarily.
One more question.
Okay, I have like 2 questions. One is basically continuation of the first, like how about in different bases? Like if we, instead of base 10, we take whatever basis we like, does it like generalize also in those? But then another question is that you have this type 1 and type 2, like things is this bilinear was this type 2 thing and type 1 was this linear in a sense. So could this idea be generalized also in higher types in a sense that type K would be some kind of K-linear thing?
Yeah, so let me just check. So the first question was about the result with missing digits, and it was talking about other bases. So one thing that I've somewhat swept under the carpet is, if you remember right back on my very first slide, I was talking about sets A that are reasonably dense. And actually, the reason I was interested in numbers with missing digits was primarily because this is a sparse sequence that contains only around x to the 0.95 numbers less than equal to x. If you increase the base, but are just looking at numbers with 1 excluded digit, then the sequence gets denser, and so morally it gets easier to find prime numbers, and indeed the same methods allow you to exclude 1 digit in any base which is bigger than or equal to 10. But conversely, if you reduce the base, then the sequence gets sparser, and so it gets a harder problem. And although you would expect to only need to have 2 digits, and so you should be able to exclude 1 digit in base 3, we can't. I don't think our techniques at the moment are quantitatively good enough to do anything below base 10. So at the moment, 10 is really the limit of what we want to do, but it does work for any base bigger than or equal to 10. Your second question was, okay, there was type 1 and there was type 2, and what about type 3 for some interpretation of type 3? And That's a good question, and yes, you very much can incorporate extra things. So this was maybe what I said rather quickly on the final slide. So these trilinear estimates would be maybe some natural 3 version of type 2 estimates, although in practice, we tend not to call them that because lots of these estimates depend quite a lot on the precise coefficients that you're looking for. And so there's a zoo of different types of arithmetic information that are variations on type 2 estimates. And in different contexts, with different assumptions on the coefficients, these can all be useful. But the basic answer is yes, they are natural things like that, and yes, they are all useful.
Maybe one last question here. Yes. Henri?
No, I had it. There was a second question.
Oh, I see. Okay. Then.
You mentioned there's some obstructions if you have to get counterexamples to the Riemann hypothesis. Still, there has to be some pattern, and you mentioned there's this 3/4 line on which you have some results. So there's a theorem from 1940 by Selberg which tells you the distribution on the half line. But is there a similar estimate you have for 3/4, or like what kind of pattern do you expect?
Okay, so this is a difficult question in a way because, of course, we expect there to be no zeros on the 3/4 line, but it's very much adopting some sort of strange mindset of if there were lots of zeros on the 3/4 line, even if there were lots and lots of them, maybe lots of the time I could still count primes in a perfectly reasonable way, unless the zeros on the 3/4 line had a particular pattern. So one obstruction to various techniques is if there were lots of zeros on the 3/4 line that happen to all line up in vertical arithmetic progressions, for example. And so part of my work that I mentioned then was to at least produce a proof of principle that says that it's not just vertical arithmetic progressions of zeros. If there were only vertical arithmetic progressions of zeros on the 3/4 line, we can nevertheless handle them. So my belief is that the key putative example of what the zeros of the Riemann zeta function would look like if you, and this is what you'd need to rule out if you want to make progress on questions to do with primes, is what Kyle and I call bows of zeros, which in a vertical sense look as if they're in a arithmetic progression, but in a horizontal sense look as if they're smoothly moving from the half line to the 3/4 line. Then there's an arithmetic progression of zeros on the 3/4 line, and then they smoothly move back with all the imaginary parts going up by a constant amount each time. And if there are lots of these strange bow-looking configurations, then I know of no technique in analytic number theory at the moment that can rule these out, and I think that's the moral enemy that one would have to rule out if you want to make further progress. But it's difficult to give a terribly comprehensive answer since, of course, we expect there to be no such zeros anywhere in the first place.
I think that might be a good time to stop. Let's thanks James again for a very nice talk.
Yes.
Okay. Please take your seats. Okay. My name is Gil Kalai, and I'm from the Hebrew University, and I will introduce our next speaker. Jun Ha received his PhD in 2014 from the University of Michigan at Ann Arbor. 5 years earlier, he proved the Heron-Rota conjecture, first for characteristic 0 and later for every characteristic. After graduating, he had position at the Institute of Advanced Studies in Princeton, at Stanford University, and at Princeton University, where he is now a faculty. Jun Ha was awarded the Blavatnik Award in the year 2017. In 2019, with Karima Di Prasito, he was awarded the New Horizons Prize. And in 2021, he was awarded the Samsung Ho-An Prize in Science. Yesterday, Jun Ha was awarded the Field Medal, the first field medalist, the first field medal awarded in the area of combinatorics. Jun, please.
Well, thank you very much for coming. I'm very glad that we are together here now today, and also many thanks to many people who are watching this online. I'm very glad that you came. Today, I'm going to tell you a story that I find fascinating that concerns the interaction between combinatorics and Hajj theory. And the story begins like this. And in the beginning, let me be intentionally vague to allow maximum freedom in the future possible development of the same story. So let's say X is a mathematical object, maybe one of your favorite mathematical objects. And let's say your X has dimension D. And of course, what I mean by dimension here will depend on the context, like what your X actually is. So let's use just the word dimension as just some placeholder. So D is some basic invariant of your X. And in the few precious examples that we have in mind, we can associate to X a triple of new objects, much simpler objects, usually, that we choose to call A and K and P. So what is A, which is determined by X? It will going to be a graded vector space over the real numbers. So it's a vector space over the real numbers, typically finite dimensional. And by graded, I simply mean that it comes with a direct sum decomposition of subspaces. And how many subspaces? D plus 1 subspaces. So A0, A1, A2, all the way up to AD, where your D is your dimension. So that is A, vector space over the real numbers. And then there was K, Kx, which will going to be the convex cone inside the space of all linear operators on A. And not any linear operator. We are interested in those linear operators that are graded and shifts degree by 1. It maps A0 to A1, A1 to A2, A2 to A3, and so on. So that is K, and we are interested in not in a single linear operator, but a family of linear operators. And the collection of all the interesting linear operators form a convex cone. And the last object is P, P of X, and this will going to be a symmetric bilinear pairing on A. And it pairs two elements of complementary degree. So it pairs A0 with AD, A1 with AD minus 1, A2 with AD minus 3, and so on. And it takes the value in the field of real numbers. so outputs a number. And these A and K and P are expected to satisfy the following rather subtle properties. And I'll show you the properties now. And there's a quantifier in the very beginning, which goes like for any K, which is at most D half, and any linear operator L in our convex cone K, we expect the following properties to be true. The first, which is also historically the first in a very specific context of compact manifolds and their cohomologies, is called the Prank Cardiology. One way of saying it is that the bilinear pairing P that I showed you in the first slide is non-degenerate. Or in other words, the linear map P that sends AK to the dual of AD minus K is an isomorphism. And the second property is the Hajj-Lefschetz property. This first appeared in the context of projective manifolds, compact projective manifolds, or more generally in the study of compact Kähler manifolds. And it states that if you apply your linear operator L right number of times, which is D minus 2K times, so that it maps AK to AD minus K, that linear map, the composition, is an isomorphism. So Prank Cardiology and Hajj-Lefschetz property, numerically speaking, both predict the same thing, which is that the dimension of AK should be the same as the dimension of AD minus K. But these are independent and, in a sense, orthogonal isomorphism statements. So you have this map from AK to AD minus K check and AK to AD minus K. So it is natural to consider their composite, which defines a symmetric bilinear form on AK. And the so-called Hajj-Riemann relations predict something very, very specific about the signature of this real symmetric bilinear pairing. It says that this so-called the Hajj-Riemann form, which is obtained by sending the pair x comma y by some sign that depends on the degree, and the P applied to x and L to the D minus 2K, this previous Hajj-Lefschetz isomorphism to dy, this is positive definite. Not on the whole space, but on this very specific subspace defined as the kernel of L to the D minus 2K plus 1. So one more L, then that would give an isomorphism. So the letters are chosen to emphasize the important people who are involved in the first development of this story, or the relevant objects. So L, that appears in the Hajj-Lefschetz property, is of course for Lefschetz, and K is for Kähler, and P is clearly for Poincare. And the last one, which is the central one for the purpose of this talk, is the so-called the Hajj-Riemann form. Most of you may have encountered Prank Cardiology and Hajj-Lefschetz property in classical context, but you may be unfamiliar with the Hajj-Riemann form. And this was true for most people throughout most of the history of development of the mathematics. Of course, the Hajj and Riemann knew of this fact in special cases. Most importantly, in the case of curves and abelian varieties, and it played some special role there. But the true significance of the signature property of the Hajj-Riemann form appeared in the attempt for the proof of the Riemann hypothesis analog for finite fields as a part of Weil conjecture. And it appears in the following letter from one algebraic geometer to another algebraic geometer in the 60s. So they are talking about not the original Hajj-Riemann relations, which was about the cohomology of compact Kähler manifolds, but not that one, but another cohomology-looking object that is entirely made of algebraic cycles. This is what algebraic geometer would call the true cohomology. That is algebraic in every possible sense. And it says that the writer says that there is young Italian Bombieri who is working on zeta functions, and he noticed all by himself that it was necessary to prove in all characteristics that, and this is the Hajj-Riemann relation, the intersection form on primitive algebraic cycles of half dimension is definite. So what does the writer mean by primitive? It means exactly this, the subspace of AK as defined as the kernel of L to the D minus 2K plus 1. Geometers often think of multiplying by L as intersecting with the hyperplane, and the primitive ones are the ones that are truly new in that dimension. It does not come from some higher dimension thing and cutting out by general hyperplane. And you want the intersection form to be definite on that subspace. So let me show you probably the complete list of known examples where this story appears to hold. And as you see, the list is not long, but let me try to convince you that at least the list is remarkable. And the one thing that I want to emphasize in this slide are the arrows. So the arrows are the important ones, or implications. So in the beginning, in each one of these listed items, there is a super cool conjecture. So in algebraic geometry, there is vague conjectures concerning the number of solutions of polynomial system of equations over finite fields. And in the theory of convex polytope, there is this generalized lower bound conjecture that completely characterizes the number of possible faces of various dimensions of a simple polytope. And in representation theory, there is this Kazan-Lustig conjecture that concerns the coefficients of the so-called Kazan-Lustig polynomials that controls large part of representation theory of Coxeter groups. And there were various numerical predictions made by classical Maynard theorists from the 60s and 70s. And in each one of these cases, the key to the proof was to find the right A and right K and right P, and then prove Prank duality and Hart-Lefschetz theorem and the Hajj-Riemann relations for them. And then the arrows give you the desired result. So some of the key players here in the first algebraic geometric context is Grothendieck and Dwork and Lean. And this first case, which is also historically the first case, is singular one, because although the implication was known, as we have seen in the previous letter, but and also Grothendieck found the right A and right K and right P, but we still do not know how to prove Prank duality, Hart-Lefschetz, Hajj-Riemann relations. So that way of proving vague conjecture was not realized, but Lean did his thing and proved vague conjectures in some other way. But except in that case, in other items 2, 3, 4, the only known proofs, in a sense, of these central conjectures in their respective fields are obtained by first finding A and K and P and proving the three properties, collectively known as the Kähler package. So in the case of convex polytopes, the implication was first noticed by Stanley, and that McMullen find the right A and K and P in the special case of simple polytopes, and Carew later generalized this to arbitrary convex polytope, introducing what is now known as the combinatorial intersection cohomology for convex polytopes. This was his A. And in the case when X is an element of the Coxer group, the general framework laid out by Sorgel was recently realized by Ben Elias and Jordi Williamson, proving the Prank Cardiology, Hard-Lefschetz, and Hajj-Riemann relations for the so-called Sorgel bimodules. This was their A. Therefore, proving the Cauchy-Lusztig conjectures and many other conjectures. And in the last case, when X is a combinatorial object called matroid, this is the item that I principally worked on with many of my collaborators, Karima Di Prasito, Eric Kess, Federico Agila, Graham Denham, Tom Braden, Jacob Mathern, Nick Proudfoot, and Bo-Tong Wang, that resolves a few of the old conjectures in matroid theory. One thing that I want to emphasize in the last item is that I have listed 3 different conjectures, and for each one of those conjectures, you had to use different AKP. So you should at least agree that, especially if you know some details about one of these conjectures, that this story is kind of remarkable. First of all, this Hajj-Riemann relation is something oddly specific, right? It's a weird statement. But then somehow it can be used to deduce this various but central conjectures that looks nothing like each other. So in that sense, it appears to be fundamental, the Hajj-Riemann relations. And also, it is ubiquitous in the sense that, I mean, you should at least agree that these 4 objects have very little to do each other, but then, for some reason, if you think about them long enough, you arrive at this oddly specific sentence on the signature of the intersection pairing. So at this point, one thing you can ask is that, why is this true? Are there any logical relations between the Kähler packages for these different objects? So we have no idea, so let's get that out of the way. So the second very reasonable question that we can ask at this point is, okay, so I have another cool conjecture in the object X that I am super interested in. So what do I do now? In other words, how are you going to find your A and your K and your P? Of course, for this, we have also very little idea, but at least we have examples. So it may be useful to go back to the short list of known examples and see what happened. So first of all, you need a very, very good conjecture, at least as good as one of these guys. And then you think about that conjecture long enough. So I think on average, it took about a decade or 2 of a few very, very good people in this field to uncover from those central conjecture the right A and K and P. And then what do? You have to prove Prank Cardiology, Hard-Lefschetz, and Hajj-Riemann relations for your AKP. Again, on average, this took another decade or 2 of work by very good people, except in item 1, which is still the unresolved Grothendieck standard conjecture on algebraic cycles. But of course, this approach to finding AKP has a central defect. So there's a decade or 2 on formulating, and then another decade or 2 in proving. But the first step, this coming up with the super cool conjecture, this took thousands of years of effort of entire humanity. So you cannot expect to come up with like next academic year or something. So what I want to propose today is an alternative method for coming up with the correct A and K and P. So what am I proposing? So let's say A0, the degree 0 piece of A, is spanned by some element. This A0 is typically one-dimensional. Just pick any generator. And let's just call it 1. And for a sequence of linear operators, let's say Li, let's define the degree of the product of D of them using the Prank pairing. So I want to pair 1 with 1 applied to this L1, L2, dot, 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 LD, so that it's a degree D element. So this is a real number. So that's just a definition of this degree function. And the fact that you can prove is that if L1, L2, all the way up to Ln, so this n is a new letter, so arbitrary non-negative integer, are in the closure of your convex cone K, then the polynomial in n variables, W1 to Wn, defined by 1 over the factorial, this is just some constant, times the degree of generic linear combination of Li's raised to the power of D, and apply the degree function to make it a number. This is a polynomial, just by thinking about it, but not any kind of polynomial. It must be a Lorentzian polynomial. And this fact is what I want to solve today. And of course, this means nothing to you right now because I haven't told you yet what a Lorentzian polynomial is. But let me tell you, at least at this point, that a polynomial being Lorentzian is a testable property. This is one of the points of the work that I did with Peter Brandon. And it just simply means that if you give me a polynomial in 27 variables of degree, maybe 5 or something, then I can feed it into a computer, and the computer will tell me whether it is Lorentzian or it is not Lorentzian. And any polynomial that arises from this context, let me just call it the volume polynomial. And this volume polynomial is central in guessing the correct form of A and P, and also oftentimes K, because in good cases, this volume polynomial, knowing just the single polynomial, completely determines A and P. Not always, but sometimes. I will be more specific when this comes back. So when you see a Lorentzian polynomial, you have at least identified the portion of the correct object A. So let me show you 2 examples of these volume polynomials, which are Lorentzian by this Kähler package, that are known since a long time ago. So historically, the first example was noticed by Minkowski, and it appears in the context of convex geometry and convex analysis. So let's say you have convex bodies, C1 to Cn. So these will play the role of linear operators that we have seen in the previous talk. In R to the D, so I'll try to be consistent with my use of n and d. Then the polynomial that measures the volume of Minkowski sum of Ci's is a Lorentzian polynomial. So I have a variable linear combination of given convex bodies, and I take the Euclidean volume. That's a polynomial in W, and that must be a Lorentzian polynomial. And this leads to, and is in fact, what is actually proven in the classical Alexandrov-Fengstel inequality on mixed volumes, proved by, let's say, by Alexandrov. Second example is from algebraic geometry, which says that for any Neff divisors, so divisors are linear combination of codimension 1 subvarieties, and Neff here means that it's a limit of ample. Ample are the things that's coming from hyperplane section, which is a typical way of producing codimension 1 algebraic cycles in projective varieties. And if you have n of them on a d-dimensional projective variety over field F, then the polynomial that you get by counting the number of points in the self-intersection of variable linear combination of the divisors di must be Lorentzian. And such polynomials arising in this way for some choice of projective variety and for some choice of Neff divisors are called the volume polynomials over F. And I'm saying you that all volume polynomials over F are Lorentzian. And it's a fascinating question to ask, how does this notion of volume polynomials over F depends on F, for example? And are there Lorentzian polynomials which are not volume polynomial over F? So on. So let me now tell you the definition of Lorentzian polynomials. Again, this may look oddly specific, but the definition is designed to make the fact here, the Lorentzianness of volume polynomials, work. So if you think about this fact long enough and try to plug in as precisely as possible the definition of Lorentzian polynomial there by thinking in conjunction with the Hajj-Riemann relations, then there's you cannot help but arriving at the following definition. So I'm going to define a class of homogeneous polynomials by degree. So let me start in degree 2. So the case of the quadratic forms, and in n variables with positive coefficients and Lorentzian signature, which is plus and all others are minus. So that's L naught 2n, space of quadratic forms. And inductively, L naught dn, I want it to be the space of d forms in n variables with a property that ith partial derivative of f belongs to L naught d minus 1 for all choice of index I, or variable wi. And the closure of this L naught dn, and this naught is here to emphasize that we are talking about the open subset of the space of all homogeneous polynomials. The closure is, by definition, the space of Lorentzian polynomials. One thing that is completely unclear from this definition is that we have no obvious way to decide if a given polynomial is Lorentzian or not. So if you want to show that something is not Lorentzian, you have to somehow produce an argument that there cannot be any sequence of elements of L naught dn, which is the, you may call strictly Lorentzian polynomials, that limits to the given polynomial. If you want to show that something is a Lorentzian polynomial, you have to produce such a sequence. And both of these seems to be non-trivial on the surface, but I'll show you that there is a way, and if you know this way, it is very, very clear, for example, that the sum of two cubes is not a Lorentzian polynomial, and w1 squared times w2 plus w3 to the cube, something like this, cannot be a Lorentzian polynomial, and something like w1, w2, w3, this must be a Lorentzian polynomial. I'll show you the trick in a moment. So the miraculous part is that the answer to the previous question, the testability, is yes. So for this, I'm going to show you one more definition, and this is the last oddly specific thing you have to read. It goes like this. So again, I'm going to define a class of homogeneous polynomials degree by degree, starting from degree 2, L to n. This will going to be the quadratic forms in n variables with non-negative coefficients and at most one positive eigenvalue. So this is obviously a closed subset. And inductively, LDN is a space of homogeneous D forms with a property that ith partial derivative is L d minus 1 to the n for all I. So far it's more or less exactly the same as previous slide. But I want one more condition, that the set of monomials appearing in F is the set of lattice points of an integral generalized permutohedron. Okay, so what am I doing here? Monomials can be viewed as lattice points just by looking at the exponents. And I want the set of all monomials appearing in the polynomial f to be the set of all lattice points of an integral generalized permutohedron. So what is a generalized permutohedron? It has a very short definition, which says that it's a polytope with all edge directions in EI minus EJ. So where EI is the ith standard unit vector. So all edges in the direction of a root in a root system of type A. And you also want the polytope to be integral. All vertices are integral. And then, so this is a picture of a typical generalized permutohedron, and this guy's name is the standard permutohedron. The theorem with Heter-Branden is that this LDN is the closure of L not Dn. In other words, this is exactly the space of Lorentzian polynomials. So like any other equalities between two sets, we are proving two different things here, two different inclusions, going here and there. And both of them are non-trivial. So what am I saying? I'm saying that if you have a sequence of strictly Lorentzian polynomials limiting to some homogeneous polynomial, the set of monomials that you see in the limit, so some coefficient goes away because coefficients can become zero, what remains must be the lattice points of a generalized integral permutohedra. And conversely, if you have a homogeneous polynomial with a reasonable signature property for all the associated quadratic forms, and also if you know that all the monomials that you see form a generalized integral permutohedra, then you must be able to approximate it by strictly Lorentzian polynomials. So that's how I knew, right? In our three examples, the first example, this is not Lorentzian because I'm missing two lattice points in between the cube and the other cube. So that's not good. The second one, the edge is not in the right direction. That's not EI minus EJ. The third example, this is good, right? There's a point is a generalized integral permutohedra, and if you differentiate once with respect to any variable, you get the quadratic form 0, 1, 1, 0, which has the Lorentzian signature. And furthermore, if you projectivize your space of Lorentzian polynomials, because everything is up to scaling, call it PLDN, so that's the image in the projective space, then that is a compact contractible subset of the projective space of all homogeneous polynomials with contractible interior P of L naught Dn. So this is a very nice set. And the point here is that although this space is topologically very nice, it is not a convex subset. That is why all these contractibility statements are non-trivial. If you have two Lorentzian polynomials, if you add them, you lose the property in general. Just like if you have two matrices with given signature, if you add them, you lose the signature. And furthermore, I have just emphasized the role of support, the set of monomials that appear in the expansion. So there will going to be one little piece for every possible combination of monomials that can appear in a Lorentzian polynomial. So let's write Lj for the set of Lorentzian polynomials with support J, where J is a given set of monomials. Then what you can prove is that Lj is non-empty. In other words, there is a Lorentzian polynomial with support J, if and only if J is the set of lattice points of an integral generalized permutohedron. This is if and only if. I have emphasized one direction before. And in this case, P of Lj, deformation retracts to the canonical Lorentzian polynomial with that support, which is the exponential generating function of that J. So you sum over all lattice points in J, and the term corresponding to that point alpha is W alpha divided by alpha pictorial. So this is a picture of the Lorentzian ball, and there is one for every given degree and one given number of variables. This is something homomorphic to the closed ball that's defined by analytic property, but miraculously on the boundary it has a combinatorial structure. and there is one piece, so it's more like a soccer ball. So in the boundary, you see a beautiful pattern labeled by combinatorial objects. There is one boundary piece for every single one of integral generalized permutohedron. And you cannot omit any one of them, and then you will lose compactness. And for every one of these pieces, there is a distinguished point, which is the generating function for that integral generalized permutohedra, to which that piece deformation retracts to. And this ball includes the familiar and classical example like volume polynomials in convex geometry, and then more generally, and there is a hidden toric geometry story between that sentence, the volume polynomials in algebraic geometry over a given field F. And all these inclusions are proper, so there is something here, there is something here, and there is something there. But the region is largely unexplored otherwise. So the strategy that I propose goes like this. Step 1, you have your X, and what you want to do is you extract many, many numerical invariants from it. I mean, that's what we do, typically, especially if you're an algebraic combinatorialist. So you want to extract an interesting multivariate generating function from it. So you have a large number of variables. You make an array in a natural way, putting it in a multivariate generating function. And you ask this question. If you just ask whether the invariant is 0 or non-zero, or in other words, if you just look at the support of your generating function in right coordinates, do you see generalized permutohedron? This is certainly a checkable thing. And if the answer to the second step turns out to be yes, and then you immediately ask this question. Do you, in fact, have a Lorentzian polynomial? And this can be tested by computing large number of matrices and computing their signatures. And then from that, you can try to come up with reasonable candidate for AKP. So, and the last step is, in fact, automatic if AX is very good, in the sense that it's a graded ring generated in degree 1 by something called the Macaulay's correspondence in commutative algebra. So, and this is what happened in the context of toric geometry and convex geometry. So there are various examples that one tries to achieve these steps to possible extent, and you will see dozens of conjectures in these two papers and also in my proceedings article for this talk. Okay. But for the remaining time, let me try to show you one example of how to apply this strategy and arrive at AKP, and maybe resolve an interesting conjecture from it in just one single example. And in retrospect, this is the canonical example, at least from this perspective. And it should have been the first example, maybe, if we were all combinatorialists since 100 years ago. Right? And the conjecture is what Gil told you yesterday briefly about. And it's an old story, goes back to 40s, which says that every set of points E in a plane determines at least E many lines, unless E is contained in a single line. So what we're going to do is we start with some configuration of points and connect every pair of points by a line and count how many lines we get. So here you get 4 points determining 6 lines. But if one of the 4 points is special, then it determines 4 lines, so there can be a tie. This is 7 points determining 9 lines. And the same 7 points, in a sense, but in characteristic 2, determines a different number of lines. It's another case of tie. So the last picture is the picture of the so-called Fano plane. So there is some ambiguity in what we mean by plane here. And the proof given by De Bruyn and Erdős was absolutely general in the sense that no matter what you mean by a plane, so long as it's a reasonable one, the theorem is valid. The one thing you can ask is what happens in higher dimensions. So you can think of a space of high dimension and configuration of points, and you can connect pair of points by a line, triple by a plane, quadruple by space, and so on. And what can you say about number of those? And that is the content of the Dowling-Wilson's top-heavy conjecture from the 70s. So first of all, it's a statement about the special kind of poset called geometric lattice. So this is a graded lattice generated by rank 1 elements that satisfies the so-called submodular inequality, but that's not so important here. What is important is that it is the right kind of poset theoretic notion that includes all possible different notions of what you mean by plane and space and so on. Is it characteristic P, or even it's over a division ring, or some more exotic projective planes or projective spaces and so on. So it includes these sort of things. And the content of the conjecture is that if you have a geometric lattice L, and if you write the set of rank K elements measured by height in your poset by LK, then the number of rank K elements must be at most the number of co-rank K elements for all values of K, which is at most D half. So the previous case was the case D equals 3 and K equals 1. But as you see, this is the case D equals 4 and K equals 1. So 4 ties with 4, 5 smaller than 10, 5 smaller than 7, 5 smaller than 5. But in higher dimensions, you have more and more numbers. So let's try to solve this conjecture by finding the right A and K and P. So how do we do this? We look for generalized permutohedron that's somehow naturally associated to this context, maybe point configuration or more generally geometric lattice. And fortunately, the generating function is something that is rather familiar to many of us. And maybe the most classical example, maybe going back to Kirchhoff, is the case when you have a connected graph G with n edges, and you consider your set J, which is the collection of all spanning trees of G, viewed as a subset of edges of G. And I want to view every one of spanning tree of G as a 0, 1 vector in Z to the n. N is the number of edges. So for a complete graph on 4 vertices, I'm looking at this collection. And every single one of them is a 0, 1 indicator function. So viewed as a vector in Z to the 6. 6 for the 6 edges. And the fact here is that for any graph G, this J is in fact a set of lattice points of an integral generalized permutohedron. So that's something. And this fact can be used to deduce many fascinating properties of like a collection of spanning trees, and maybe even used to compute or approximate the number of spanning trees of a large graph. Another related example is when you have n vectors in a vector space over F, where F is a field, and you consider all bases contained in A, again viewed as 0, 1 vectors. So for example, if you have 4 general vectors in R2, J is the set of lattice points of the octahedron. So I have 6 bases, 4 choose 2, and every single one of them is something like 1, 1, 0, 0. Take the convex hull, you see the octahedron in 4 space, and every single one of the edges in EI minus EJ direction. So that's a generalized integral permutohedra. And such generalized permutohedra are said to be realizable over the field F. And more generally, for any geometric lattice L of rank D, you can consider the set J of its bases viewed as a subset of Z to the E, where a basis of L is a D element subset of rank 1 elements whose join has rank D. It generalized the examples 1 and 2. And for any L, it turns out that J is a set of lattice points of an integral generalized permutohedron, and hence the basis generating function summing over all elements of J is a Lorentzian polynomial. So for this 4-point configuration, I'm talking about this sort of a 4-term homogeneous generating function. So any triple is a basis. And for this one, any triple is a basis except 1, 4, 3. So that's why this one has one less term. Both of these polynomials are Lorentzian. So that's the starting point. You want to produce an algebra-like structure that naturally produces the basis-generating polynomial. And there is, fortunately, very, very obvious candidates. So there is something called the graded Möbius algebra of L, which is simply the vector space consisting of all functions on your geometric lattice L. Let's say Q-valued. So L is a poset, but among other things, it's just a finite set. So in this way, you get a finite dimensional Q vector space that comes equipped with a basis, the single basis, so delta function, so delta F. And there is a natural way, again, to make this into a graded algebra, where you simply transfer the lattice structure of the poset into the algebra structure of the graded vector space. So you want to declare that the product of two elements, F1 and F2, is their join, if the rank of the join is the sum of the ranks, and 0 if otherwise. So I have just transferred the lattice structure into graded algebra structure. And then, if you think about what basis means in this context, then it's very easy to notice that the basis generating function of L in the sense of previous slide is simply 1 over d factorial times sum over all the rank 1 elements, which is E, with variable coefficients, and raised to the power of d. So if you expand this, if you don't get a basis, the term goes away, just because how the multiplication is defined here. And only the basis terms survive. So that's the right object. So this suggests taking A to be the graded Möbius algebra H over L, and K to be the multiplication by positive linear combination of delta I. That's the most naive thing that you can come up with. And P to be simply the pairing given by the multiplication in the graded Möbius algebra, maybe composed with the fact that the top rank element there is exactly 1. So HD is isomorphic to Q. So that's all good, except that your A does not satisfy Prank duality. And you don't need to do anything to notice this. Just by construction, the dimension of HK is the number of rank K elements. And the dimension of HD minus K is number of rank D minus K elements. And we have seen from slides before that typically these two numbers are very different. And the content of the top-heavy conjecture is that one side is always at least as large as the other side. So you have to modify your A. And what I want to emphasize is that this is the typical case. You come up with the first approximation of A, which is a ring, and then you have to modify it so that it satisfies Prank duality. And then your A will not be a ring. So this process happened already once in the context of geometry when geometers replaced the cohomology, the singular cohomology, with the intersection cohomology for, let's say, complex projective varieties. And it appears that you can do something like that in many, many other contexts as well. In every single one of the items that I've shown you before, this has happened or expected to happen. So in this case of geometric lattices, what happens is that we can define the intersection cohomology IHL of L, that is a graded HL module that repairs the failure of Prank duality. And if you are familiar with some part of Cauchy-Lustig theory, you can even attempt to make that this IHL is, in fact, the most efficient replacement of the Prank duality. And the main theorem obtained by Tom Braid and myself, Jacob Mathern, Nick Proudfoot, and Botong Wang is the existence of this IHL with the required properties. So for any geometric lattice L of rank D, there is an indecomposable graded HL module, IHL, and the map of graded HL modules go from IH to IH check, shifted by D degree. Let's call this map P. that satisfy the following properties for every k at most d half, and for every positive linear combination L of the rank 1 elements, delta I. And you can now probably expect what will show up in the next slide. So this IH, the intersection cohomology of geometric lattice, satisfy Prank Cardiology and Hard-Lefschetz property and Hajj-Riemann relations. And there is one extra thing that is important for the application, which I call purity, which is simply the statement that the submodule generated by the degree 0 piece of IH is in fact isomorphic to HL. So the degree 0 piece kills nothing in H. In other words, H is a submodule of IH in a natural way. So how do you construct this? And the idea comes from algebraic geometry, which is actually a valid mathematics when your geometric lattice is realizable as a point configuration over your field F. And in that case, what happens is that there is a resolution of singularities x to y of projective varieties over F. So y is singular, x is smooth, but then the pullback between the operational Chow rings, which is defined for arbitrary singular things and produces a ring out of algebraic variety, let's say going from CHY to CHX, depends only on L, not on the realization of L over F. And this Chow ring of Y is isomorphic to graded Möbius algebra of L. So your CHX is a HL module. So you can try to decompose it into indecomposable graded HL modules. So you write it down. So there is some large chunk and some other thing. And the overall shape of the decomposition is that it's IH plus shifted IH of minors of L. And you can take this as a definition of IH because the arrow here depends only on L, and the whole decomposition is unique up to isomorphism just by the Krull-Schmidt theorem in the category of graded HL modules. So you can define IH up to isomorphism of HL modules in this way. So what's the corollary of this existence? Is for any k at most d half, there is an injective linear map from HK to HD minus k. What is the linear map? You just multiply by degree 1 elements, which are positive linear combination of delta i's. So this is your linear map. And by purity, this H embeds into IH. And by Hard-Lefschetz on IH, IHK is isomorphic to IHD minus k. And the point of this commutative diagram is that the vertical arrows are injections, and the bijective maps do not restrict to bijective maps, but injective maps restrict to injective maps. So you have the injection from here to there. And the corollary is that just by taking dimension of this vector space and that vector space, you can conclude that the number of rank k elements in L is at most the number of co-rank k elements in L. So that concludes another, like a very specific instance of this ubiquitous phenomenon. And I hope that we together will going to find a few more examples. And maybe if we collect enough number of examples, I don't know how many would be enough, maybe 10, and then the future generation can start thinking about why this is happening all over the places. I'll stop here. Thank you.
Thank you, Jun, for this wonderful talk. And other questions? Yes?
I missed your definition of realizable.
Of geometric lattice. So if you have a point configuration in a space, if you connect everything points by lines, planes, and so on, it forms a poset of flats. And then such poset must be a geometric lattice. But not all geometric lattices come from such configuration over the chosen field. The ones that do come from this construction are said to be realizable over that field. Maynard theorists call this representable over F.
Yes.
Maybe, yeah.
Thank you. It's on? Hello? Yes. So you mentioned that in special good cases, when you have AX, you can generate the entire Kähler package structure and all these objects because of this Cohen-Macaulay.
Can you speak louder, please?
Oh, because of the Macaulay correspondence. So I'm wondering if there's a generating method if you get the ring to be like almost Cohen-Macaulay.
It's not the Cohen-Macaulay, it's Macaulay's correspondence. So the question was that in nice case, where A is literally a ring and not something intersection cohomology-like, and the claim was that if that's generated in degree 1, then the volume polynomial completely determines your ring A. And the question was, what if you have omitted the condition that the ring is generated in degree 1? Can you figure out somehow way to fill in the higher occurring things? And I don't know, and I expect the answer to be no, because like this, if you think of this A in the specific case of algebraic cycles, modular homological equivalence, the thing that's not are coming from degree 1, so these are the algebraic cycles that cannot be obtained as intersecting higher many divisors in codimension 1, and these are known to be rather hard to control. So yeah, I expect that there's to be no obvious things to say there.
One more, you mentioned the result to be also in characteristic 2, but the definitions seem to assume F is a field of characteristic 0, or?
The result has nothing to do with the specific field on the geometric lattice.
Oh, okay. So,
yeah. In particular, it's valid over point configuration over any characteristic.
Oh, okay. Thanks.
Somebody raised his hand. Yeah, you with the curly.
Okay, so I have two maybe a little bit naive questions. So the first one concerns for the very first polynomial volume form. What was it called? Of these convex bodies. So I noticed that it didn't have power d. Was this a typo, or is this a thing that there isn't this power, that you took this 1 over d factorial times something, but there was nothing to the power to the d, although every else has?
The question is maybe if you go way back where the volume polynomial of convex bodies appear.
Yes, so it was in the very beginning.
Yeah. So I haven't explicitly told you what the ring or module is in that specific context, right? You're asking why there is no d's power there.
Yes.
Yeah. So in fact, there is a hidden ring that satisfies Hart-Lefschetz and Hodge-Riemann relations that you can use to deduce the Lorentzian property of that polynomial. And on that ring, every single one of convex bodies define a degree 1 element in such a way that if you take the dth power of that degree 1 element, the resulting real number is the volume of the convex body. So if I want to explicitly appeal to that ring, I could have written in exactly the same way.
Okay, thanks. And the other question, maybe more like linguistic one, is that this K, you said that it's like the like some kind of a convex cone of these linear operators. So where does this terminology come from, that it's convex cone?
So the original context is that of Kähler geometry or projective geometry, and then they were interested in the classes of Kähler forms or the classes of hyperplane sections. And the fact, an interesting fact about these classes is that they form a convex cone. If you have one hyperplane section and another hyperplane section in completely different projective embedding, you can add the two classes together, and the sum is, again, a hyperplane section in a third different projective embedding. This was the great observation by classical geometers, like a Segre embedding. So you can add two projective embeddings, and that's the source of this convexity, historically speaking.
In the last few slides, after you had the spanning trees appear, would you be able to explain the context of some of these algebraic objects in the context of, say, spanning trees or spanning forests? Like what these actually correspond to?
I'm not sure I have digested the...
So so you have this J, this
yes,
this generating set, so this is all the spanning trees, and then I guess you get some matroid, which is
yes,
corresponds to like the spanning forests.
Yes.
In terms of how the all these constructions, like the intersection homology and, and the size of these the various grades of this algebra.
Yes.
What does that correspond to in terms of the graph?
It's explicit, but not simple.
Okay.
So you can explicitly describe...
Or say, for instance, even just the previous slide, this
all this. I mean, this one is easy.
Multiplication.
You have to, this one is just describing the lattice of flats of a graphic matroid, and this is well known. And even the IH part, you can be explicit, but that amounts to writing down this, this explicit description of this arrow from CHX, CHY. Yeah. So it's not simple, but it can be done.
Okay, so maybe one last question, please.
Maybe you have to wait for the mic.
The mic will come soon.
Hello, this seems to be a vast, all-embracing, unifying notion or idea in combinatorics akin to Langland's program.
Oh, I don't know much about Langland's program. No.
It's unifying, the way it unifies such a broad variety of things within a single umbrella of ideas.
Yes, that's a good thing. Yeah.
Okay, so I think let's stop here, and let's thank June Hajj.
My ears are not very good. So it's my pleasure to introduce Mark Braverman. Mark was born in 1984 and got his PhD at Toronto in 2009. And after a postdoc at Microsoft and an assistant professorship at Toronto, he joined Princeton University in 2011. He has won numerous awards, and I want to mention that in 2016, he both got the EMS Prize by the European Mathematical Society and the Pressburger Award from the European Association for Theoretical Computer Science. So both the mathematics community and the theoretical computer science community want to claim him as a possession, but this is, of course, impossible. And then he got the Alan T. Waterman Award from the NSF, which is awarded to only a single person or maybe two people a year in the US for a young person across all fields of science and technology. And of course, yesterday he got the Abacus Medal, so he's doing well. So his thesis was on the computation of Julia sets. He has done marvelous work in circuit complexity and mechanism design, but he's most famous for his work in information complexity. And this is what he'll tell us about today. Please, Mark.
Thank you. Thank you for the introduction, and thank you for joining. So I would like to start by thanking the organizers and the hosts. So. As you all know, the ICM was supposed to be held in person in St. Petersburg, and after Putin's government invaded Ukraine, that had to be canceled on a short notice. So this invasion, of course, it brought and continues to bring unimaginable death, suffering, and destruction to the people of Ukraine. And to this, the only thing I can say is a 200-year-old quote from Thomas Jefferson, an American president and founding father, who said, indeed, I tremble for my country when I reflect that God is just and that his justice cannot sleep forever. So that pretty much sums it up. I am fortunate to live in the United States, where we are not under immediate danger of physical attack, but the way this war has been impacting us, and in general, Putin's government's actions in the last few years, is profound and deep nihilism that emanates from it. So sure, we are bad, but so are you, and there is no such thing as right and wrong. There is only spheres of influence and alliances and whatnot. And nihilism, it's like a nilpotent operator. You cannot, if you try to invert it, it will explode. Or you will explode, rather. You cannot fight it with, as far as I can tell, you cannot fight it with drones or rockets. The way to fight it is with positive activities that celebrate life and what makes it worth living and what elevates the human spirit. And research in mathematics and celebrating mathematics is definitely one of those activities. And so this event had to go on, not despite the war, but in part because of it. So I'd like to thank the organizers for pulling through, and I'd like to thank everyone also online across the globe who are joining us for this. So this talk is based on many works, almost all of them with my collaborators, the later ones with my students. And I will not always acknowledge all the references in my talk, but there is a detailed bibliography in the paper that accompanies this talk. So I'd refer you there. This award definitely recognizes my group as much as it recognizes me and my co-authors. So the topic of this talk and the topic of much of my research is computational complexity. And the high-level goal of computational complexity is to map out the limits of computation. Computation here is in quotes because part of the charge is to also define what computation is. And kind of the main way you map things is through upper bounds, which are often kind of people call algorithms, the people who are not complexity theorists. And lower bounds, impossibility proofs to show that something is impossible. And this is the mathematical side of things. On the more applied side of things, there is also a general charge of having a sense of how difficult problems are, regardless of what you can prove. So we should have some sense, given a problem, at least based on, because many of those problems are applied, so we cannot say, wait 30 years. We have to give an answer, even if it's wrong, as long as it is useful. And the second charge is to guide new algorithms and heuristics, and this has often been very successful. So in terms of the two main tools, so this is a crash course in computational complexity, the two main tools we use, the first one is abstraction. So you take a computational problem and you map it to some mathematical problem about some model of computation. The model of computation is a mathematical object. So an early example of that is a Turing machine. So it's a completely defined mathematical object that turned out, it was defined before computers ever existed, but turned out that for many, but definitely not all purposes, it's equivalent to our modern computer with an unlimited memory. And communication complexity, which is will be the topic of much of the talk today, is also another very useful abstraction that had found many applications in the last 40+ years. The second tool that is very important and relatively unique is the tool of reduction. So reduction is a statement of the form, if we can solve A, then we can also solve B. And typically, it's used contrapositively. So if you believe that B is difficult, then so is A. So for example, if someone claims that they can generically predict the future and will provide you these services in exchange for 100 euros, you can present them in a simple reduction from predicting the future to winning the lottery or making a killing in the stock market. And by reversing this arrow, you can tell that if they haven't beaten the stock market and instead offering the services to you, they cannot actually predict the future. So that's how it's usually used in complexity theory, in the contrapositive. And okay, what do we mean by mapping out limits of computation? So here is a typical combinatorial problem. This is the three-colorability problem. So given a graph G on n nodes, we want to figure out if it has a three-coloring and how long does it take to figure out if there is a three-coloring and find it if one exists. So in this case, it exists, but of course there are graphs where it doesn't. And there is an easy algorithm that can do it in 3 to the n steps, right? So just try everything. And with some work, the best currently known algorithm is also exponential with some smaller bases here. But in principle, there is nothing stopping us from solving it in n-squared time steps. So that's a reasonable question to ask. Can we do it in quadratic time, in n-squared time, in the size of the graph, roughly the time it takes to read the edges? This is unlikely, but it's wide open. It's roughly as difficult to prove as p not equal to np. And this begets a broader question. So if I want to show that something is possible, so sure, it might take a clever algorithm, but in the end, I'm holding something concrete that then I need to prove that it works. And even if I cannot prove that it works, but it works well enough, people will be convinced that it works. But how do you prove that something is actually impossible? So I'll be able to list most unconditional lower bound techniques, which tells you something. So an early success in terms of unconditional lower bound techniques is the diagonal argument dating back to Cantor and set theory, and then Gödel and Turing's results are also diagonalization results. And so an example of a diagonalization result in computer science is that the halting problem is not computable. So there is no algorithm that, given a code for a computer program, decides whether this will loop forever or it will terminate eventually. So you should treat TAs in intra-computer science course as well, because that's the problem they have to solve. And another example that's good news for us in here is that automated mathematics is also undecidable. I mean, it's not well defined, but for any reasonable definition of this, this is also true. And there are specific instances like the Fontane equations, but generally there is no algorithm to decide whether a given statement follows from given axioms. So, okay, so what about three-colorability? So it's good that we can prove something, but that was the question we asked first. So there is some evidence that I won't go into here that that makes it less likely that you'd be able to show computational hardness of three-coloring using diagonalization. And more generally, as I mentioned, unconditional lower bounds. Unconditional here means that, like, what normal mathematicians call a proof, so just lower bounds. So that a theorem that says you cannot do three-colorability in quadratic time seems out of reach because it was pretty much proved that P is not equal to NP. So this leads us to so-called conditional lower bounds. So, and using reductions. So reductions lead to conditional lower bounds. What is a reduction? So here is an efficient algorithm for solving circuit satisfiability. So circuit satisfiability is the problem is you're given a Boolean circuit, and you need to decide whether there is an input that causes the output to be 1 or not. So the naive algorithm for this takes exponential time. You need to try pretty much all possibilities, and this is believed to require exponential time. So a reduction in this case is an efficient algorithm that runs quickly, like in linear or maybe in n squared time, but that uses three-colorability as a black box. So someone gives you a routine you're allowed to call, that you give it a graph. Is this graph three-colorable? If yes, give me a coloring. Given that routine, you're able to solve Boolean circuit satisfiability. So this is a reduction. We solve one problem using another, and this establishes a relationship between those two problems. So in particular, Cook-Levin's theorem tells us that circuit satisfiability is NP-complete, which means that if circuit satisfiability is easy, then P is equal to NP. And putting those statements together, if P is not equal to NP, you cannot solve three-colorability in polynomially many steps. So that's the logic. So this is the conditional lower bounds logic. And this is a very powerful logic because it allows us to classify problems into complexity classes constructively using algorithms. And this leads to a whole computational universe. So this is a partial list of complexity classes that's been explicitly studied. This is from the complexity zoo that maintains this list. So some of them eventually might collapse into each other, but most probably will not. So as with the real universe, there is a subset that we actually care about. Here is P, here is NP, so that's Milky Way. This entire chart is enabled by reductions. Okay, so still, if you want to remain optimistic, you want to work on unconditional lower bounds that do not follow from diagonalization. And these statements still, for the third time, I guess, appear out of reach. So let's say we want to prove a very concrete statement. There is no Boolean circuit of size n squared that receives a graph on top and outputs whether it's recolorable on the bottom. So, okay, what can we do? Well, we can try to break this problem into many steps and then build a ladder and then slowly climb it, or quickly if you're lucky. And there are several kind of so you do it by restricting your model. Instead of saying a general circuit, you say, okay, let's use a monotone circuit. You notice that it gets harder to three-color when you add more edges, so let's only allow monotone circuits that for this problem. Or arithmetic circuits that have some more arithmetic structure. Or you restrict your circuit to, say, Boolean formulas, but that are formulas of bounded depth and not general deep circuits. Or you can abstract away part of the model, which is what we'll do with communication complexity. So let me just, this is by far, the circuit complexity route is still by far the most studied one. So let me show it to you. So it's a complexity theory talk, so I have to have a lot of abbreviations. So the compromise is that they're all fit on one slide, and you don't need to know what they are, except it's some kind of chain of inclusions. Pn and P are here in the end. So if we manage to separate, to put a separation here, then we solve the P versus NP question. But even very consolation prize are amazing results. So whoever does this or this will probably be given this talk in some multiple of 4s. So for example, this class can do whatever artificial neural nets can do because they are of bounded depth usually. So let's see how we are doing here. So so we have some separations here. None of them follow from diagonalization, so that's good. So the first one is about 40 years old, and this is combinatorial. And since then, there were also algebraic separations for this one, but the best ones are still combinatorial. The next one is from late 80s. This is algebraic by showing that some shallow classes can be well approximated by polynomials. And this concludes. So we've been stuck here for about 35 years. This is probably some clever argument can do. The next ones, it seems that it's probably as hard as P not equal NP in some sense, at least to me, but some people might disagree. So maybe this ladder doesn't lead us all the way, or the bounds are out of reach. And this motivates, so there are other reasons to study communication complexity, but for me, it's still the main motivation is to build a different ladder. And based on communication, so here is a situation that is very common for a complexity series. We have a computing device that we don't understand, trying to compute a function that we don't understand. That's very complex. So how can we at least make some sense? So, okay, so if we manage, let's put a line in the middle. And let's view the input as partition between the two parties. And let's abstract away anything that goes in the left brain and anything that goes in the right brain, and only measure activity across this red line. So that's, we gave away a lot because the left brain and the right brain are allowed to do arbitrary calculations, but at least we get to make some progress. And a lower bound on this, if you manage to show that you need some amount of activity on this red line, you get some lower bound on the activity needed to perform computation. And this is very powerful in many models and many realistic scenarios. This actually gets you all the way. So it's a very useful abstraction in many cases. So circuit design, you literally do what I just did to a circuit instead of a brain. But also things like data structures, distributed algorithms, and application and other applications. So it's in many cases it gives unconditional lower bounds for that are pretty much precise, so as good as the best algorithms we have. So let's take a step back and define communication complexity a little bit more formally. So we'll focus on the two-party setting. We have Alice and Bob here. Alice has input X, Bob has input Y, and they wish to implement some functionality. So the basic object here is a communication protocol. So we assume they have shared randomness because we will allow errors, so we need shared randomness. And the protocol is just, so we abstract away, we assume that Alice and Bob are computationally omnipotent, so they can do whatever they want as long as it's casually valid. So the first message can only depend on what Alice knows and the public randomness. The second message can, and any subsequent message can depend on the messages so far, on the knowledge of the party speaking, and on the randomness. And in the end, they are supposed to output an answer. And the communication cost of the protocol is the number of bits that have been exchanged by this protocol. So you can define the communication complexity. OK, here is a formula. But here's what it actually says. So you need to complete the task with acceptable error, exchanging as few bits as possible in the process, and that's the communication complexity. So you want to solve the problem, speak as little as possible, and that's the communication complexity of the problem. In the brain slide, that's the number of blue arrows. So that's a measure of interest. So our running example will be actually one that has many immediate applications to some of the scenarios that I pictured before, is set disjointness. So there are n species of animal, and Alice and Bob each has a bag of k animals out of n species, and they want to know if they have an animal in common or not. So this is a primitive in many other downstream applications. So in this case, there is. Sometimes there isn't. OK, so again, so two sets of size k out of universe of size n want to decide whether they have an element in common or not. The trivial upper bound would be for one of them to send the animals to the other. And this requires, so one animal takes log n bits to name, so it's k log n. So this is the trivial algorithm. And it turns out that you can do better. There is a result by Hasted and Vigderson that shows that you can do in order k, the size of the set, bits of communication. And you can also prove, it's possible, it's a result from late 80s, early 90s, it's a combinatorial proof showing that actually k bits are necessary. And this is a building block in many unconditional lower bound results for various models of computation. So since we want to kind of build forward, a more generic approach that we can hope to generalize is based on something called the direct sum principle. So if we look at the problem, let's fix n to be 3k. So we need to make 3k decisions of the form, is 1 in both x and y, is the second animal in both x and y, and so on. So we have 3k decisions, each of this simple form. So if by some miracle we could say that the communication cost is 3k, the number of decisions, times the cost of each box, so we need two miracles to happen. We need this product to hold, and a priori there is no reason for that, and we need the cost of each box to be at least constant. But if those two miracles happen, then you get an omega k lower bound, and indeed this is the case. In this specific example, there is an information theoretic. OK, so I haven't said information, but there is an approach based on this type of reasoning for this specific problem. So in general, so this is a very generic type of statement. A direct sum conjecture asks, I give you a task that costs c. Then is it true that k independent instances of t cost roughly k times c? So you can always solve them one by one, but maybe I can get a huge volume discount. And it's a very promising approach to unconditional hardness proofs because it's a generic way of taking a hard problem and making it harder, which is something that sounds crazy, but that's exactly what you want to do if you are a lower bounds person. If you want to prove impossibility results. So strong enough direct sums, even for communication, lead to progress on that ladder that I showed you before, say through Karchmer-Vigderson games. So it's a well-motivated problem. In many cases, direct sum is false. So here is one spectacular example of that. So the model here is circuit complexity. And the problem is a very simple one. You get a matrix over F2 and the vector, and you want to multiply A by X. So you get n bits input, n bits output. And OK, and A is completely random. So A is not part of the input. A is fixed once and for all by nature randomly. So a simple counting argument tells you that you need a circuit of roughly n square size because there are 2 to the n square matrices. So you need 2 to the n squared different circuits. So a typical circuit will be of size at least n squared. you get to shave some logs that are not important, but that's pretty much it. So n squared. What about n copies of this problem? Now I fix A. A is not part of the input, and I need to multiply A by n different x's. So direct sum would predict that it requires n cubed circuit size, but of course you can do better. This is a matrix, and this is a matrix, and you can do fast matrix multiplication and do at most n to the 2.38, but possibly even better, but definitely much better than n cubed. So it fails miserably. And this leads to the same question about communication complexity. So is it true for communication that n copies of a problem is roughly n times one copy? In full generality, it also makes sense in specific examples, but most interestingly in full generality. And one source of inspiration so in complexity theory, we are lucky to have definitive answers, and even more lucky to have precise answers, but one source of inspiration and envy is Shannon's information encoding theory, where it actually does have all the answers, at least to basic questions. So so a tale of two theories, coding theory and computational complexity. Of course, so the goal in coding theory is to understand data transmission. The goal in computational complexity is to understand computation, as I mentioned on the first slide. Here, there is a zoo of different channels. We have models of computation. Big questions are actually theorems, some of them from the 40s and 50s. Big questions like P versus NP are conjectures. And moreover, never mind what this specific statement is, you can take a very specific question about very specific channels, very specific transmission tasks, and get a very exact answer on the cost. So you need you have all the exact answers in many cases, whereas here, three-colorability, the best algorithm is whatever is 1.3 to the n, and we basically have no non-trivial lower bounds. So the gap is not just big, it's exponential between what we can prove is possible and what we know how to do. So let's try to learn a little bit from Shannon's theory. So this is Shannon's theory in a couple of slides. So we assume as a lossless binary channel just means that Alice gets, now it's a transmission task, so she gets to transmit zeros and ones without any interference. So, and there is a message X that she wants to send, and it's distributed according to some distribution mu. So the inherent amount of bits it takes to transmit X is given by its entropy. That's an earlier result. So it's sum of mu times log 2 1 over mu. And the cost of communicating many, so Shannon's noiseless coding theorem, which is one of the earlier results in the field, says that the cost of communicating many copies scales like the entropy. So Shannon's noiseless coding theorem says that if we define by Cn of x the cost of transmitting n independent copies of x, then the amortized transmission cost, the per copy cost of transmitting, so the limit of cost of transmitting n things divided by n scales like h of x. In particular, even if you hate logs and you think it was just fancy math to make things complicated, this tells you that that's the truth, so you have to deal with it. So it gives an operational kind of physical meaning to the formula for h. And h is nicer than c. So here's a toy example. So you want to encode a random treat, so a random number which is 1, 2, or 3. And the best encoding is something like you assign 1 to 0, 2 to 1, 0, and 3 to 1, 1. And this costs 5/3 per message. And sending 2 turns out, you just do the calculation, it's 29 over 9. So you get that C1 plus C1 is not equal to C2. It's actually less. So this is 30 over 9, and this is 29 over 9. So 1 plus 1 is not equal to 2. Direct sum fails for C. But for entropy, of course, it doesn't. Log 3 plus log 3 is equal to log 9. So it's a nicer quantity. In this case, it's not a huge difference, so it doesn't really matter. But you can see that it's essential that this quantity exists. So if people were trying to study C, maybe it would be a very heavy subfield of discrete mathematics instead of the streamlined theory of communication. Because very quickly with C, you start looking at binary trees, and it becomes a nightmare. So direct sum holds for H, and Cn up to lower order terms is n times log to 3, the cost of transmitting random digits between 1 and 3. So information complexity is now defined by analogy. So information complexity to communication complexity is what Shannon's entropy is to transmission cost. So the goal is to find a continuous relaxation that looks nice and has nice properties. And another kind of thing that we get to borrow from Shannon's theory, and if you haven't seen this before, it doesn't matter, but it's good to know that those are actually not some crazy statements, but actually simple mathematical formulas. So you can quantify things like uncertainty left in x given y, that's conditional entropy. Mutual information is how much does y teach us about x, which is just the reduction in the uncertainty in x after you learn y. Conditional mutual information, this is a formula for how much y teaches us about x if you already know z. And it's nice that it's a 4-symbol formula. Of course, you can write it, it's backed up by some logs, but this is friendlier, and especially if you need to write a lot of those expressions. So it simplifies life a lot, and also conceptually, this actually tells you what it is. So now the information cost of a protocol, so given a prior distribution on inputs, the information cost of a protocol is what the protocol reveals to the parties about each other's inputs. So this is what the protocol, as executed, the transcript, what it reveals to Alice, who already knows x about y, plus the other term. And this depends on both the protocol, the transcript, and also on the prior distribution, because for some priors, you just have more uncertainty than others. And the information complexity of the problem is it's just complete the task with an acceptable error while revealing as little information as possible. So instead of communicating counting bits, we want to reveal as little as possible about the inputs. Doesn't matter how long the communication is. So this is the definition. It's literally the same. There is one difference you'll notice. Instead of a minimum, you have an infimum, because it's possible that you'll have a chain of protocols that keep growing and keep revealing less and less information because they become some clever way. Actually, it happens already for the simple 2-bit AND function, which is the simplest non-trivial function, so as we'll see. An easy fact is, just as Shannon's entropy is a lower bound on communication, information complexity is a lower bound on communication complexity, and it will be important what's the relationship in the other direction. And now we get to nice properties. So the first nice property is that information is equal to amortized communication. So the limit of communication complexity is this information complexity quantity. So justifying kind of that it's an analog. It has, just as log 3 plus log 3 is log 9, you get the direct sum property that the information complexity of two independent tasks is equal to the sum of the two pieces. So you have the direct sum property. OK, so and with this in mind, we actually have a way to tackle this direct sum question. So we have this theorem that says that if I take many copies and divide the cost by n, I get the information complexity. So n times the information complexity is roughly the communication complexity. And remember, direct sum question was whether it's equal to n times the communication complexity. So it's if and only if, by canceling n out, communication complexity is roughly equal to information complexity, which is a meaningful question. So so direct sum question is equivalent to whether information is equal to communication, which is roughly equivalent to something called interactive compression. Because it asks whether if I have a low information protocol, can I convert it into a low communication protocol? So let's see. So in the one-way transmission case, so Shannon's results tell us that C of x is at least h of x. But there are early coding results, like Huffman coding, tells us that H is actually off by at most 1 in expectation. So basically, whenever you have a signal like English letters, you can encode them with the bit strings. Roughly speaking, you give long strings to letters that are worth a lot in Scrabble and short strings to letters that are not worth a lot in Scrabble. And you can get an encoding that's within 1 bit of optimal. So C is roughly equals to H. And long but informative messages can be shortened to almost their information content. So things like this lecture maybe can be shortened. And the question is, what about the conversation, the back and forth? So can a long but uninformative conversation be compressed into a short one? And this is almost equivalent to, by this logic that we saw, this is almost equivalent to the direct sum question. So let's say here is a long and uninformative conversation. They send 2,000 messages that are just an interleaving blah, blah, blah. So here is a compression of that you can imagine that is much shorter. So, and it conveys the same information. So is this possible? And it turns out that the answer is no. So at the time, it was surprising both that it's no and that you can actually prove it. So kind of the thinking was that if it's yes, we'll prove it, and if no, it will be very hard. But they showed that you can have an exponential gap. Sometimes communication is exponential in information. So you can have a protocol that transfers I bits of information, but it's very long, and there is no way to arrive at the same place of very little knowledge through fewer than 2 to the I bits of communication. And as a result, no direct sum for communication complexity. And weaker interactive compression results, which we do have, lead to weaker direct sum theories. So maybe you can't compress all the ways, but I won't elaborate, but the best we have right now is a square root n instead of n. So we are partway there, and we don't know if you can get to n to the 1 minus epsilon, for example, here. So far, let's make an interim summary. We have two-party information complexity. That's an analog, an interactive analog of Shannon's theory. It gave us a handle on direct sum questions, and eventually led to the resolution of the direct sum question. And next, let's see. So remember, the other aspect of Shannon's theory was the ability to give very precise answers to concrete questions. So let's revisit the animals with this in mind. So here we have a bag of, out of n species of k animals each, and we want to decide whether they have an animal in common or not. And of course, now it's obvious that we'll want to use the direct sum approach. So we break it into n questions, each one about a single animal. And based on this theory that we've been discussing, the communication cost of this problem is exactly n times the information complexity of what is the basic building block. It's an n function. It's whether the peacock is in x and also in y. So it's an n function with respect to some prior distribution. And the prior distribution is where you add each animal with probability k over n, because you have to end up with sets of the right size. So this question about intersection boils down to understanding the information complexity of 2-bit disjointness. So even if you miss the last 15 minutes, here is a concrete question. Alice and Bob each have a bit. So it's a question about 2 bits. It can't be too bad. It's about 4 numbers. They are distributed according to some mu. So the 3 degrees of freedom, 4 numbers, it's a distribution on 2 bits. And they want to figure out the end of the 2 bits. Are the both bits 1 or not? And turns out that we can actually give the optimal protocol for AND in terms of not revealing information. So here's the protocol. So Alice gets a bit, and she'll make it a continuous number now. So if x is 1, she sets a equals to 1. If x is 0, she privately samples a number between 0 and 1, a real number. And Bob does the same thing. Now, there is going to be a clock that continuously runs from 0 to 1. And so you locate your number on this real line. So in this case, both of them got a 0 because they're both not at the tip. Here, Bob got a 1. So that's what they're going to do. Now they're going to start the timer. If your number is called, you raise your hand and the protocol stops. So if someone raises their hand before the clock reaches 1, it means that they have a 0 and the answer is 0. If the protocol runs out to 1, they both have a 1 and the answer is 1. So at least it's correct. It takes effort to prove that it's optimal, but it is optimal. And you can calculate its information complexity, and it works out to 2 over ln 2 times k over n. So ultimately, we get a refinement. So in the first slide, we saw that it was omega k and order k. Now we know that it's 2 over ln 2k plus low order terms, whenever n is much larger than k. Otherwise, you get, we also know what it is, but it's some other number. OK, so that's an example. So what we got here is an asymptotically optimal communication protocol based on this clock algorithm for end. It would be, I can't imagine how I would discover, or anyone would discover it directly, because it's not a natural protocol from kind of, it would be very hard to discover directly. Moreover, you can prove that you need super constant number of rounds to get this performance, that if you stick to a constant number of rounds, you'll actually lose some extra multiple of k factors. And the clock, it's not even a real protocol, right? So it's a continuous protocol, and you discretize it. And when you discretize, you lose something. And to make this something small, you need to discretize into super constant number of steps. So it's actually, and that's actually a theorem, that you need a super constant number of rounds to get to optimal communication cost. So in addition, so far, so what we see is that it's a new tool for precise communication complexity bounds. So this is one example of that. And there are additional connections that I briefly cover in the note, but let me just mention them here. So of course, whenever you have communication complexity is useful, information complexity is also useful, things like distributed algorithms, distributed learning, streaming algorithms, which is, it's an algorithm where, like, think about yourself as a router. You need to compute on a stream of data where there is no chance that you'll be able to store all of it. Within complexity theory, as you can imagine, direct sum is about making hard problems harder. And there are also approaches to making hard problems even harder, like direct product theorems, that they're useful for cryptography, among other things. And so it's things like saying, not only do you need a lot of resources, but if you fail to get those resources, your success probability is exponentially small. And this is a type of result that we can also get using similar technique. Parallel repetition is a tool in complexity theory, again, for a similar kind of reduction in success probability. Another direction is you can take this analogy further and not just talk about, so we kind of spoke about noiseless coding, but you can start asking about noisy coding. John mentioned it a little bit yesterday, but you can build a theory of interactive coding. You can adapt those definitions to quantum communication complexity and get and quantum information and get interesting results there. And actually, the final connection is also the earliest connection is to private computation, which is the last thing that I want to touch upon. So in terms of, it works where it works. And so far, it works to a point, we know exactly where it stops working, so far at least. It stops working at the point where information theoretically secure computation begins. So, and of course, there is always this persistent fear that this ladder will also get stuck before we reach the moon. So what is secure computation? So it's an important field. It's mostly studied in cryptography. So it's the same setup. So Alice has some input, Bob has some input, and they don't care about how much they communicate anymore. What they care about is they don't trust each other. So let's put sunglasses because they're shady. So they want to reveal as little information to each other as possible. So an early example of that is the 2 millionaires problem, where there are 2 millionaires. They want to figure out who has more money without revealing their wealth to each other or the authorities. So the threat model here is the honest but curious model. It's relatively weak for cryptography, but that's exactly what makes sense for us, where they'll follow whatever the protocol, but they'll try to be nosy about and learn some things they're not supposed to. So this is essentially the information complexity setting. If it looks like it is, it is. And actually, it was, if tracing back to the literature, it was one of the alternative motivations for writing the same expressions. It's very common in theoretical computer science that things that make sense come from different directions simultaneously. It was an alternative motivation for this entire area. And as a corollary of what we've been discussing earlier, it's bad news for this theory. Information theoretical security in this model is almost entirely impossible. Basically, if you want to compute disjointness and you want to reveal as little as possible, your best hope is to just communicate as few bits as possible. There is nothing clever that you can do. And this is in contrast to cryptographic security, which is attainable, and it's subject to a lot of ongoing work, both theoretical and applied. So cryptographic security means where you assume that Alice and Bob are computationally bounded. OK, so in the three-party setting, so you have three parties, Alice, Bob, and Charlie. Now they're allowed to communicate privately. There is a surprising result. It's actually possible to execute information theoretically secure computation. It's possible to compute anything without revealing anything except for the answer, which is, it seems false, but it's actually true. And moreover, here is an even more surprising result, to me at least. Here is a tiny modification of the communication setup. So you give them this is called an AND channel. So it's basically a circuit where they can press a button simultaneously or not. So if Bob presses the button, nothing happens. If they both press a button, then the light goes on. So this is the AND channel because you press buttons and you get the AND of the inputs. So that's the truth table of this channel. And it turns out that even this is enough to essentially implement secure computation. So this small tweak is enough to do secure now with two parties. So the 2 millionaires can use this device to compute their function. And in both cases, actually, and in one case, we actually wrote a paper with a student, and that you can write very happily, write the direct sum, it works, everything is great, but you get a result of the form 0 plus 0 equals to 0, which is true, but not useful. So that's what happens, and so which brings us to the question of what's next. So new tools to get around. So secure computation here is not our friend because it destroys our measure of complexity. So it's possible that we reached the end of information theory that we can borrow, and now we reached the stage where we have to invent new information theoretic definitions. It's possible that we have to go, so it's everything, the story I said today, a big chunk of it you could repeat without saying the word information using matrices, semi-definite programming, and inner products. No, it wouldn't be as precise, but you could get maybe 80%. And that approach, it's not, maybe it's better studied. So it's possible that there are new analytic tools that we can borrow from 3D tensor theory. So with three parties, instead of matrices, you have 3D tensors. A lot of the nice theory, of course, doesn't carry over, but maybe enough does. So that's another approach. And we have now the two-party information complexity case as a blueprint, at least, maybe not what to expect, but at least for what to hope for. Or, of course, as many times in this area, maybe we'll find another frontier where communication ends and computation begins, and computation is just this beast that resists analysis. So in any case, it should lead to exciting new results about those. Thank you.
Thank you very much. Are there any questions? Yes?
You mentioned the cases for two-party and three parties. I'm just wondering what the scaling is with respect to n parties, because I think for quantum, at least, like there's a multiple interactive proof system which is classified as RE computable. Is there a corresponding result?
Okay, so you have to, it depends on what the question is. So this is not a proof system. Proof systems become more powerful very quickly with the number of parties.
Yes.
In terms of communication, there is definitely, so the gap, the kind of the difficulty gaps are 2, then 3, 3, 4, 5, 6 up to log n are roughly the same, and then it gets really hard. So if you beat polylog, like log to the 100n, you already are in the circuit lower bounds domain. So I would say that 3 is interesting, and the next stop after that is log n. And there are surprising upper bounds for communication there, actually. But that's the scaling here.
Thank you.
Thanks.
Any other questions? Yes.
So I have two questions. The first regards about this when you talk about this two-party computation with the clock. I was just wondering that how is this clock actually defined? Because to me it seems like they exchange something, but there is this weird time parameter which I have hard time to seeing how to define it.
Correct.
And then the other question regards about this. For example, two or multiple computation, when you said that there is this theorem that three-party computation, they can compute any function f with this without revealing information. Like, what kinds of functions are we talking about here? Like, are they like, okay, for example, like each gives n bits and outputs k bits or something like that?
Okay, so the first question was about the clock protocol, pointing out that it is not a real protocol. So it's a process. The way you turn it into a protocol is you take your continuous clock and turn it into a digital clock with seconds, and every second they raise their hand if their number is in that interval. And there is some loss if they're, so this works perfect unless they fall in the same interval. And this causes a loss that turns out to be 1 over r squared, which is, so we can quantify that also, that the loss from digitizing it into r seconds is 1 over r squared, which tends to 0 as long as the number of rounds is super constant. So indeed, this is just a nice way to present it, but if you turn it into a protocol, it becomes just digital time. The second question was about secure multi-party computation, and it's any function. So it's completely unrestricted. So anything that you can imagine, you can do with this. At least you start getting into details when you want to be more efficient and so on, but if you abstract everything away, you can compute anything without revealing anything. That's pretty much the case.
Is there another question? Yes.
Can you explain again why diagonalization techniques you think are not useful anymore? Or
It's not. I'm not a huge fan of those statements of theorizing what's not useful. There is a specific thing called relativization, which is, so you can add an oracle to computation, and there is a sense that diagonalization results survive that, and we know that some of those statements that we would like to prove are not true under relativization. So that's an obstacle, at least. So you need, basically, if you carry them as is, we believe that you'll prove something that's false. So this chain has to break somewhere. It doesn't mean that it's not going to work. It just it raises a question mark. So also, for example, when you get a proof that p is not equal to np, that's one thing you look for if you don't want to actually read and look for a mistake is how does this break down? Does it get around this obstacle? So, but of course, yeah, I'm not a huge fan of statements that this technique will not work. It's just evidence that should give us pause but not stop us. Especially if you're a student or you should try. That's how that's the richest fields are where people are afraid to go because of some ancient reason.
Thank you. Any other questions? Yes.
So what's your expectation on P equal NP?
It's more likely to not be equal, but I think there are several annoying scenarios, like they're equal but not practically equal. So I don't know, I mean, steering controversy. So for example, if the unique games conjecture turned out to be simultaneously true and false, P would be equal to NP, or at least maybe closer, but there would be no kind of immediate ways to to practical algorithms because the chains of reductions are really long. So I would say that more likely they're not equal, but I'm not as sure as all that.
Thank you. Are there any other questions? If not, we thank you, Mark.
Thank you.
Wonderful talk.
Okei, käytetään halua. Ei. Lisää ainakin 5. Nämä on luultavasti huonommat komponentit, mutta taas 150. Tässä ollaan joo. Suunnilleen samassa. Se tarvitaan pointti. Vai onko se Ukolla oma pointti?
So tomorrow is really here? The same
Yes.
big?
Yeah. Mä luulen, että Ukolla oli oma. Missä oli? Katsotaan. just ei käy. Oliko se just äsken tuossa? Tämä pitäisi olla ihan semmoinen, että pistää vaan kiinni. Onko sitä mä näin?
Onko toi nyt Mac-yhteen sopiva?
Se on ainakin pitänyt olla, mutta... Vahingossa.
ladies and gentlemen, dear colleagues. So it gives me a particular pleasure to introduce Hugo Dominique-Copin as a fellow probabilist, and since yesterday also as a fellow Fields medalist, and also as a fellow Genevois from Geneva. So Hugo has finished his undergraduate studies at École Normale in Paris, after which he moved to Geneva, where he completed his PhD under supervision of Stas Smirnov in 2011, and he became full professor there in 2014, and then also had a position at IHES in 2016. And well, his work has been distinguished with a number of prizes, so I have a very long list here. I'll give you a few. There's the Rollo-Davidson Prize, the Oberwolfach Prize, the Prize of the European Math Society, the New Horizon Breakthrough Prize, the Loew Prize, and the Dobroshin Prize. And as you've heard, well, his work has contributed tremendously to our understanding of phase transitions for not just two-dimensional, but also three-dimensional and four-dimensional models of statistical mechanics. And, well, I'm sure you're all impatient to hear him speak. And so, well, we're all looking forward to his talk about critical phenomena through the lens of the Ising model.
Thank you very much. Thank you. Wait to hear the talk before clapping. So I'm not the first speaker, I'm very happy about that, but I'm the first speaker with a French accent, so it's still something. So if you don't like the math, you can at least see that as a warm-up for the many talks with French accent that you will hear during this workshop, this ICM, sorry. So what I decided to do in this talk is definitely not giving you like an exhaustive list of what I like in my papers. I thought I would rather do a panoramic view, but of the field, by focusing on one specific example, like one model, and taking the time to introduce it, and through this example, trying to give you ideas of what is happening in my work, but also more generally in the whole field. Okay, so for instance, we will flash through a number of things. Don't try to read before I go to the next one, just to give you an impressionistic impression of certain of the things that I will discuss. Some I will take time to explain to you precisely what it is. Some others will be concepts that will pop in and just disappear almost immediately. But these are things that we will touch during this talk. But before I start this talk, I want to thank everybody who is important for me. And in particular, while preparing this talk, I realized that by choosing a very specific example to present to you, two very important people to me just disappeared completely from the talk. And I felt that this was very unfair because they are extremely important people in my life and in my, as a normal person, but also as a mathematician. So I want, look at these adorable faces. So Johan Manulescu and Vincent Tassion are my closest collaborators. They are also my closest friends. And I would not be here today if they would not be also here today, by the way. And, well, I know it's an individual prize, but I would like to cut a piece of this medal to give to each one of you. So thank you very much for being part of my life. This was like, ooh. Second thing is that I'm very lucky to have supervised a number of people and to be supervising a number of people. So I really want to thank all of them first, and for all, because they actually bring many things in my life. And we all know as scientists how important it is to transmit to people. But it's also, we all know that the people we transmit to are actually also giving us a lot of things back. So thanks to all of them. And then a chunk of my collaborators, actually, they were not all fitting there, so still speak to me tomorrow if you are one of my collaborators and you are not here. So these are also very important, of course, and more generally, I want to thank the whole community. I'm very lucky to be part of a very, very joyful community with only great people, so thanks to all of them. Okay, that was for the emotional part of the talk. Let's dive into the math now. You know, I was almost crying. Now it's your turn to be almost crying. So let's start with, just the basis. So how do you cook up a mathematical model for a physical phenomenon? And I want to give one example again, and I will focus on this one, the example of the Ising model. Okay, so how do we cook up a mathematical model? First, we need a motivation. And in my case, for this model, it's going to be a motivation from physics, but it could be from computer science. It could be from another part of mathematics. I mean, it can be from many different things. And what happens is the following. So maybe you use Hugo the mathematician. Now you have Hugo the experimentalist. So what am I doing here? I'm taking a magnet, and I'm heating it. And as you may already know, but otherwise you are going to discover in like 30 seconds, when you heat a magnet above a certain temperature, it just loses its magnetization. It stops being a magnet. This temperature was discovered by Pierre Curie. I mean, this phenomenon was discovered by Pierre Curie more than 100 years ago. And what happens is that if you take different magnets constituted from different things, then there is a different critical temperature, but it's always the case that at a certain temperature, voila, you cease to be a magnet. Okay? So how do you explain this phenomenon? That's going to be the motivation of the talk. Well, first thing that you want to ask is, what do you mean by, I'm going to do a mathematical caricature in some sense of this phenomenon. So I need to understand what is a mathematical magnet, right? So we are going to make a few assumptions. That's what we do when we try to make a model. We are going to simplify the picture in order to get a well-defined mathematical object. So first thing we do is that we are going to use the fact that magnets are in some sense a huge collection of tiny dipoles that have their own what we call magnetic moment, but think that they are like tiny magnets themselves. Okay? So these are what I drew here. And I want to be understanding how this thing interacts. And that's going to be basically the Ising model. But before I do that, I'm going to follow the advice of the wiser people than me. So in particular, Mark Katz had this motto that you should be wise and discretize. And I'm very well aware that every single time I said that, half of the audience is like, no, you should do the opposite, you should go to the continuum. But in my case, I discretize. So I'm going to discretize in two ways. First, I'm going to just think that my dipoles are actually regularly spaced on a finite chunk of a lattice. And you will see much more exciting lattices in an hour, but in this case, it's always going to be ZD, okay? Second thing that you do, a second discretization in some sense, is that you are going to assume, and this one, you can discuss it a little bit more maybe, but you are going to assume that your dipoles, they only point in one out of two opposite directions. Let's say north or south, or up, down, which mathematically is just +1, -1, for instance. So I'm going to assume that my dipoles my moments are valued in +/-1. And now I just have a magnet. What is a mathematical magnet? It's just a function from this subset of the lattice into +/-1. Okay, up to now, I hope I didn't lose everybody. Very good. And what do I want to measure on this magnet? Well, I want to measure if it has a magnetization, if it acts like a magnet. So I'm going to look at the mean number of up dipoles, up moments compared to down moments. So I'm going to just look at this quantity here, the average spin, if you want. But for now, sigma is just like one element of the functions from lambda to +/-1. So that's the first step in our French cuisine. We do these discretizations to get what a magnet is. Now, second ingredient in the recipe is that, as you have guessed, a magnet is just made of like millions of millions of millions of small dipoles. It's a very complicated system. So it's kind of hopeless to really study it completely in detail. So what we are going to do is we are going to introduce some randomness and pick a magnet at random, because then if we do that, we can ask ourselves a question which is a priori much simpler, which is what is the typical behavior of the magnet? So let's introduce some randomness. And we are going to just try to understand, to construct our randomness in a smart way that is kind of coherent with somehow what we see in actual magnets. And in actual magnets, what you see is that if you put two of them, they want to align, right? I mean, the north pole of one is attracted by the south pole. So here what we are going to say is that for each small dipole, it has a tendency to align with its neighbors in the sense that if it's disaligned, then there is an energy cost, okay? And if you think of that for all the magnets, the pairs of magnets in your big magnet, then you end up with an energy cost which can be written like that. And here, x tilde y would just mean that I'm going to restrict, I'm going to think that the most important interactions are between neighbors. So I'm going to completely forget about the interaction between a small dipole and a point which is far. I'm only looking at pairs of dipoles, of neighboring dipoles. So. And once you have done that, then you can go back to prehistory almost of statistical physiks and say, okay, if I have an energy, then the probability of an object should be smaller and smaller when the energy is larger and larger. And actually, Gibbs and Boltzmann actually gave us kind of the right recipe to cook up the probability measure once I have the energy, which is to say that it's proportional to exponential of -1 over t times the energy, where t is should be understood as a temperature, which is telling you how much you care about the energy. Okay? So the larger t, for instance, when t goes to infinity, this becomes basically 0, and you are looking at a uniformly sampled magnet. On the other hand, if you let t to 0, you care more and more about the energy, and you are going to get one of the two magnets with the with the mean energy, so the max probability, and it will be all plus or all minus. Okay? But in between, you have something interesting. So T, as I said, should be interpreted as a temperature. Okay, so that's just the Ising model. Okay, I told you what a magnet is from a mathematical point of view, or from the Ising model point of view, and I told you how you sample one at random. Okay? And notice one thing, so before I was measuring the magnetization of a given magnet. Now that I have a probability measure, the magnetization is going to be the mean, like the average against this measure of the magnetization of each magnet. So here, I'm going to define the mean magnetization as the average of the magnetization for each magnet. And notice that here, if I look at this measure, there is a plus-minus flip symmetry. If I reverse all the spins, I get exactly the same energy. So it's a very simple computation that you can make in your head that this average is 0. So up to now, okay, we defined a mean magnet, but its average is 0 at every temperature. I don't get anything smart out of that. So that's the last ingredient now that I want to introduce. I want to introduce a symmetry breaking. I would like to be kind of breaking this plus-minus additional symmetry that I find not so natural. So what I do is simply, I fix the boundary spins here to all be plus. Those are not allowed to be anything else than plus. One way of interpreting this is you can imagine that you are immerging your magnet in a magnetic field, and that the boundary of it is going to be forced to be aligned with the magnetic field. I'm lying a little bit for people who know, but I mean, in this type of talks, you are allowed to lie, so let's use this superpower. And so let's fix plus like that, and here is a simulation where you see the two things, and here you feel that there are more pluses than minuses compared to here. There is a symmetry breaking ready. So you can define the measure exactly as before. It's just that now, if you want, it's the energy, but when you are forcing the boundary spins to be plus, and again, you can look at the average
of your magnetization, and because of this thing that you feel here, in fact, there are going to be more pluses than minuses, so the magnetization now is going to be strictly positive, which is quite good. You kind of want to say that your magnet, in some sense, has a tendency to align with the magnetic field that you are putting. Very good. But even more interesting and more importantly, as I said, the magnet is made of billions and billions of small dipoles. So essentially, especially because we are mathematicians and not physicists, we are allowed to just take the limit, and we want to be looking at the limit in infinite volume of this object, because this is what is going to describe a very, very large magnet. So you do that. You take the limit when you take lambda to ZD. You take a bigger and bigger box, for instance. And you look at the convergence. What did I do? Oh, you take this thing, and you take the convergence, and you define the limit, which I'm telling you exists. Okay, you have to trust me. You have to prove it, but this is not very difficult. You look at the limit, and this you call it the spontaneous magnetization. And really, you should think of that as exactly the quantity you would get if you take a real magnet at temperature T, and you measure the strength of the magnet. In some sense, this is a mathematical equivalent of this quantity. Okay, so in particular, if this is strictly positive, it's kind of telling you you are a magnet. You keep a spontaneous magnetization. If it's zero, it means, well, you are not a magnet. You are just a magnet of zero strength, so you are not a magnet anymore. Okay, so really, this is going to be one of the key players of the talk, and the game is going to be, is it positive? Is it zero? When is it positive? When is it zero? Etc., etc. Okay? And just one thing I want you to remember is that here we are going to soon talk of a phase transition, and really it's going to happen because we took the infinite volume limit. We go to infinity. So most of the interesting phenomena in statistical physics happen when you go to the infinite volume. Okay? When you take infinite limits, sorry. Okay. First recap. So you survive first part of the talk. Congratulations. Oh, well, there is still a slide, but most of first type of the... So first thing, you start from a physical phenomena, and this, from a physical phenomenon, sorry, and this leads to a mathematical model by assuming some simplifying features, right? There was a discretization, there was like, I'm going to take things at random, and I take the infinite limit, for instance. But this is not something isolated, and that's why I wanted to tell you, like, I'm taking a special example, but actually I want to illustrate something much more general. It's not isolated. For instance, if you want to understand interface growth, there are tons of like mathematical models that actually describe this, and there are models that are in the KPZ universality class, we call it. You will have talks on that later on in this ICM, because this is a very, very rich and exciting area of research nowadays. You could also start with, trying to modeling a gas. And again, by some different, so there will be no discretization, but by some assumptions, you can get to a mathematical model. Here it's called the hard sphere gas, and you will also hear, I will come back to that later, about this in this ICM. Or if you want, you could try to understand what happens in a heavy atom, in the nucleus of this. And Wigner kind of told us that if you look at random matrices and spectral properties of random matrices, you can get information on this. These are just 3 examples. I could give you 1,000, but I was specifically told that I should not, keep you more than 1 hour. So I'm not so good at this. But so there are tons of examples, and they always follow the same pattern. You start from a physical phenomenon, and you make a simplifying feature to get to a mathematical model. And let me say what I like about this is that clearly, I'm motivated by understanding what's the physical phenomenon, but much more than that, what I'm interested, it's like, okay, the physics gives birth to this model, but I'm mostly interested to see just him like walking. In the sense that for me, it's just a good opportunity to get a very rich mathematical object. And actually, we are lucky, it's a gift of nature, that most of these models that you get from a physical phenomenon, then they reveal themselves as extremely interesting models, which have connection to actually the rest of mathematics. So for me, this is actually the main motivation. And that's why I will first call myself a mathematician before being called a physicist. Okay, I wanted to advertise a few talks here, just because, just to promise that it's not an isolated opinion. Everybody wants to do that. So Remenick, for instance, is going to talk about this interface growth model. Laure Saint-Raymond is going to make this picture that, like that, doesn't look so great. It's going to move. So as soon as things move, usually it's much more exciting. So I recommend her talk, and Thierry Bodino is also going to talk about related things. And for random matrices, Alice Guillonnet in her plenary talk will also be telling you much more things about these things and in a much better way than me. So, okay, I hope I gave you an idea of how you cook up a mathematical model and that this is something very general. Now let's dive into the second part of the talk, which is what do we want to ask on this mathematical model. And the first thing that you may be interested in is to understand if there is what we call a phase transition. So do you see in your model exactly what you see in nature? In the sense, in nature you see that there is a critical parameter above which, so a critical temperature, above which you are not a magnet, meaning that your spontaneous magnetization is 0, and below which you are a magnet in the sense that it's strictly positive. And here, just for your culture, this is called a ferromagnetic phase, and here the behavior of your system is called paramagnetic. So do you have that, and can you get information on this critical temperature? Okay. So let's go back to the roots and tell you a little bit about the history of this model. So the Ising model was introduced 100 years ago, not by Ising, but by Lenz, his PhD advisor. And what Ising did is that he proved that if you look at the linear chain, so you are working on Z, okay, in dimension 1, then the critical temperature is 0, meaning that you are always a paramagnet. You are never a ferromagnet. And Ernst Ising put it much better than me. He said, I discussed the result of my paper with Professor Lenz and with Pauli, and there was some disappointment that the linear model did not show the expected ferromagnetic properties. And I must say, he's putting it better than me, because disappointment, I would have said that this was more of a huge catastrophe than a disappointment, because, that just means that the model is a catastrophic model for the actual, there is no magnet for this model, if you follow this lead. And so it was actually so disappointing that Ernst Ising just left academia, unfortunately for all of us. He became a teacher, and he realized only much later that actually his model became one of the most famous models of statistical physics and mathematical physics as a whole. So, second thing that probably didn't help either is that you are not without knowing that at this time, in the 2030s, it was the golden age of quantum physics. And the thing is that actually Heisenberg, from the Heisenberg uncertainty principle, cooked up a better model in some sense for ferromagnetism. The Ising model is a model that in some sense is not that good for ferromagnetism, in particular because it relies on a classical interpretation of it. While actually the Heisenberg model, that I will not discuss and not define, but this Heisenberg model, it explains in some sense the magnetization by saying that it comes from the spin angular momentum of the electrons in atoms. So it's really relying on quantum physics. So the fact that the Ising model was not, in some sense, at the same page as the current development in physics at the time was also a catastrophe. Okay? So at this stage, you could decently think, why is this man 100 years ago, 100 years after the introduction, still didn't get that this is a terrible model? The man is me, not... well, because actually after the cons, there are actually pros. And I want to tell you about those, otherwise I will not be speaking to you today. And we owe a lot to Rudolf Peirce, who actually did two things on the model that were absolutely fundamental. The first one is that he said, okay, in one dimension, there is no magnet, but we don't care about one-dimensional magnets. Let's look in higher dimensions. And actually what he found is that whatever the higher dimension, he proved it for 2 and 3, but actually you can extend it to any dimension. In fact, there is a critical temperature which is strictly positive. So there is a phase with a ferromagnetic behavior and a phase with a paramagnetic behavior. So hoof, as we say in French, we are back on track. Magnets exist. But he did a second thing, which is probably even more important, is that he observed that certain modelizations of other physical phenomena are actually also bowing down to the Ising model. And this is something which is extremely important in mathematical physics, is that the same mathematical model actually can explain different phenomena and model different phenomena. And this is one of the powers of mathematics, is that it gives a bridge between different physical phenomena that if you look at them maybe naively, you will not see that there is a connection. But going through mathematics, you end up with the same mathematical model, and it explains different phenomena. So in this case, binary alloys, and more generally, what we call cooperative phenomena. By the way, this cooperative phenomena, that's why the Ising model is, for instance, also used when you look at neural networks in the brain, and how the neurons talk to each other. So of course, in this case, it's not on a regular lattice, but you have connection to other science thanks to this Ising model and this interpretation of it. Okay, so it may be not so clear from the end product, but we are more on this side than this side, okay? There are more pros and cons at this point, but maybe it's not completely clear yet that the Ising model is so interesting. What really made a huge change is actually a chemist, Lars Onsager, Nobel Prize in chemistry, but actually math aficionados. He was loving mathematics and mathematical challenges. And he actually, I think, succeeded in one of the biggest mathematical challenge of mathematical physics in the 20th century, is that what he did is that he took the two-dimensional Ising model, so we are on Z2, and he actually computed explicitly something. So the something, I don't care so much if you understand what it is or not. It's called the free energy. Just think of it that it's kind of the mean energy per unit of volume of a typical magnet. So it's kind of the mean, I was going to repeat exactly the same phrase. I'm not going to do that. But the important thing about this free energy is that it has a closed formula for it, which I just shot here because it's nice. It's a beautiful formula. And so he announced this in 1942 in a conference of the New York Academy of Science. And he wrote the proof in 1944, and it was really a tremendously difficult proof. So I think that what happens with this Onsager revolution is that both, is going to get a result you are going to see that has many very powerful implications. But in addition, he really showed that inside a mathematical model that can look pretty simple, you can find extremely rich mathematics. And that, I think, for us, 60 or 70 years ago, it's a very important thing to keep in mind. Actually, the proof was simplified and maybe put in a much better, let's say, framework by Brouillard, Kaufman, together with Onsager in 1949. And in particular, since then, you have many different approaches based on combinatorics, algebra, analysis that lead to the same result. And just to tell you how many there are, there is even a paper by Baxter and Enting in 1978 saying that this is the 399th solution of the Ising model. And it didn't stop the count since then. There were others. I think it's a slight exaggeration, but, well, I like it nonetheless. So many different approaches leading to the same result, a very delicate result. But for now, you can think, okay, how do I relate this free energy to actually your story? Because you were talking about, spontaneous magnetization. The key player was not this free energy. What is the connection? And the connection was made, conjecture by Onsager, but proved by Chen-Ning Yang, who at the time was a very young physicist that you probably all know became one of the most influential physicists of the 20th century. It's Young Mills, Lee Young, Young Baxter. If I keep the list, I think any mathematician will find at least one thing related to Young, so one of the most influential physicists. And in his youth, he used to do Ising model, you see. And he proved that the spontaneous magnetization has exactly this formula, a closed formula. You can compute it. And when you look at this quantity, you realize that there is a plus here, okay? So you realize that it's strictly positive when t is smaller than this value, and it's 0 when t is larger than this value. So this is exact formula for the critical point of the Ising model in 2 dimensions. You can really compute everything. And this work is actually strongly based on the observation, the breakthrough of Onsager and Kaufman. Okay? So it's a continuation of this. I could give you a full talk on this. I could give you a full set of lectures, but there are many other people who want to talk during this ICM, I was told, so I will keep to my hour. But one thing I want you to realize and to keep in mind, so I'm going to put it huge, is that it's on the square lattice. This is a square lattice. And also, it's based on some magic word called integrability. There is an integrability property of the 2-dimensional Ising model. Okay? But if you believe in that, then you can do everything you want. Okay. Well, you survived the second part of the talk. Very good. Let's go to the third. So in the third, what do I want to do now? I know that there is... oh, my timer just stopped. Does it mean that I get free time? No, huh? Right. Okay, so the third part of the talk is we are going to keep zooming somehow on our understanding of the Ising model. We defined it, that was level 0 of understanding. We prove, we mentioned that there exists a phase transition. This is level 1. Let's go to level 2. And when you look at phase transition, there are tons of phase transition in nature. They come in 2 kinds. The first kind is actually what you teach your kid just to avoid that it hurts himself or herself, is that, for instance, if you take water and you go below 0 temperature, something drastic happens is that the volume of the water changes discontinuously at 0 degrees, right? And you may have, a bottle that explodes where you don't want it to explode. Usually you don't want things to explode. So there is a discontinuous phase transition. So here I did the mathematician in the sense that I wanted to give you an explanation of a concept, and I explained what is not this concept. So actually what I will be interested is in the continuous phase transition, where there is no discontinuity. And it's exactly the type of phase transition that magnetism is. If you look at a magnet, and if you look back at the experiment of Curie, this is actually extracted from one of his writings, and you measure the spontaneous magnetization of real magnets, what you get is that it's continuous. It's continuous at the critical point. So there is a discontinuity in the sense in the phase transition that there is a difference between ferromagnet and paramagnet, but when you measure the strength of the magnet, it's going to get weaker and weaker when you reach 0. Actually, you saw it in the video because at some point, the key changes, the weight of the key starts to be too strong for the actual magnet because it goes slowly to 0 before it reaches, it stops to be a magnet. And in fact, if you look at, oh, that's not what I wanted to do. So we rediscover slowly this is the default of this system. But yeah, if you look at dimension 2 and you plug the spontaneous magnetization, you exactly see that it's continuous. There is no problem there. But there, in 2 dimensions, you are really using in a very strong way that you have an exact formula for the spontaneous magnetization. And, well, we like 2 dimensions. Obviously, I love 2 dimensions, but, clearly magnets are 3-dimensional objects. So what happened in 3D? I think we all agree this is a natural question at this point. Well, what happens in 3D is that you don't have integrability. Even physicists agree with you, so this is usually a good sign. They don't even believe that you can compute, or at least it's completely out of reach of physics, so definitely out of reach of what we can do. They don't believe that you have a closed formula for the free energy or for the spontaneous magnetization. It's not, they don't even believe there is a closed formula for the critical parameter. So we are going to try to prove something on the behavior of the magnetization, not knowing where the critical point is. Right? This is something maybe important to keep in mind. But nonetheless, you can still prove that the spontaneous magnetization at the critical point that you don't know, but you can define it implicitly, and you can prove that at this point, the spontaneous magnetization is 0. And as soon as you have that, in fact, it automatically gives you that the phase transition is continuous. It's not difficult to get it from there. So you really need to understand what happens at the critical point to be able to say what happens, how m star of t behaves when t approaches tc. This is a result that we got with two collaborators, and they are also among my closest collaborators, so Michael Eisenman and Vladas Sidoravicius. Vladas actually left us way too early a few years ago, and I'm sure he would have been extremely happy to be here with us, so I have a small thought for him. And so you get that the phase transition is continuous. And at this point, I was told that any good talk should include a proof. So it's not a good talk, so it's just going to be an idea of a proof. But I'm still going to try to give you just a glimpse at how we do it, because I think it illustrates very well one of the things I like in my area of math. So what's the idea? Well, first, we introduce another key player that up to now I kind of have hidden from you, which is called the spin-spin correlation. So the spin-spin correlation is kind of a measurement of how much the small dipoles in your system lag to align. Okay? So what do I mean by that? I'm just going to take the average against the measure here. It's either the plus or the one without boundary condition, what we call the free. So the mu plus or mu free of sigma 0, sigma x, which I gave you the formula here, but it's just the average against your measure. It's always positive, in fact, and you want to see whether it's really positive in the sense that there is some correlation between the two systems, or if the correlation tends to 0 when you take points that are farther and farther away. By the way, here it was defined on lambda. You can, again, take the limit when you take a larger and larger system. Why do you want to do that? Because typically we are going to look at large scales. We are going to look at 0 and x that are very far from each other. Okay? Again, because we are interested in the infinite volume limit. So when you do that, you realize two things. The first one is that whatever the temperature, when I look at the correlation between the spin at 0 and the spin at x, in fact, it converges when x goes to infinity to the mean of each one of the players, so sigma 0 and the mean of sigma x squared. Why? It's very natural, because you expect that the two spins are going to become more and more independent, so then when you look at the correlation, it's just going to converge to the mean of each one of them, the product of the mean. Up to now, it's not very difficult to prove that. And in fact, there is a second kind of miracle, is that at TC, you can prove that the correlation tends to 0 via what we call the infrared band. I don't want to be telling you what this is, but you can prove without too much trouble that the spin-spin correlation tends to 0. Once you have done that, you feel, well, very good. Then the magnetization at TC is 0, and this was not a result that they should have awarded the Fields Medal for, clearly. But you see, there is a but. What's the catch? The catch is that here there is plus, and here there is no plus. And we are mathematicians, we know very well that if we don't put the same thing, is that there is something catchy there. And the catchy thing is that, in fact, it's not clear at all that free and plus are equivalent. And in fact, that's the whole difficulty. Can one prove that taking the correlation with plus is equivalent to taking the correlation with free? That's the whole difficulty of the proof. It doesn't seem like a huge one, but it's actually exactly equivalent to the original problem in some sense. Up to now, I just, reformulated the problem, but I didn't tell you anything smart yet. Well, I'm not saying I will say something smart, but definitely what I said is true. Yet, okay. So let's make a small detour, because we are in the middle of a proof, so we need oxygen for the brain. A detour to percolation theory, which is my real love. This is the one I love. So what is percolation theory? It's a theory where you sample a random subgraph omega of a given graph. Okay, so imagine you take the square lattice or a piece of the square lattice, and you sample, for instance, this red graph. So the red edges are edges of omega, and the gray edges are edges of lambda, but which are not edges of omega. Okay? And let me give you the simplest example just to give you an illustration. For instance, I need to tell you how I take the thing at random. So what you can do is you can take, for each edge, you take it with probability p, you put it in red with probability p, and in gray with probability 1 minus p. And you do this independently for all the edges. It gives me a random graph, and then what I really want to be understanding is the connectivity properties of this graph. Maybe you don't find it interesting, but at least it gives you a nice picture, which is always nice. So here is a picture at 2 different values of p. Here it's for p smaller than what we will call the critical parameter, and here it's for p larger than the critical parameter. So what do I mean by that? In the definition here, there are no colors. Here there are colors. So what are these colors? It's just the connected components of my graph. I color in different colors the different connected components. And what you see very well here is that all the connected components are small. And in fact, if I would look at an infinite system, what I would see is only finite connected components. They are all small. On the other hand, here you see that at least in my box, there is a huge connected component, the red one, where basically, you know, almost every point in some sense in these systems are connected to each other. They are all in the red area. And if I would go to infinite volume, what would I see? I would actually see one unique infinite connected component, like a huge sea with small islands in it. Okay? So that's a phase transition in percolation. A phase transition between the existence of an infinite connected component and the absence of an infinite connected component, almost surely, because I need to be careful that, you know, probabilists don't decide I'm a traitor. And okay, and just to tell you a little bit what's the motivation between this percolation theory, it's a clear model for porosity of a medium. Whether, you know, a liquid or a gas goes through a porous medium. You just imagine your stuff as a random maze in some sense. So it was actually a good opportunity. This model was defined by Broadbent and Hammersley in 1957, but Mendes Ulamara, one of my PhD students, noticed, I think, what is a very cool story, that Rosalind Franklin, the same as the one for helicoidal structure of DNA, actually worked during the war on an experiment where she was taking coal, and she was looking at whether certain gas, depending on the size of the atoms in the gas, were percolating through the coal or not. And she was even studying, depending on the temperature of the coal, whether that was true or not. To me, it sounds like, maybe not the first, obviously, experiment, but clearly an experiment that predates the introduction of percolation. So I thought it was a very good thing to be reminding about this great scientist and somehow her contribution to percolation theory, even though she didn't know about the model yet. Okay, so why percolation? Why did I tell you about this porosity? Why I was in the middle of a proof on something about magnetism? What's the connection? Well, the connection is that often in my life, at least maybe not yours, but in my life, percolation just saves the day. In the sense that what you can do is that you can reinterpret the correlation in the Ising model between the small dipoles in terms of connectivity properties of a percolation model. Not Bernoulli percolation, this would be too simple, a much more complicated percolation model, but you can rephrase the first problem into the second one, like a translation of the problem. And just to give you exactly what I mean, so this, by the way, this percolation model is called random current representation. And if I look at the correlation between the spin at 0 and the spin at x, it's equal to the probabilities that 0 is connected to x in my random graph for a certain percolation model again, which is not the Bernoulli percolation. It's a complicated percolation model, but it's a model of random graph. Okay? So why is it good? At this stage, it doesn't bring you much information. But in fact, you can even rephrase the difference between the spin-spin correlation for plus and for free boundary condition. And what you see is that the difference is actually written again in terms of drawing, if you want, a property of random graph. Here in this case is the probability that 0 and x are connected to infinity by a path. So why is it good? Because exactly like for Bernoulli percolation, remember the picture for P larger than PC, there was a unique infinite connected component. Well, in this very complicated percolation model, not Bernoulli again, it's still true that when there is an infinite connected component, it's unique. But then if 0 and x are connected to infinity, then they must be connected together, because there is a unique infinite connected component. So then you immediately get that this is smaller than this plus something smaller than this, because if I have the red here, I'm in this case. So what I get immediately is that this is smaller than this. But remember that this is tending to 0, and this is tending to the magnetization squared. Voila. Okay? So why did I want it? Of course, I'm hiding tons of things. Again, I'm allowed to cheat you, so I will use this. But what I wanted to illustrate here is that the connection to this percolation model, so two completely different physical phenomena, give rise to two completely different mathematical models, but those are connected actually by a very deep link. And if you use this link, then you get just a few drawings and you get your proof. This actually percolation interpretation is a very strong tool, and it's used quite a lot, at least in my research. But I wanted to give you at least one striking example of that. Okay, second recap. So you survive the third part of the talk. So the phase transition of the Ising model is continuous, exactly like the physical phenomena underlying it. So that's very good. In 2 dimensions, you can solve that just by using integrability. I say just, but this is actually a difficult computation, but you have integrability that gives you exact formulas. And in higher dimension, well, you need to do something much smarter. No, that's new, I meant new. So you need to use a link to percolation theory. So it's much more less direct. You don't have an exact formula at your disposal. It would be good, but you don't. And just I don't resist the opportunity to give you a few pictures. I'm not responsible for any of these pictures. I have zero ability with computers, so none of them are due to me. So this is a model of percolation again. You just sample, in some sense, your random set in a different way. Here you throw balls. It's called Boolean percolation. You can look at percolation models that are dependent. This is, in particular, the case of the Fortuyn-Castellan percolation or random cluster model. It was mentioned yesterday in connection to the Potts model in the Laudet show of Martin. And you can even play other games. Think, OK, I take a random function, and I look at where it's larger than a certain parameter. For instance, here, it's it's random spherical harmonics, and I look at where it's larger than 0. It gives me nodal lines as the boundaries, and I can study the connectivity of these things. You can really play many games and get many different percolation models. There is a whole zoo of percolation models. So if you want to join and have fun with us, we will find you a percolation model to play with. There is no problem. OK, very good. So this was end of third part. Let me dive into the last part of the talk, because I see that some people start to be worried that this is going to be a very long hour. So I zoom yet one more step. So now I know it's a continuous phase transition, and I want to just illustrate one of the wonders of our area of mathematics, of mathematical physics, is that when you look at continuous phase transition, there is something marvelous happening. That's what we call emergent laws. Emergence is a notion that comes more from philosophy, but here it just means that if you tune perfectly your parameter, typically if you look exactly at the critical point, and if you look, for instance, at large-scale properties, then you get new properties that are completely absent from the discrete model. When you look at your Ising model, you don't see that, but if you tune these things properly, you have these new marvelous properties that emerge. And I want just to give you a hint of this very interesting phenomenon, which is one of the fascinating phenomena in mathematical physics, both on the physics and mathematical side, by the way. And I want to give it to you through an example. So I'm going to come back to my second key players, the spin-spin correlations, what is measuring the alignment between spins. But I'm going to look more generally, I look at the correlation between two spins. I could look at a collection of spins and try to see how they are correlated. In fact, this is very interesting from the point of view of physics to generalize to two endpoints. So I look, for instance, at the correlations between two end spins. So you have points in the plane, in your graph, and you look at the correlations. And I would like to understand what happens when it's at criticality. Okay? And what happens is that you get emergent laws, as I said, and in the case of dimension 4, which will be my example, I can tell you, for instance, one emergent law that we get, is that we get what we call Gaussianity. So what do I mean by that? I mean that if I look at dimension 4 and I look at the critical temperature, if I look at the two endpoint correlations, the correlation between two endpoints, I can in fact express it in terms of two-point correlations through a formula which is more and more true when I look at distances that are farther and farther away. So the limit when L tends to infinity is going to be an equality. And by the way, if I would get an equality here, I would get something which is called the Wick law. And it's a characteristic of Gaussian processes, which is a very classical and big class of processes. So what I'm saying is that if I look at the Ising model, it's not true that it's Gaussian at all. It's not a Gaussian process. But when I look at larger and larger distances and I'm at the critical point, I get something which is more and more Gaussian. And in fact, if I take really the limit, there is a way of taking the limit, I get a Gaussian process in the limit. This is not at all true in the discrete. It emerges when I do this characteristic. Okay, by the way, for dimension larger than 4, this was actually known from the 80s, before I was born, by Eisenman and Fröhlich. And the rate here in the convergence was actually like a power, of L. It was converging polynomially fast to 1. For d equal 4, actually it's a logarithm, a power of the logarithm that emerges. It's because we are at what we call the critical dimension. So there is something more subtle happening there, and this is why it actually took more than, let's say 40 years to get to this result. Let me just mention, I'm just going to flash it, that actually this result is important from the point of view of field theory, because there is a close cousin of the Ising model called the 5-4 lattice model, and that this can be used to construct quantum field theories. And this result is basically reinterpreted as the fact that what you try to construct from the 5-4, from this cousin of the Ising model, is always going to be what we call a trivial field theory, a field theory that describes particles that don't interact, which fortunately for all of us, particles do interact usually. So this is why it's not, if you want to be constructing non-trivial quantum field theory, you need to do something more subtle than taking the Ising model. So in some sense, it's a no-go theorem from the point of view of quantum field theory. But notice that it's a very positive theorem from the point of view of the statistical physicist, because what it tells me is that I only need to be studying the two-point function if I want to understand the whole field, the whole correlations. So this is very positive. It's good news. So now, how do I do, and this is what I'm going to finish in the last 5 minutes, how do I do to determine this two-point correlation when I look at correlation of 2 points? Well, first thing, I'm going to tell you a bedtime story for for kids of physicists. The physicists like to call this story at night, and I understand why. I'm not a physicist, but I will tell this story at night to my daughter. So anyway, what you do is that the story is the following. Leo Kadanoff came with this absolutely fantastic idea that if you start from a lattice and you cut it into blocks, imagine like 3 by 3 blocks, but you could imagine something more complicated. What he suggests is that you could replace the spins in each block by a spin which is just the majority of the block. So for instance, in the first block, there are more up than down, so I just replace it by a big up, and I do the same here, it's a big down, and I do the same for all the blocks. I do the same for all the blocks. Yeah, okay, that works, very good. So you get a new assignment of up and down. Then, second step, you just rescale. And you end up with something that looks very much like before, right? Of course, it's just a drawing, but the idea of Leo Kadanoff is that Well, what you end up with is basically an Ising model. It just maybe the parameters, for instance, the temperature changed. And by using this very simple observation that when you rescale, you get back to the same model, but with a different parameter, he was able to, you just iterate, and what you should end up with is a fixed point of a certain dynamics, which is this rescaling operation. So, very good. You should converge to a fixed point. So then, of course, somebody is disagreeing, or not really disagreeing. It's a quote that I learned from Roland Bauer-Schmidt, and I love this quote. It's called In Short, so it's Kenneth Wilson, Nobel Prize in Physics, that says that, in short, the Kadanoff block picture, although absurd, will be the basis for generalization which are not absurd. I love this quote because I think, I disagree with the Nobel Prize, which is always good. I think it's almost perfect, except I would say naive here. It's also, this is true that thinking that when you rescale, you are going to end up again with an Ising model, just a parameter change, it's a little bit naive. But, like every naive idea, it's actually a bright idea. It's a very, very smart idea, because what happened is that Kenneth Wilson, exactly the same person, just took this idea and transformed it into a breakthrough, into maybe what is the most, one of the biggest advances in theoretical physics. What he said is like, okay, it's maybe not the same model, that's true. But what I think is that this rescaling map, or actually they should be, when I just rescale a system, I should understand that as just a rescaling map on the space of all models. Maybe I don't end up with the Ising model in one step, but I will end up with another model. And if I keep doing this rescaling map on these models, I should still end up with a fixed point of these rescaling maps. So he really took this idea, which was super beautiful, and just turned it into something more powerful. And I think we can all relate that this is something you do all day long in mathematics. You start by something naive, and you just, improve on it to get to something very deep. And that's what these two fantastic physicists did on this thing. So you rescale, and what happened is that then, when you rescale, then the limit, by definition, should be, because it's a fixed point, invariant under all this rescaling, so it should be scale invariant. So if you start from the Ising model and you rescale at criticality, you should end up with an emergent symmetries again, which is a scale invariance. So this is very good, because it tells me already something on the two-point function. But as all good things, they come with even better things, which is that if you assume that the fixed point of this renormalization of this operation, so you have a dynamical system in some sense, if you assume that the fixed point is unique, then if you start from a rotated or a translated version of my lattice and you iterate, you should also end up with a fixed point, so you should end up with the same object. And that tells you that you should have, in fact, even rotation and translation invariant, two other symmetries. So you have three symmetries, and if you look at this, it tells you that your two-point function necessarily looks like constant over L2 norm to some power. So you pin down, in some sense, the two-point function. There are very few degrees of liberty in what it could be. It should be like that. And in fact, when you merge it to Gaussianity, then the two things together, it allows you to describe, that's not in the right order, sorry. So what happens? Yeah. You should definitely, you can describe the whole limit of your Ising model, describe it in full detail if you want at criticality, and you should end up with what we call the Gaussian free field. So again, all these emergent properties together give you all the information you want on the system somehow. Of course, you need to prove the emergent properties, so Gaussianity is proved, that was a theorem. Emergent symmetries, we are on the way, but, well, give me a few minutes. I have still 3 minutes. This is good because I have 10 slides. No, I'm kidding. Don't worry. A last thing is that if you start from another lattice, by the way, if you iterate, well, you end up to the same fixed point. So this is something I wanted to mention, is that you should have universality in the sense that if you start from different Ising model, you always end up to the same limit. And this is something very reassuring for somebody who wants to understand a physical phenomenon, because if the discretization is giving you something completely different, then probably you are not describing what happens in nature. But if your discretization is not that important and that you always get up with the same thing, then it's very reassuring. So I don't have 10 last slide, but I have 2, but they are very short. So third recap and moral to the story, at criticality and large distances, emergent laws, that it can, this I think I justify this with symmetries, for instance, or Gaussianity. And in fact, I want you to remember that understanding the Ising model in parallel to percolation is very fruitful. In fact, there again, the link to percolation is fundamental to get the Gaussianity. So again, you use percolation to help you for the Ising model. And I want just, if you think that proving all these things seems maybe difficult in general, I want to give you two super successful stories. The first one is the story of random matrices that you will hear more in this ICM and that you heard a lot in the previous ICM, where many of things are understood, even universality. And if you want an exercise, you can think of the central limit theorem as being a perfect example. You start from random walk, and you see emergent laws, like you see Brownian motion appearing, which is scale invariant, and so on. You see universality. If you start from different random walks, you end up always to Brownian motion. So this is a very good illustration of a place where that works. And the last slide is about what is next. So you want to understand 3D, obviously, because this is, I didn't tell you about it. I told you 2D and 4D. You want to understand these universalities that I mentioned. And you want to understand other models and renormalization, meaning you want to make physicists happy and change this fairy tale, which is renormalization theory, into a mathematical theory. And this, I think, will be actually mathematics for not even me, but probably the next generation. Thank you very much for your attention.
Thank you very much for a beautiful lecture. Are there any questions? Yes, Carlos. Microphone.
Is it difficult to show the uniqueness of the fixed point?
Yeah, I mean, as mathematicians, we actually know many dynamical systems that don't have a unique fixed point, and that's exactly the limit of this approach, is that it's a good, fairy tale, but at the end, you need to really pin down exactly what happens, and you need to prove that there is a unique fixed point. In fact, there are a few, by the way, talks during this ICM that are related to renormalization, where they actually start close to a fixed point. So even there, they don't prove that there is a unique fixed point. They start close to one, and they prove that it converges, and it's already like fantastic achievements of mathematics. But in this context, we don't know how to prove uniqueness, and in fact, it's not always true. Yeah.
Nalini? Oh, just behind you.
Thank you. So I'm familiar with the 2D Ising model, but not so familiar with the higher dimensions. And I wondered, does the higher dimension give you more freedom to, for example, have more than one critical temperature? Is it possible that you could have different critical temperatures? That's one part of my question. And the other one is, in the 2D case, when you take the critical limit, the scaling limit of the two-point correlation functions, you get functions that satisfy ODEs.
Yes.
Are there any similar results here?
Okay, so there are two questions. The first one, so indeed, you could imagine to have different critical points. First, the spontaneous magnetization is decreasing. This is not something difficult to prove. So if you stick to spontaneous magnetization, you will never get more than one critical point. But you can look at different properties. For instance, you could look like now, if I look above the critical temperature, the spin-spin correlation, in fact, they tend to 0. How fast do they tend to 0? And you could imagine that there is a range where it's polynomial and a range where it's like exponential, for instance. But you can actually prove that all these phase transitions, there are many others that you can imagine, they all happen at the same point. Yes. For your second question about the two-point correlation in Z2, so indeed there, when you take large-scale behavior, you get ODEs. In higher dimension, we don't actually know how to do. You see, in 2D, you even get conformal invariance if you look at things correctly, which is an even stronger invariance than just rotation, scale, and translation. But even in 3D, for instance, there is a whole theory of what we call conformal bootstrap in physics that is exactly trying to extract as much information from these symmetries. Because they don't have nice ODEs like in 2D. They don't exactly, I mean, it's not strong enough in some sense to really pinpoint what is the behavior of the spin-spin correlation. So it's a tremendously hard question to understand that in 3D, for instance. Yeah.
Any other questions? Okay, so let's thank Hugo again.
I think.
Yes, like exactly like when changing the indeed, it's very universal. You should get the same result. For instance, if you look at when you do finite range, before finite range, for instance, when you add a correlation with the next universe, then integrability to be fixed. Yeah, so that's why I don't think because it's a very sense of expectation and it's very what is beautiful is
density of the material.
yes, I mean, whatever, like these things are the same thing at different density, I think.
Different case.
Then, I mean, of course, these materials have natural density.
Yeah. So, I mean, if we're going to calculus, first you isolate your system and thought that the material is the same, then you're going to solve the system.
Yeah, that's not a model. Here you are talking about the physical system, right?
Yeah.
I mean, the mathematical modelization of the system, whatever the material you are looking at.
No, I mean, you think the material,
okay, I need to think about your question and answer the others.
So I come from Mathematicians. We've just actually if you're not, that's fine. You can basically essentially model meters, 2D ICM. You know, so I mean, you can set up the perspective so that and so I was able to show it's just this thing where you like move the parameters because you want to make your network smaller and sometimes I think small meters. And I was able to show that like the ruling process responds to like an RG process as well. And so we are trying to sort of extend that thinking to like because the fully connected model is just like one kind of others. And so some of them then we can think of as a 3D ICM. You know, and so I mean yeah, like it's a little bit of
well, I think in your case you do not care so much about the actual tools, but also not just the
Exactly.
So there you can go to the physics literature because there is this conformal bootstrap theory that describes the critical behavior of the switch, which is not a full theory, but it's a very powerful one.
So you think it's like effectively powerful?
Yeah, I mean, it beats even the Carlo and things like that. It's quite
Thanks.
Yeah, this is...
Yeah. So, I mean, isolating, I mean,
Okay. Which is gauge theory, gauge model, which is
No, still not working?
Yes.
Is it working now? Yeah. Okay, please take your seats. We're going to start with the last lecture. So we wait a minute or two, yeah. Okay, so please take your seats. We're going to start now. It is a real pleasure to introduce our last Fields Medal talk by Marina Wiasowska from EPFL, the École Polytechnique Fédérale de Lausanne. Henry Cohn couldn't be here in person, but he sent me these remarks. Our next Fields Medalist talk will be given by Marina Wiasowska, who was awarded a medal for her solution of the sphere packing problem in 8 dimensions, as well as related extremal and interpolation problems in Fourier analysis. She holds a chair in number theory at the École Polytechnique Fédérale de Lausanne, and her areas of expertise include modular forms, discrete geometry, and Fourier analysis. Let me say a few words about my experience collaborating with Marina. What I found most impressive about her is the clarity of her perspective. She has a gift for identifying and formulating exactly the right mathematics for a given topic. Sometimes it seems so clear in hindsight that it feels like someone should have done it long ago, but nobody did. Other times it seems like a miracle that Marina could do it at all. Either way, she has a bold vision and a unique perspective on mathematics. Today, she'll tell us about her work on radial Fourier interpolation and other related topics. This work began with conjectures that seemed implausibly strong to me, but they turned out to be true, and as with all of her work, they lead to fascinating mathematics. Please welcome Marina Wiasowska.
So thank you very much. It's a big honor for me to speak here today. So today I will speak about magic functions. So they were already introduced by Henry Cohn yesterday, and I hope you are excited to know what they are. So let me explain, and maybe as a warning I would say that this word is not a mathematical term. It's a very unclear, it's just a very, very vague idea. And so here what it means. So with one of my taste as a mathematics, I do like solving geometric problems, and maybe my favorite type of problems are problems for optimization. So we are looking at some geometric situation, and there are many questions we could ask. So what is a typical situation? What is a random situation? But I want to know what is the best or what is the worst, what can happen in this case. And so here it's a very incomplete menu of questions we could look at. We have the whole big family of packing problems, and they have their cousins covering problems. And yeah, we also can ask all kinds of questions, for example, looking for shortest geodesic or looking for geometric spaces with certain Laplace spectra. for example, with big gaps or with small gaps. And so, of course, this menu is very big, and we do not hope to find any universal solution for all this type of problems. And so we have to choose something. So the problem I've chosen for us for today is the packing problem. And so let me frame it a bit more generally. Yesterday, Henry spoke about usual packing problem in Euclidean space. But we can look at a slight generalization of it. So we can just fix some metric space. And as long as we have a metric space, then we know what is a ball in this metric space. It's just the set of points within a given distance from its center. And now, so the natural question is how many balls of given radius can be packed inside of this metric space. And so here, if our space is compact, then it's always a finite number. And here we stop our work on posing the question is done. And if we are in some more complicated space, like an Euclidean space, we have to work a bit more. We have to formulate exactly what does it mean, how many. For example, in Euclidean space, it's very natural to say what would be the density of this of the packing, and I don't give an exact definition here. Maybe one thing I should say that, for example, packing in Euclidean space, it's a very well-behaved problem, and it's not that difficult to pose it rigorously. And actually, whatever we attempt to do, it will always be a good formulation, and almost all these formulations have the same answer. And so there are also, because I did consider metric space, so I don't want looking only at the Euclidean space. I also want to add more problems so that we can see some similarities. And so here, one closely related class of problems are the error-correcting codes, or even independence, searching for independence number of a graph. It can be seen essentially as a packing problem. And so here's another class of problems I will consider today. They are so-called energy minimization. So now, instead of, so it's an averaged version of a packing problem, if you wish. So now we consider a set of points in our metric space, and we would like to, for each point configuration, we would like to define its energy. And in here, we will assume that the energy depends, it's only a sum of energies of pairwise interactions between points. And so here for energy profile, we have the energy profile P, and here it can be essentially any function for us. And then again, our game would be to find a minimum of this number among all possible configurations. And if we have a finite number of points, and if, for example, in Euclidean space, it's natural to consider infinite point configurations only with a fixed point density. So here I would have to work a bit more to have a nice definition, because this definition would not work. So what I write here, this formula essentially gives us average energy per point in our configuration. And so you have to work a bit more to define what we mean in Euclidean space, but I hope that the idea is clear to you. And so the problems I have described just now, they are, I would say, highly nonlinear problems. And maybe, as you know, that somehow one of the first subjects we learn in mathematics is linear algebra, and then we all like linear things, and nonlinear things seem to be very difficult. And so here it's one of the very general tricks is when we have a difficult problem, we don't know how to solve it, let's linearize it. And then we might get hope. And so here's in a realm of optimization, there is also a class of problems which are not exactly linear, but they are convex. And so, for example, this is so-called conic optimization. And so it's also, I would say, a class of geometric optimization problems, or it can be viewed this way. And what I've written to you here, it's a typical example. So it's a finite, so it's an optimization over cone in a finite dimensional space. So a typical, sometimes called linear programs. So typical linear program looks like this. So we are fixing a cone C, so convex cone, and then we are considering some linear subspace, and we are fixing a linear functional on this space. And so our question would be, what's the smallest number of this functional on this intersection, on this convex set, which is an intersection of our cone with some hyper, so not a hyper, like a affine subspace. And so one of the nice qualities that this type of problem have, here we have a well-established and well-studied notion of duality. And so it turns out that if you want to solve this linear problem, it's very natural to consider a problem dual to it. And so for each convex cone, we can define its dual cone. It's defined this way. It will be just the set consisting of all vectors which have non-negative inner product with all vectors in our cone. And so here's an example. If we take this to be a cone C, then its dual will look like this. And so we can formulate the dual linear program. And so here, what is convenient about this is that any feasible solution for this dual linear program, it gives us a bound on our initial linear program. And so here we have also very convenient proof technique where we want to prove a statement about optimality of something. And to prove it, we need to present a certificate. So here, certificate, it's an element of this. It's some feasible solution to the dual problem. And so as I've told you, so this, all this works quite nice for convex problems, but our problems are not convex. So we have to do something about this. And so here, we have to introduce some linear spaces and some cones. And so if we have a geometric space, then a very natural linear space related to it to consider is just the space of functions on our original space. And now in this space of functions, and it's also somehow here also we will see that some of the functions, in some sense, they are dual to configurations. So this is where we hope to use our duality ideas. And here we'll introduce this useful cone, which is called the cone of copositive. Cone of copositive functions. So they are all functions. So this time, you remember in all our problems I introduced to you, what was actually important for us is not the 2 points, exactly the points on our configuration, but rather distance between our points. And so this is already first simplification. Also, we don't have to consider functions on all space. We're only considering functions on a support of the metrics on our metric space, and it makes our life easier. And so we would say that a function is copositive if for any finite subset X of our metric space, this sum is non-negative. And so now we could reformulate the geometric optimization problems I described to you above in terms of this cone. So if we would have access to this cone, then our problems would be very, very easy to solve. And so, okay, but here there is some bad news, is that this cone is actually very complicated, and even for other simple metric spaces, we don't have access to it. And so we have found the maybe next best thing, or another cone of functions, so-called cone of positive definite functions. And so here, these are also all the functions defined on the support of our metric, taking complex values. And here we are changing our conditions, so we are requiring more for our functions. Now, not only the sum of f at all pairs of points should be non-negative, but also if we introduce any complex weights, then this sum still should be positive. So it means that, of course, positive definite functions, they are a subset of copositive functions. And so in some sense, one could think of this con as an analog of con of positive definite matrices. They're actually very close to each other. And so now a good news is that for many still interesting spaces, this con of positive definite functions is actually simple. It's nice. It's very nice to work with. And so now let me introduce you it's maybe an archetypical theorem, and it actually was used a lot in the literature on optimization in different forms. And so here it looks in the following way. So suppose it's a theorem which gives us a bound on the number of points in R0 code in our metric space. So here we pretend that our space is compact, and so we expect only finite R0 codes. And I recall that an R0 code, it's a subset of our metric space, such that distance between any 2 points in it is at least R0. And the theorem is the following, that suppose there exists a copositive function which satisfies these two inequalities, and then from the existence of this function and the fact that we can prove that it is copositive, we could say that this each R0 code can have at most capital N points. And the proof of this theorem is actually very simple. So what we are doing here, we are just assuming that we have some R0 code, and then from the fact that our function is copositive, we deduce this first inequality. And on the other hand, we also know that our function has to satisfy these two inequalities. And so, on the other hand, we get an inequality like this. So now we have estimated this sum from above and from below. And because these two inequalities should not contradict each other, we arrive at this result. So this seems like a rather simple scheme of proof, and it has been successfully applied to many situations, to Hamming codes, to spherical codes. And here is let me give you one example. So this is, let's consider the Hamming 8-4 code. So it's a linear subspace in the space f2 to the power 8, and it is generated by the rows of this matrix. And so it's a subspace of dimension 4, and therefore it contains 16 elements. And in fact, so you can, maybe it's not that obvious from this presentation, but the minimal distance in Hamming code is 4. And so now we will show that we cannot improve this. Of course, this is a baby example because it's such a small problem. After all, we have finitely many possibilities. We could have just checked all of them, but let's just look at this as a proof of concept that our theorem works and it gives useful results. And so first, I've already told you that the space of copositive functions is actually difficult, and even in this case, it might be not that easy to describe. On the other hand, copositive functions have easy and nice description, and here this nice description comes from the fact that our metric space, it has a lot of structure on it. So first, it has structure of linear space, and then also we have a symmetric group acting on it and preserving a metric in it. And so if we combine all this information, it is actually easy for us to describe all positive definite functions on this space, and they are essentially the convex con of so-called Kravchuk polynomials. And so how we do it, so from the linearity of our space, we can see that flat waves, they satisfy this condition, which is very similar to the condition of being positive definite, and the only thing that fails here, that is this function, it's not a function of distance between points x and y. And so, but here the symmetric group comes to rescue us, because now we have to somehow take the average of this function over the action of symmetric group, and then we will arrive at the Kravchuk polynomials. And so the next step is actually to apply this knowledge to our example. And so we will prove this theorem. So let X be a chord in this Hamming space, two space of dimension 8. Suppose that it's a chord of distance 4, then it cannot have more than 16 points in it. And so to prove this with the theorem I've showed you before, now what suffices to do is just to give you the certificate, to give you this positive definite function f, which would satisfy the conditions of the theorem. And here it's actually very difficult to construct this function, and it equals to this. Because actually the spectrum of our so we can consider this polynomial, and fortunately for us, it's a convex combination of Kravchuk polynomials, and so this finishes our proof. So I've told you a successful story of this method. We had an example, we have a bound, they match perfectly. So now the bad news that this is actually a rare situation. Even in the situation of error-correcting codes in Hamming space, we don't expect this to happen. And actually, we have a handful of codes which are optimal, and their optimality can be proven with this method. And so now what Kohn and Elkis have done, they have adopted same method, as I told you in the first theorem in my slides, to Euclidean space. And so here maybe I should tell you that I'm skipping on the work of many, many people who have actually worked first on these discrete spaces, on compact spaces. There was also work done in Euclidean space, but maybe a bit later I will come back to the history and some historical successes of this method. Before 2003, but in 2003, Henry Kohn and Dam Elkis, they have published this theorem, and so it tells us that suppose that there exists a Schwarz function f, and the Schwarz function satisfies the following conditions. So first, the values of f are non-positive for all points x outside of a ball of radius r0. Second condition is that the Fourier transform of the function is non-negative. And the last condition is that our function is normalized in this way. And so after normalizing our function in this way, we would see that these two conditions, they start competing with each other, because it's difficult for a function to be almost negative except for a small ball, and for its Fourier transform to be positive. However, if you can construct this function for some R0, then we know that each periodic configuration in Euclidean space, which is an R0 code, it will have point density at most 1. And of course, it gives us immediately an estimate on the best possible density of a sphere packing, and that's because if you take this R0 code, and we place a ball of radius r0 divided by 2 into our Euclidean space with center at this point, what we will get would be a sphere packing. And of course, point density of centers is just linearly related to the density of our sphere packing. And so maybe a few more words I want to tell you that, of course, this theorem looks a bit different from the theorem I have shown you before. However, it has the same structural elements. And so this condition here, it's essentially a condition for f to be positive definite. So this is the right definition of positive definite in Euclidean space. And so this condition is the condition, the replacement for the inequalities I showed you. However, Euclidean space, it's non-compact, and so we have to be smart here, and maybe I think actually correctly formulating this condition, this was not an easy task, even though the theorem looks simple. Actually, it has a very short and nice proof. But for coming up with concrete formulation, this was not that easy. And so as I told you, like finding such a function for a small R0 is not that difficult. However, finding an optimal one, it is complicated. And so what Kohn and Elkis have done, they have applied this method in all dimensions from 1 to 36. And in all dimensions, they have constructed some function for some R0. They've done it numerically. And so here, this is I think this plot we have already seen in Henry's talk yesterday. So this is the red line, it's the bound, and blue line, these are so it looks like it's a discrete line, but it's a continuous line, but actually it's not. These are just different densities in different dimensions, just connected by a line to make it better visible. And so you see, always there is some bound, and in 2 points that are somehow maybe these points like 1, 2, we don't really see what happens on my plot, and maybe let's forget about them for a moment. After then, in those dimensions, packing problem is settled. It's not that interesting for us at the moment. But we also see something very interesting happens in dimensions 8 and 24. And we see that here, this linear programming bounds, they came extremely close to the densities of existing packings. And so these numerical results, they are from the paper on 2003. But one can actually, but even in 2003, Kohn and Elkis made a conjecture that this is just, so this bounds should be, so this 1, 0, 0, 1, 16 should be replaced by 1. So if we could find the right function, and same for 24. And over the years, somehow the evidence for this was growing, and in a few years, these 3 zeros, they were replaced by 60 zeros. So we were pretty confident that the function does exist. But what we had to do, we had to give an exact function. But maybe before I come to the function, let me tell you a bit more about these 2 special points. So I think at the moment, I don't have a very good understanding what is so special about these points, but I can represent for you these 2 lattices, the E8 and Leach lattice. And maybe when you see how great they are, you will understand that indeed nothing better can be done. And so let me start with the lattice E8. So the E8 lattice, it's a lattice in 8-dimensional Euclidean space, and up to an isomorphism, it is actually the unique even and unimodular lattice. And here, what I mean when I say that it's even, it means that the Euclidean lengths of all its vectors squared, they are all even integers. And unimodular, it simply means that the co-volume of this lattice is 1. Or in other words, if we take a basis of z basis of this lattice, computes its determinant, it will be equal to 1. And also E8, it's a very famous object in mathematics with lots of connections, very important one. It appears in many different, at first sight, maybe unrelated theories. For example, in the theory of Lie groups. However, unfortunately, in my talk, it will play absolutely no role. So also, it has very beautiful group of symmetries, and again, this will play no role in my talk. But what is maybe closer to my story is that not only E8 itself, it seems like it's a winner of all of many extremal geometry competitions. But even if we take some parts of this lattice, then they are also optimal in many natural senses. So one beautiful result is that the shortest vectors of E8 lattice, and we have 240 shortest vectors, they are the unique, essentially the unique solution of the kissing number problem in dimension 8. So a kissing number problem, I hope you know what it is, and if not, then it's following rather natural geometric question. So we're taking one unit red sphere in d-dimensional space, and we are taking other blue unit spheres, and we want to locate them so that each blue sphere touches the red one, and at the same time, blue spheres don't intersect with each other. And so that this is the famous kissing number problem. And in dimension 3, we know that. So in this picture, we know that in dimension 2, for example, the obvious answer is 6, and it's so obvious that it doesn't even require the proof. In dimension 3, actually, it was a difficult question, but people in the 19th century found a way to resolve it. And now it's resolved in dimension 4, but it's also quite recent result of Oleg Musin. So if I'm not mistaken, then he done it in 2004, so already in this century. And however, dimensions 8 and 24, they were okay, I'm spoiling my own slides. Forget what I told you about 24, but in dimension 8, this problem was solved in 1979, and here actually two proofs came simultaneously. So one was by Vladimir Levenstein and another by Adlishka and Sloan. And so this theorem tells us that this is the unique optimal kissing configuration in dimension 8. And actually the method of the proof, it's also the same method which I showed you in my first theorem today, only adapted to the spheres. And also we can consider a sphere packing, which is associated to the E8 lattice. And so because minimal distance between 2 points in E8 lattice, it is square root of 2. So we can pack our space with balls of radius 1 over square root of 2, with one ball at the center, with a center at each point of E8 lattice. And so we will show you today that this packing, it is actually the unique dense periodic packing in dimension 8. And also this E8 lattice, it has another nice property, which is we call an universal optimality. And it means that E8 lattice, it's a simultaneous solution to a big class of energy minimization problems, which I will specify later in my talk. And so here are the Leech lattice. So Leech lattice, it is maybe even more beautiful than the E8 lattice. And in dimension 24, actually we have 24 different even unimodular lattices, so-called Niemeyer lattices. But Leech lattice is the one which stands out among them, because as an even lattice, the shortest possible distance between points is square root of 2. But this distance is not realized in the Leech lattice. And of course, from this, we can immediately think, okay, so this is probably, it's a hint for us that this is a good candidate for a packing problem. And so the Leech lattice was discovered quite late, already in a second for half of the 20th century. And the discovery of this lattice, it actually came from, so inspiration for mathematicians was, they found it from engineers who worked on error-correcting codes. And so first the Galley code, error-correcting code was constructed, and then John Leech, he used this construction and wrote down the Leech lattice. And but for now, after the Leech lattice has been discovered, I think it also found its place in mathematics, and many beautiful relations between Leech lattice and other areas of mathematics were found. For example, it has extremely rich group symmetry related to maybe it helped to identify last missing pieces in the classification of finite groups. And so it also related to the big number of other deep problems, but actually for our story, none of this will play a role, so unfortunately. And so in the same problem year, 1979, actually in the same 2 papers, it was also proven that the shortest vectors of Leech lattice, they solve the kissing sphere problem in dimension 24, and this solution is unique. And so maybe one thing I want to tell you that even though kissing sphere problem is solved in dimension 4, we still don't know whether the configuration in dimension 4 is unique. So it's really, there is something we don't know about dimension 4, but we know about dimension 24. And so associated to the Leech lattice, we also have this packing configuration. And so a result which we have proven together with Henry Kohn, Abhinav Kumar, Steven Miller, and Danilo Radchenko is that this pair packing is the densest. And also we have shown that the Leech lattice is a universally optimal lattice. It also satisfies this maybe averaged packing problem. It's also the optimal solution for it. And so this is the theorem which I was able to prove in 2016. I showed that there exists a Schwarz function, Fe8, such that all the conditions of the Kohn-Elkies theorem are satisfied, and they are satisfied with the optimal value of R0, which is square root of 2 in this case. And also together with Henry Kohn, Abhinav Kumar, Steven Miller, and Danilo Radchenko, same year we have found this also a suitable Schwarz function for dimension 24, and it satisfies all the conditions of the theorem, again with the optimal value of R0, which is 2 in dimension 24. And so here maybe now I can explain you the terminology. So we would say that these 2 functions, and I think it was a suggestion of Steven Miller, he suggested to call them the magic functions. And that's because they magically prove a very difficult theorem for us. Because we all know how nasty geometric optimization problems could be and how much work it could be, but here this function does everything for us. And so this is how the function looks like. So this is the 8-dimensional function. So now I will tell you about a bit of how to find this magic function. So first I show you its portrait. But please remember important features in here. I will come back to it. And then I will also explain you how to derive an explicit formula for this function. And so now, maybe one question is how to find these magic functions. And so as Henry told us yesterday, this was a somehow open question for quite a long time. So here are some things which would help us. So first, we can assume that these 2 functions are radial. It means that the value of a function depends on, or at some point, depends only on the distance from this point to the origin. And so why can we assume that? Because the theorem, all the conditions in the theorem of Kohn and Elkies, they are invariant with respect to rotation around the origin. And so if we are able to find one Schwarz function which satisfies it, then all its rotations will also satisfy the condition. So we could, for example, take an average, and this would be a radial function. And of course, it's much easier to search or to work with functions, radial functions, which are essentially one-dimensional. And so this way you can also see that actually, you already seen it in this picture when I told you the portrait of the function. This is obviously a portrait of one-dimensional functions and not function of 8 variables. And so here another thing maybe you can, again, see from the plot. It's that the functions here, I've rescaled my function again. So here I choose, because all the lenses in my lattice, they're square roots of even integers. But when I plot my function, I plot it not as a function of the lens, but of the lens squared. And so this is because then my plot looks a bit better. And so you see that the spectrum of our lattice, there are also somehow special points of our function. So we see that our function itself has zeros and even double zeros at these points of the spectrum of the lattice, and same happens for its Fourier transform. And this is not a coincidence. So actually, we can prove this analytically. So if we have a magic function, then it should satisfy this condition. And so one way to see it is through the Poisson summation formula. If we assume that this is a magic function and satisfies all the conditions of Kohn and Elki's theorem, then, of course, this equation is just the Poisson summation formula. And now, from two conditions of Kohn-Elki's theorem, we can estimate this sum as one from above and from below. And therefore, we see that in these inequalities, we actually cannot have any losses, and it's possible only if function vanishes. And so, but now we will see that this information is actually sufficiently to identify our function uniquely in the class of Schwarz functions. And so, but before I explain to you that, so let me just show you the explicit formula. Because in my, so this was maybe some kind of something I kept secret in my first paper, because in my paper, what I have written, I have just written explicit formula. And that formula is actually very constructive. And so here the main technique is the chicken claw contour integration technique. Yes, so here I make this assumption. So I search for my magic function in this particular shape. And from what I've already shown you, this can be explained because I know that my function, it has double zeros, and this sine square is responsible for double zeros. And maybe, okay, I cannot at the moment to explain this integral transform, I actually would have to go deeper into theory, and I still hope I still have time for that. But for now, we can just think, okay, so we are looking for a function as an integral transform, and we all know and love integral transforms. So, and how I guessed it, it's okay. For a moment, I will open some cards later. But anyway, see, this seems like a nice integral transform. It's essentially, this is like a Laplace transform. Many people work with it. It's not a bad transform at all. And also, there is one important thing is that as you remember, that the function, the Fourier transform of f, it does have all these double zeros. But the function f itself, it has only single zero at r squared equal 2. So maybe I can show it to you here. You see, so this is only a single zero. And so therefore, it means that this integral, actually it cannot, if it was like this, then it would have a double zero, and it's not what we want. So what we assume is that maybe this integral, it converges only when r is big enough. And when r is small, then we get a pole, and yeah. And so this sine square helps us to remove the singularity. And so now we have, let's make this assumption, which maybe is not very motivated for you at the moment, so let's rewrite this sine square in a different way, so as a sum of exponentials, and then we rewrite this one integral as a sum of 3 integrals. And here our mysterious function phi, which we still have to discover, it comes with 3 of its shifts. We are shifting it by +1 and by -1. And this is where the chicken contour comes in. So here we have these 3 contours like this. But now if we make some extra assumptions on our function, we could hope that maybe we can do, because we are searching for phi as a holomorphic function in the upper half plane. And so we hope that if we are lucky enough, we would be able to deform this contour. And so this is where the chicken claw appears. And now we have to observe another thing. So now I can maybe explain you a little bit about this presentation of my function. So why this integral transform? And that's because if now we want to apply a Fourier transform to because we know that f needs to have double zeros, and the Fourier transform also needs to have double zeros. And so here we have written this complex Gaussian, and Fourier transform, it actually acts, we understand very well how it acts on complex Gaussians. We have a very easy formula for that. And so if we apply Fourier transform to this, of course, this shape of our integral representation, it would change, but it would change it to something rather similar to this formula. And so let's apply it. And so now it's also like this important property. So this is what if we do if we apply Fourier transform just. So again, at this point, we forget about all the convergence issues, just apply it formally. Imagine that we can interchange taking Fourier transform and these integrals. But as Hugo told, we are allowed to do this in a talks of this kind. So now if we make this change of variables, we see that our chicken contour, it looks into something a bit different, but it's also kind of a chicken, like inverse chicken contour. And this is really the key to the proof. So now what we are doing, now we would inverse engineer, and we will search for this function phi, so that after making this change, our function would still have a form like this. And so here are some computations, and maybe I will not go into all of them, but you can trust me that I've done my homework, and I think in a paper written by Henry, he explains it actually very, very well. So this is the Fourier transform, and I do all this computation. So I'm trying to somehow to make my new contour, the integration of our new contour, the same as to the old one. And so in attempt for doing this, I will obtain these conditions for my function phi. So if I want, what I really want, I want my integral at the end to look like this for some function psi. Don't know which one. But if I do want to achieve this, then these are the conditions that I would have to pose on my initial function phi. And here something really nice happens is that actually this system of functional equations, it can be solved explicitly with help of the theory of modular forms. And so here we are lucky, because if we look at all these transformations, so we have these relations between different linear fractional transformations of function phi. And we see that all of these linear functional transformations, they actually generate a discrete group. And this is a very well-known and well-studied discrete group, so they're just the full modular group. It's isomorphic to the group of 2x2 matrices with integer coefficients and determinant 1, and it acts discretely on the upper half plane, and functions which are symmetric with respect to the action, they are called modular forms. And but this functional equation is a bit complicated, so the answer we get for phi here, it's not a classical modular form, but it's what we call it's a certain linear combination of classical modular forms and quasi-modular forms. But that's maybe a technical detail. I will also skip that one. And so now, how to conclude the solution. So now we have an explicit formula for phi, and therefore we also have this very explicit formula for the magic function. And so now really the final step is to verify that it does satisfy the conditions of Kohn-Elkes theorem, and those are explicit inequalities. And so here it's where we actually have to ask computer to help us a little bit and to verify the inequalities. But we have like very nice explicit expression for phi, and we are lucky enough that phi itself, like actually to proving those inequalities, we essentially don't have to work with the integral, but with the expression under integral. And so this finishes the proof of the packing problem. And so now let me, the last part of my talk, let me go a little bit into universal optimality, and I hope it will, that's another optimal property of E8 and Leech lattice, which nicely generalizes this optimal packing property, but it also actually maybe will open you some of my tricks of finding the magic function and where these integral representations, where they actually coming from. And let's formulate, so this is, now we'll look at the energy minimization in Euclidean space. And so I already presented you how the energy minimization problems look in general. But as I told you, we are in Euclidean space, and it's interesting, and Leech lattice, E8 lattice, they consist of infinite number of points, and so simply considering finite sum is not enough. We would have to maybe take some limits in here. So for example, we are taking our points of our lattice inside of some big ball, compute the average energy per particle in this big ball, and then we take limit as r goes to infinity. And this limit might, for different, depending on how bad or good this configuration C is, this limit might exist or not. So here there is a bit of analytic work to be done. But essentially, everything can be worked out because Euclidean space is a nice space. And also, maybe as we are running this competition for having minimal energy, it's probably fair to run it among configurations of equal density. Otherwise, we could have some pathological solutions. For example, configuration, which is essentially, it could happen that our potential favors almost empty configurations when points are extremely, extremely far away from each other. Or it could favor configurations where all points collapse into one, and we don't want that. So we are fixing the density here. And now the Henry Kohn and Abhinav-Kumar, they formulated the following nice property, which they call the universal optimality. And how it works is it's the following. So we would say that a discrete subset with a well-defined density, it's universally optimal if it minimizes P energy for all potentials P, where P it's a completely monotonic function of squared distance. And you might ask, why this condition? So one explanation to this is that all Gaussian interactions for any positive parameter alpha, they are all completely monotonic functions of squared distance. And if we take positive linear combinations of them, or the convex combinations, then we actually will get all completely monotonic functions of squared distance. So that means that, in other words, this configuration C is universally optimal if it's optimal for all Gaussian interactions. And Gaussians, it's a nice class of functions. And then here we can see that packing problem, it's in some sense, it's on the boundary of this class. So if we take alpha, for example, very, very big, then essentially we will get the packing problem. And so the theorem we have proven together with Henry, Abhinav, Steven, Danilo, and myself is that we have shown that E8 lattice and Leach lattice, they are universally optimal. And so here the method we are using, we are again using linear programming. And so linear programming can also be adapted to this energy minimization problem. And this actually was done by Henry Kohn and Abhinav-Kumar in 2007. So they have proven the following theorem, or maybe a proof gave us this proof technique is that if let P be our energy potential, and suppose that we can construct the auxiliary function F, which is, okay, for our purposes, we write here Schwarz functions, but in principle, this condition can be replaced by some easier condition, but because we were able to find the Schwarz function, and I like this space, so I will stay with Schwarz functions. So we could find the Schwarz function F such that it satisfies these two inequalities. So first, okay, so I think there is a typo here, and this inequality actually has to be resolved. So F, it should not exceed P on one hand, and on the other hand, the Fourier transform of F should be non-negative. Then we would say that for every subset in RD with density rho, its P energy can be bounded by this number, which can be read only, it depends only on rho and the function, auxiliary function F. And so now in this case, we also hope to achieve sharp linear programming bounds. And if our sharp linear programming bounds are, and this assumption that the linear programming bound is sharp will tell us something about our potential auxiliary function. And so we suppose that lattice minimizes P energy, because in our case, actually, our candidates for optimal configuration are lattices. And we assume that optimality can be proven by some Schwarz function F. And then again, from the Poisson summation formula, and it's very similar, maybe a bit more technical than what I showed you in the previous slide, but the basic idea is the same, that from Poisson summation formula, we would know that our function f, it actually has to coincide with function p for all points in the lattice, and the Fourier transform should be 0 for all points on the dual lattice. And maybe one important thing is that our lattices, E8 lattice and Leech lattice, they actually self-dual, and lattice is actually equal to the dual lattice. And because in our case, our potential functions are infinitely smooth, we would know that our inequalities, they have to hold to the second order. And so now it turns out that actually this information is sufficient to recover our function uniquely. So what we know about our function f, we know about its values because we take a radial function, and we know its values at the spectrum of our lattice, E8 lattice or Leech lattice, and we have the same information about its Fourier transform. And because we have vanishing up to second order, actually we know also the values of the derivatives of function at the spectrum and the derivatives of function at of a Fourier transform at the spectrum. And it turns out that for actually we could prove this Fourier interpolation formula that this data, so if you have any function, any Schwarz function f, then its value at any point x can be reconstructed from its value at square roots of even integers, the value of its Fourier transform at square roots of even integers, and the square roots of the derivative of f at square roots and derivative of its Fourier transform. So here maybe I'm cheating a little bit, so maybe I would have to tell you is that, of course, when I take derivative, now I look at my radial function as function of one variable, namely the distance, and I take derivative with respect to this distance from the center. And so maybe let me tell you a few words about Fourier interpolation formula. So it's actually the Fourier uniqueness sets are quite well studied in analysis, but the situation when Fourier uniqueness set is discrete was not that well studied before. And so before maybe proving this rather complicated Fourier interpolation formula of second order, first we practiced a little bit together with Daniil Radchenko and proved an analog of this formula for simple roots. So here we take, so we did it only not in d-dimensional space, but only in one-dimensional space. And instead of looking at square roots of even numbers, we took square roots of all integer numbers. And so here to compensate for it, we proved formula not of the second order, but of the first order. So one can argue that this is probably the same amount of information as in the formula before, because we have twice more points, but sampling twice less information. And so then somehow this theorem, it opened maybe a new wave of interest into Fourier interpolation formulas, and more formulas of this type were proven. So first, there is a very interesting paper by Andrei Bondarenko, Danilo Radchenko, and Christian Seib, who showed the Fourier interpolation formula for zeros of L functions, and this is in some sense a generalization of a Weil summation formula for the roots of L functions. And maybe here I also should say that I would like to thank Andrei Bondarenko, because we, even way before this formula was proven and the formula on the previous slide was proven, it was actually we did a discussion with him what led me to believe that such formulas are possible at all. And yeah, so then it's somehow, if you are an analyst in heart and you look at this interpolation formula, which has this very strict algebraic structure, you might be unhappy because this seems like a very analytic property. And so indeed, this was confirmed. So first, Ramos and Sousa, they perturbed our formula a little bit. So they proved that there is an interpolation formula if we took the same roots as here and perturbed them by each root by epsilon n, and where epsilon n actually goes to 0 rather fast. So in this sense, it's an analytic result. And then there is maybe a stronger result by Mikhail Sodin, Alexei Kulikov, and Fyodor Nazarov. So they show, their work in some sense shows that, okay, so this Fourier uniqueness pair, discrete Fourier uniqueness pairs are not that special. And it's only some, there should be a rather mild density condition on points, and then we always have the Fourier uniqueness property. Maybe the Fourier interpolation for property seems rather delicate, but at least Fourier uniqueness, it's okay. It's an analytic property as one might suspect, as things should be. And yes, so now we are ready to, with this information, we are ready to construct our magic functions. And so now suppose that we have our Fourier interpolation formula. And you remember that for our function f, we know its values at square roots of f, values of its Fourier transform. So we can just substitute them into the interpolation formula. So here we assume that f is a magic function, and for some energy potential p. And from the interpolation formula, we know that this actually is the only possible candidate. And so here an and bn is our interpolating basis. And here maybe I also should tell you that if we look at this, what about packing problem? So this is for Gaussian energy minimization. And packing problem is somehow, it's in a limit. And for packing problem, the magic function, it's just this first function b and 0. If you take one of our functions in our interpolating basis, it will be the magic function for the packing problem. And so now in order to prove that E8 lattice and Leach lattice minimize P energy, we also have to prove this inequalities, and then it will give yes, and so for universal optimality, it's only sufficient to look at this particular family of functions P, because all others are the linear, the convex combinations of these functions. And so here now, how can we find magic functions? So what should we do? So maybe this is my almost last slide. So we have this mysterious interpolating basis, and if we know it, then we can solve our problem. And as my PhD advisor Don Zagier always tell me, if you have an interesting sequence of numbers form a generating function, and it will give you somehow, then you can find the numbers. And so I hope that it works not only for numbers, but also for functions sometimes. So let's consider this generating function. So here x, it's our variable in the Euclidean space, and tau, it's our, so to say, formal variable for which we use in our summation. And so here we want tau to be a complex number with positive imaginary part, so that this series actually converges. And so now we can consider this function, which is a Schwarz function, this complex Gaussian, and apply our interpolation formula to the complex Gaussian. And then it will be equivalent to this functional equation for this generating series. And we will see that this is actually the only possible magic function for this energy potential. So in a sense, what we do, we take our magic function and extend it in this parameter, which was our real parameter for real Gaussians. But now we extend it to the half plane. And so what we get this functional equation, but secretly we have two more functional equations for f and f tilde because of the way we have constructed it. We know that f is not exactly periodic, but it's, so to say, linear periodic function, and f tilde is also a linear periodic function. And here you see again, so if you look at these functions, f and tilde as functions of variable tau at the upper half plane, we see that all these transformations we are doing to tau, they're linear functional transformations, and they all, again, span the discrete subgroup, which is the full modular group. And so that's why we can apply all strengths of the theory of modular forms and solve this functional equation explicitly. And actually, from this functional equation, the contour representations appear naturally because this is the standard way to solve functional equations of this type. And so now after we have solved this functional equation, we have obtained an integral representation. I will not write it down for you, but you would have to trust me that it exists. And we have to have a rather explicit kernel in this integral representation. And so now the final step in the proof is, of course, to verify the inequalities of Kohn-Kumar theorem. And this is where we again need computer to help us, because this time we have a function not of one variable, but actually two variables. Here R, it's our real variable, and alpha, it's also our real variable. So we can, after some massaging this function a little bit, we would have a function of, for example, on a unit square, but it's very explicit, but still rather complicated function. For example, it includes polynomials, logarithms, and elliptic integrals of points in this integral. It's a rather long expression, and so here we would need a computer to check, to verify that indeed it is positive. And so this was a program which was first version of program was written by Stephen Miller. And I think it took like several days on a supercomputer in Rutgers to run that. But then we have actually, again, I say all co-authors except of myself, because and we actually, Henry and Abhinav, they worked, I think, the hardest on making a better, somehow faster version of the program. And the last version of the program, I think it runs actually few minutes or even seconds on a laptop. And so here I would like to stop and to thank all of you. And maybe as a last speaker, so maybe I also want to thank organizers. I think they had very difficult job for this Congress, and so thank you very much.
Thank you, Marina, for the beautiful talk and the beautiful mathematics. Amazing.
Okay, so maybe to questions. So I haven't prepared a slide to.
Any questions?
Yes.
Okay. The usual suspects. Yes. Okay.
Beautiful talk, Marina. So I couldn't help noticing that many of the techniques you presented work in any dimension. So if your dimension is not 8 and 24, what goes wrong? Is it because the functional equation doesn't have a unique solution anymore, or because the functional equation does have a unique solution, but the inequalities are no longer true?
Yes, maybe I can even show it to you. Okay, exactly. So what is wrong is that blue and red plot, it's just two lines don't meet. Okay, so this, because here in terms of, okay, where was it? I think it was. Sorry. Okay, so here in terms of numerical optimization, I think, at least in these smaller dimensions, we are quite confident about this. Okay, so the red line, of course, it's a numerical line, but we know that it's pretty good. And so also in the small dimensions, we do, okay, maybe not up to 36, but maybe here up to, I don't know, 10. We are pretty confident that we do know the best configurations. And simply two bounds don't meet. And we even could have an actual explanation to it, and I think recently Henry has a paper on it, and there are more papers appearing, so like proving bound on a bound. So this, the linear programming method, it has some obvious, I would say, limitations. So one could have something like, for example, one-dimensional object which mimics the distance distribution in a packing, even though it does not correspond to any kind of packing. And as those things exist, they actually prevent us from proving correct bounds.
So there's no analog at all of the magic functions in other dimensions. I mean, this strategy just stops working somehow.
Yeah, so it has to, we have to, I mean, okay, so maybe it depends on what you call this. So the Kohn-Elkis theorem, yes, it does has it with limitations. Of course, we can be creative, we can replace it for something by something else. For example, there is another field called semi-definite programming. So as I told you here, so, okay, so we are working in this realm of, okay, what I've done, everything, it all worked with, yeah, so we have this positive definite functions. And this is a very nice cone, but unfortunately it's too small. So the cone we really want to work with are copositive functions. But those are difficult to understand. And there are also many ad hoc methods how we could construct more functions which are not positive definite, but copositive. And yeah, then we also could try to do it in some systematic way. And yeah, so in this sense, if we are, when we are replacing cone of the positive definite functions by copositive ones, I think it's also there is a theoretical, more or less theoretical result, I think, by Frank Valentin and okay, I forgot the name of. There's a second co-author of that paper, but I hope you forget me for forgetting. Yeah, I think also David together with David Delat, where they show that somehow having access to this positive cone essentially gives us the solution. Unfortunately, we don't have that, and it's somehow we know that it's a very complicated cone, very complex from computational point of view.
Thank you.
Other questions? Yeah, go ahead. There was somebody behind you who was quicker.
Yeah, maybe just to follow, I had a similar question. What about other exceptional groups like E9, E7? Do they satisfy some, or are they like winners in other competitions?
Yes, so I think the E6 and E7 lattice are quite nice, and if I'm not mistaken, I think they do give. They are believed to be optimal, but okay, might be wrong. But there is a very beautiful paper by Conway and Sloan, where it's called All the Best Sphere Packings, and they describe what they believe are the best sphere packings in dimensions from like 4 till 10. But I think E6 and E7 are in that list, even though we see that the linear programming method does not work for those. So.
And then if there is a analogous problem defined for generally groups or like say sphere packing on spheres or something like that.
Yes, a sphere packing on spheres is maybe something like spherical codes.
Yeah.
Yeah, so there is this like problem of kissing spheres, and of course it can be replaced more general by the problem of spherical codes. And yeah, there are some. Yeah, so it's a very kind of field where there are some special configurations for which the things do work. But for like most values of but those are usually like very rare exceptions, and the generic, more or less generic problems are usually very complicated.
Thanks.
Thank you. Yeah. Just pass it on.
Hello. Could we look at one of the last slides with the functional
which
equation?
Which
with
one?
capital F and F tilde.
Okay, this one or this one?
Yeah, and we can look here, for instance. So here, of course, you have a very important transformation on the upper half plane, that you work with this reflection of -1/tau.
Mm-hmm.
And you have an equation like that, what's written there, and some periodicity conditions.
Mm-hmm.
Now, what do you think about more general equations of this type? Could you have other kind of reflections and maybe like 2 reflections? One term, like you have first term, and then 1 term involving a reflection, and the third term involving a second reflection.
Yeah, one could look at it, and it. Yeah, so I think it all depends on details.
Yes.
Oh, yeah, I think at least for my method, what is important is there is some discrete group behind all this.
Of course,
and
yes.
Yeah, so probably the question you would like to write, I think it's so here it will really depend on whether there is a discrete group of on the background, and also this what we will get from equations like this. It would be some representation of this discrete group, and it will also depend on whether we can understand this representation, because here, like this functional equation, it leads to a certain representation of SL2Z, but it's a very nice representation which we can somehow understand very well. So it's a symmetric square, and also the another like rather nice representation. But on the other hand, the representation might behave in a more difficult way, and then it would be a more difficult story. Then maybe modular forms will not come out. There will be some other types of special functions. And if the group is not discrete, then I actually don't know what will happen. Then it will be a very difficult story.
But suppose the group is discrete and so on.
Yeah, then I think it really depends. Okay, if group is discrete, then it's already a good news. But then, I think it depends. So maybe the linear representation will be difficult, and so here again, like when we write like solved explicitly, here we would probably have to define what it means to solve explicitly.
Yes.
So.
Okay.
There was a gentleman at the end over there.
Thanks for the very beautiful talk. I have two more questions. One is regarding the graph of this optimal packing density. So is there, like, because when I'm looking at it, it looks quite jagged. Is that like expected behavior, or is there some kind of monotonicity or convexity expected to be in there? And then the other question is about this, that are these, like, at least to my understanding, these currently best known packings are all periodic. Could there be some aperiodic lattices which would like give better packings than periodic ones?
Yes, okay. About function, I did not understand. Okay, so
I mean the where you had the dimension in one coordinate and denseness in the other.
Okay, it's not the right plot. Sorry.
Yes. This one.
No, I think we will. Okay, so if you see this case here, this line that does look rather sporadic, and I think it's okay. So at least maybe we do have confidence in many of these numbers, and I think there are of course somehow some relations between solutions to sphere packing. For example, if we have like sphere packing in small dimension, then we can use it as Henry told us yesterday. We could use those, for example, as layers and construct something in slightly bigger dimension, and this will give us some relation between values of this curve in different points. At the same time, if we have something in big dimension, we can try to something project. Also, there are geometric constructions which, like from having good high-dimensional packing, we still believe that we still can construct smaller dimensional ones, which are not too bad. But in general, yes, I think there is this chaotic behavior, and so probably like this peak here and this peak here, they are true peaks, and And so your second question was about?
Yeah, about the structure of the packings that.
Yes, it's very mysterious. So I really like, if you one thing I can suggest is really to read the paper of Conway and Sloan. I think it's written somewhere in 1990s. And it's they do give constructions in in dimensions up to 10, and already up to 10 you can see how wild this problem is. I think in dimension 10, as in all smaller dimensions, typically, okay, so first, a very typical situation is what happens in dimension 3, for example. It is that we have not one optimal solution, but like uncountably many of them. So that's quite typical. But it's not always true. So they at some point they thought that maybe all best packings can be constructed as these laminated packings, as we are taking best packing from smaller dimension and then stack them together in some optimal way and get a new one. But those seem to be that they are good in small dimensions and very bad in very big dimensions. There is something much better. Then I think next interesting thing is dimension 9. When in dimension 9 there is a lattice, but then this lattice, this lattice, it can be divided, elements of the lattice can be divided into two sets, and these sets can be continuously moved somehow with respect to each other without changing the radius of the packing. So there is lattice, which is optimal, but then there is this very strange, actually continuous family of packings which have the same density and at the same time they don't have lattice structure. And in dimension 10, I think it's the first example when there is a packing, which is the best packing is not the lattice packing. I think it's still periodic. And yeah, so there's also a question about non-periodic. I think it's a very tricky question because, okay, constructing non-lattice is rather easy, but then constructing something what is non-periodic is quite difficult. And so this seems to be a much harder question. And yeah.
Thank you.
I'm sorry, I have to make an announcement. There's a bus outside for those of you returning to the Grand Marina Hotel. And this may include you, and the bus is going to leave if we don't finish. So I'm sorry, but I can't have any more questions because we don't want our people here stranded. So let me just finish by thanking all the participants here and thanking especially our Finnish organizers who have done such a wonderful job for us here. Thank you.
Test, 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 mikki testi, mikki testi, mikki testi.
Saatko juteltua mulle jotain nättiä, mukavaa? Mä oon täällä Kaiun ulkopuolella. Luoko sinne sali oikein hyvin täältä? Pätki, tarkoitatko silleen niin verkkoista? Joo, mutta muuten kuuluisi niin kuin soundit. Varmaan kyllä. No mulla on 4G täällä kuitenkin. Okei, joo. No pätkimiselle me ei voida tossa mitään. Se voi johtua siitä Aalto-Openista, että mä sautetaan se tuohon lankaverkkoon huomenna. Ja onko meillä tarpeeksi kaapelia siellä päässä, että me voidaan vetää sinne Mulla ei ole jatkopalaa mukana, mutta olisiko... Mä katson täältä näin huviksi. Onko tää... Joo. Terva. Joo. Voidaan, joo. Jes, kiitos.